Good morning, everybody. I am Alberto Del Bimbo, and I lead Work Package 5 of the AI4Media project. I think most of the partners of the project are connected already, so very few words to resume the goal of the project. As many of you know already, the project goal is to create an European center of excellence for media, society, and more in general for democracy. We have a number of objectives in the project. One of that is doing research on the different topics on production of media, new tools for production of media, risks and solutions for introducing artificial intelligence in the society. And one of them will be discussed, privacy, with the next invited talk. We have also other goals concerned with the technology transfer between research and society. And finally, also we have a PhD program where most of you already and other will follow have given courses to PhD students on artificial intelligence technology. So today we have the workshop that is organized by Work Package 5 of the project. And this is a work package related on creating new tools for media production and distribution. So we have 14 speakers today, plus 2 keynote speech, one given by Professor Mohan Kankanali that will follow in a few minutes, and the other from Professor Smitton that will be in the early afternoon. So given the number of talks we have reserved 40 minutes for the invited speakers and 20 minutes for the ordinary speakers. So we please all of you to stay within the time limits, not to have this workshop finishing in the late night. So we also have moments for discussion at the end of the sessions. And the general idea is to have few questions per speaker, and then using the break session for open discussion on the talks that we had in the session. So given that, it's my pleasure to introduce an old friend and distinguished speaker, Professor Mohan Kankanali. He is a well-known researcher in the multimedia community. He is presently chair professor of computer science at the National University of Singapore, but is also the dean of the School of Computing in the same university. He is a well-known and respected researcher in this field from many, many years. And particularly in the last year, he has launched and lead a research center working on key topics like privacy in using multimedia technology and relationship of this multimedia technology with societal needs and context. So today he will give a talk on privacy-aware analytics for human attributes from images. So it's my pleasure to give the room to Professor Mohan Kankanali for this invited talk. Mohan.
Thank you very much. Thank you very much, Alberto, for the kind introduction. Let me share my screen. And if everything goes well, you can see my screen.
We see that.
And I'll go to the full screen mode. So I think given that you have a lot of excellent speakers and talks and the time is tight, so let me launch straight away into my talk. So basically, I'm going to talk about privacy-aware image analytics, really. And this is work done in my center, Encrypt, which is the NUS Center for Research in Privacy Technologies. And this work actually has been done with my collaborators. Anshu, she's my master's student, Zichi, PhD student, and Xiaojing is a senior researcher in my group. And the work I'm going to describe today, most of it will be presented in the ACM Multimedia Conference in October. So this is kind of a preview to that work. Okay, so my talk is in 4 parts. I'll talk about the motivation, then the human study, computational modeling, and some conclusions. Okay, so let me start here. Uh, as all of us are individuals, and how would you feel if unknown to you, your photo is publicly available in some data set? Okay, and the worst thing is that it might be further exploited. For example, if you are aware of the tiny image data set, they have collected random photos from all over the world, including could be yours, could be mine, I don't know. And they classify each of the images against these categories. And I think that is quite offensive, to be put against a classifier that you are a child molester or not. It's a bit crazy. More importantly, I think we are aware that there is a need for facial privacy. I should not be talking about the need for facial privacy to Europeans. You are the people who have actually pioneered privacy regulation in the world. And a lot of countries in the world which are following. Singapore has a strong privacy law. US has passed the law. India is passing the law. And surprisingly, even China has recently passed a privacy law. So privacy is becoming very important, and we know all the reasons, right? People can do profiling attacks, there can be abuse on social networks, algorithms can inappropriately use it, and also it can be inappropriately used by authorities. For example, you are a protester somewhere, takes a photo, and then they use to prosecute you. So then the question I would ask is the flip side. Is facial analytics at all useful? I mean, if it is so bad, is it useful? And I'll give you an example where indeed it can be useful. For example, the place where I live in Singapore, nearby we have a departmental store where I normally go there to buy grocery. And to me, it is useful if they know that an Indian person buys grocery so that they can stock up items, some of the spices and the masala dal which Indians use out there. So from that purpose, if they have a video camera system in the store and they do analytics to find out what fraction of their customers are Indians and therefore put items in the store which will cater to the Indian customers, I don't mind. But they don't need to know that it is Mohan who is visiting the store. All they need to know is some Indian is visiting the store. They don't need to know exactly I am this thing. So analytics is useful in getting some attribute at a gross level, and it can be useful to us human beings in society. So the question is how to balance the trade-off between privacy and visual analytics with faces. So can we obtain the benefits without sacrificing our privacy? So that is the question. And I think our philosophy, and I think hopefully you'll not dispute that technologies should, as much as possible, aim to accomplish a task without compromising the privacy of a person. So in our work, our take on price, so there is a privacy utility trade-off, right? I mean, if you make the the image completely encrypted, you get full privacy but no utility. And if you don't do anything to the image, you get full utility but no privacy. So in this study, our context is we want to study the human attributes of age, gender, and emotion from image data. And for privacy, we use blocking obfuscation techniques on the faces for preventing identification. And we actually consider various privacy scenarios by increasing the amount of blockage. So in the lower set of the images, the leftmost face is the original image, no blocking. Then second is the eye blocking. The third one is the lower face blocking. The fourth one is the face blocking. And the fifth one is the complete head blocking. So we're going to study all the scenarios because we want to understand what can be done by how much blocking. Okay, so now before we started that, we actually tried to do a empirical human study. So our question was the following, that we'll create a data set and we'll do a study on by humans. And the idea is that can humans actually do this task when you block the faces? Because if humans cannot do it, then it is hopeless for our machine learning algorithms to do it. So we actually first wanted to do a human study. So let me delve into that. So first what we did is we first looked at some data sets are there available, but we found that there is no good data set. Mostly there were only pedestrian data sets from surveillance, no general purpose data set without diversity. And also there was no diversity in terms of the ethnicity, ages, gender. And the annotation was not so good. So one of the first things which we did was we created a new data set called the diversity in people and context data set called DPAC. And this we have made publicly available. There are about 8,000 images with more than 10,000 annotated targets. And it is very well balanced in terms of the diversity in variety of ways of geographical diversity, ethnicity diversity, age diversity, gender diversity. And we have given extensive annotation. So the second part I will move on to is the human psychophysics experiment. And this is where we did a human study. So here is the terminology for our human experiment. For the image on the left, the target is an individual whose privacy we are going to stop. So this boy in the front whose face is green is the target. So the everything else we call it context. And also we have another term which is called the situational context. So context is the face, sorry, the target is the individual, context is everything except the individual's face, and the situational context is everything except the face and the body of the target. Okay, so that is the terminology, and this is standard terminology in psychology, and that's why we borrowed it from there. So what we did is we took these images from our data set and we created four scenarios. One is cropped obfuscated. We took the target and then we blocked the face. Then we took the full image and all the faces we blocked. Then target obfuscated, the number three is the full image, but only the target whose privacy we want to protect is blocked and the rest people are not blocked. And of course, finally is the original image with no obfuscation. And what we did is we made humans observe these images and we asked certain questions. And we use an eye tracker to track their eye movements. So what we did is we basically wanted to ask two questions. First was, how accurately can humans predict these attributes? The attributes are age, gender, and emotion. As I said, if humans can do with blocked faces, then I think there is some hope that we can train our algorithms to do that. So as far as, so you can look at the bar chart on the left. For age, the highest bar is 78%, which means if you present the whole image with no obfuscation, human beings can guess the age uh, with some amount of categories. The categories, the quantization is on the right hand side, which is the age group less than 19, 19 to 24, 25 to 34, and so on. With 70% accuracy, humans can do it if there is no blocking. And if you fully block all the faces, it drops to about 59%. So it's not too bad. As far as gender goes, uh, if you have a full image, we can get 91.5%. And if you block all the faces in the image, it drops to about 82%. Again, which is not too bad. That means humans we can guess. And as far as the emotions go, 84% when you have no blockage, but it drops to about 52% when you block all the faces for emotion. So emotions has the maximum effect in terms of the blockage. The second thing which we wanted to ask in our human study was, Given that when we block the face, still human beings are able to guess uh, more or less quite well age, gender, and emotion. So what are the cues which are exploited by the human observers? And what we did is we basically studied the eye tracking data in order to understand what the humans are looking at. And then basically we did very careful analysis of that data. So these were our observations. I'm kind of going fast because I have limited time. So number one, we found that the situational context is very important in the age and gender prediction, because situational context is everything except the target. And this is reasonable, right? I mean, for age and gender, we look at other cues. For example, what is the person wearing, the clothes, the hairstyle, maybe other nearby objects, and this thing for the purpose of guessing. The second observation, we found that for guessing emotional prediction, the objects and background information like the events and the scenes in an image have a strong contribution for emotion inference. And that is obvious, right? If the scene, for example, is of people in a birthday party, and if you block all the faces, then since you can guess that the context is a birthday party, then more or less you can guess that the emotion on the face of the blocked person is probably a happy emotion. Okay, so it's a guess based on these contextual factors. So it's not surprising, but I think we wanted to study to what extent it does. The third observation, this was slightly more interesting, was the emotions of other nearby people play the most significant role in inferring the emotion of the target whose face has been blocked. And furthermore, the emotions of the socially interactive person in close proximity to the target have more weight in such inference over the emotions of other people in the image. And this is very natural, right? If one person is talking to another person and having a social interaction, it is likely that the emotions shared by both of them are similar. It is highly unlikely that one person is extremely happy and the other person is extremely sad, and they are having a social interaction together, right? So this is reasonable. And the fourth observation, we found that there is in terms of the situational context which is exploited by humans when the target face is blocked, uh, for emotion the faces are more important uh, than for age and gender prediction, and with the gender having the least dependence on the face, that means the face of the other people around. And again, this is reasonable. Okay, so this was basically in short the findings from our human study. And we actually followed up with a post experiment survey. So we made people watch the images, and we asked them to guess and predict the age, gender, and the emotion. And after that, we asked them the question, what factors did you use to guess emotion? What factors did you use for age? And what factors did you use for gender? And their answers, which is the conscious answers, not the involuntary eye gaze data, the saccades and the fixation, more or less corresponds with the eye tracking information, that they focus on the human body for gender cues, for the context, for some of the event, and therefore guessing the emotion. So these were kind of aligned. So that was gratifying. So the next part was, okay, now that we know human beings can guess age, gender, and emotion. So our question is, can we now design a computational model which can do the same thing? And more importantly, we have made some observations from our human study. Can we incorporate these observations in our computational model? Okay, so that was our intention of building the computational model. So the third work is or basically we design a deep learning based model to predict these attributes under privacy preserving conditions. So basically, we basically designed a network, context guided human attributes prediction network. We call it ChapNet. It is basically an end-to-end multitasking human attributes classification model. Has two branches, as you can see. There is a target branch and a situational context branch. And mind you, one thing which we, unlike any other deep learning models, which explicitly encode the facial information, we don't make use of the face information here. And let me go into some of the details of the design of this network. So basically, let me start with the target branch, which uses multiple features. So basically, the input is the target, which is the cropped part of the image. So this is the person whose privacy we are preserving. And basically, again, for it, there are two parts. So we capture the global features. The global features are basically determined by using ResNet 50. And basically, we take the global features of the target and get a feature map of this target person and the occluded regions and in the larger spatial dimension. So that is one part. Then, so it has two branches here, the global features and the pose related features. So let me now go on to the pose related features. For the pose related features, what we do is we take this target and we use the open pose work to figure out the 18 pose landmarks. And based on the 18 pose landmarks, we create 18 two-dimensional Gaussian heat maps centered on these landmarks. And if the heat map, that means if that particular landmark is not salient, we set it to 0. Otherwise, we binarize it to or we make use of it. That means noisy features we ignore. And this heat maps we multiply with the global feature map and do some average pooling. The whole idea is we wanted to emulate the eye saccades, the eye saccade movement, which we found through the eye tracker in capturing the local features of the target, which the humans used in inferring the doing the prediction. So this is from the target. So the target gives us some cues. So that is one major branch of the network. The second network is the context branch. So the context branch has again three parts. So what we do is, one is what we call it as F event. So we try to figure out. So what we do is we use the pre-trained model on the Places 365 data set to capture the event and scene related features. So this is very important because it tells you the background context, what kind of a scene this is. Is this a birthday party? Is this a classroom? Is this a meeting? Is this just a crowd? So we get a lot of information on the background event scene. So this is using the PlaceNet training on the PlaceNet data set. So that is one part of the situational context branch. The second part is we basically try to do the ResNet 18 model. We capture all the other humans in that, and we all the other humans and objects in the images. So we basically use an ImageNet and try to detect all the humans and objects in the image, and then we feed it into the object features. Because as I said earlier, in the context, if we figure out this is a classroom, then there is a screen behind, then we detect the object called the screen, which gives us a cue. What is the kind of the scene? The third thing what we do is, remember, for guessing the emotions especially, the social interaction was very important. So what we do is we basically build a graph attention network of all the people detected in the images, and we create basically a social network graph. And with attention, that means we weigh an attention, so the person who is closer to the target whose privacy we are preserving is given more weight. Okay, which is again trying to basically infuse the idea from our human study into our architecture. and we kind of do that weighting in the graph network. So we get this target information, and now we get this contextual information, and we basically if you see the network here, we then take all of these features, and we do a max pooling, and then basically we estimate the emotion, gender, and age we output. Okay, so this is our network. And now I'm going to move on to the last part of my talk, which is what did we find. So other than the data set which we created, we also tried to use some standard data sets which have been used for emotion detection, which is called the emotic data set. IOG is the images of groups. This is a people data set. People use it for a lot of people related research. And also CAIRS is another context-aware emotion recognition data set. So we use this data set because these are the standard benchmark data sets. So the first thing which, and then of course, this is the kind of parameters, the training specifications we use. We basically use a cross entropy loss. We use the mean average precision as a metric. And these are the kind of the training parameters, the batch size, learning rate, the decay rate, and we basically use the standard gradient descent optimizer. Okay, so the first thing what we wanted to do is uh, our network is actually totally new network. So when we don't do any phase obfuscation, how does our network compare to the state of the art for emotion detection? Okay, so for emotion detection, we compared, and for on the CAIRS data set, actually our basically average was 88%, which is actually better than any of the state-of-the-art methods. Of course, some of them we could not do because the data set or the data was not available, or the code was not available. In terms of the emotic data set, we beat all of the state-of-the-art methods except one, the Trisha et al., which actually uses some extra information. So they use some extra information, but we do pretty well. We got a 28.81 on the emotic data set. Just to let you know, how did we do the obfuscation of faces in our data set is we used OpenFace for pre-processing. And we get the 67 landmarks which it detects, and then use the eye region, face region, lower face region blocking, and the head blocking in order to do that. And of course, you may want to question, is our face de-identification reasonable? Did we do reasonable? So what we did is we took a lot of the celebrity from the celebrity data set. We took a lot of the celebrity faces and we applied our obfuscation. And then what we use is there is the Amazon face recognition algorithm called Amazon recognition. So if you see the leftmost images are the original data set on which the Amazon recognition algorithm works correctly for 98% with 98% confidence. And for our obfuscations, actually all of them failed on the Amazon recognition algorithm. That means our face obfuscation is not bad. So we wanted to kind of do a sanity check on that. We actually did some interesting privacy settings in our training images. So we did where only the target was obfuscated and we trained the network, or we did all the faces in the image were obfuscated, which is a strict privacy condition for the training. Or what we did is partial privacy. That means for some images, we did the full obfuscation. For some images, we did no obfuscation. That means the fraction of the training images are obfuscated and not all. And we wanted to study this scenario because this is more realistic, because what we can do is we can mix. For certain people, we can give consent and they can actually not have their faces blocked. Plus, we can have some people who have not given their consent, so we have the blocked faces. Can we mix these together and train the network and see how well it performs? And that is a useful, realistic scenario to have. Okay, so this is basically our results, the effect of face obfuscation. Now, there is a lot of information here, so let me parse here. So DPAC is our data set. And if you notice, the bottommost row is without Intact means no obfuscation whatsoever. So if we look at for age, if we do no obfuscation at all, we get 66.73 accuracy. For gender, we get 91.12 accuracy, and for emotion, 72.66 accuracy. On the other hand, if we do TO is target obfuscation, and we do the full blockage, which is BF. So target obfuscated with full blockage, 66.73 drops to 57.52. It's a drop, but not too bad. In terms of all obfuscation, that means you block all the faces in the image. From 66.73, it drops to 56.02. Again, not too bad. For gender, from 91, oh sorry, this one is 51, sorry, it's 66 to sorry, from 66 to 51 and 66 to 52 for age. For gender, from 91 to 73 for target obfuscation, and from 91 to 77 for all faces obfuscated. For emotion, from 72 to 55 for target obfuscation, from 72 to 54 for emotion obfuscation. Sorry, for all obfuscation for emotion. So it's not bad, it's pretty good. So what we did is, of course, if you only do I, then it is from 66 to 63. For lower face, 66 to 60. Only face, 66 to 57. And for full head, 66 to 51. So obviously, the more you mask, the less accuracy you get. So it monetarically drops. But even under the best privacy scenario, that is the full obfuscation with all the target obfuscated, our chapnet is uh, able to perform far better than chance. And in fact, for gender, it's pretty good. It's almost 90%, for emotion, 72%. So this is actually quite gratifying. And one thing which we wanted to study is, what does our model actually look for when we block the face? So these are the different privacy scenarios. So this is an image, and this is no obfuscation, and this is full obfuscation. And then we wanted to study the second last layer. What is the network paying attention to? So if you notice, if there is no obfuscation, then our chaplet pays more attention on the face. But when it is trained with fully obfuscated faces, it focuses more on the body, which means it tries to go for the contextual features, which is reasonable, right? So which means that what we intended for the network to do, actually it does. So it aligns with what the human beings did. That means they looked at the contextual features. So our network kind of mimicked what the human beings did. Also, as I said, we wanted to study, can the model perform better under partial privacy? So what we did is, we had, so 0 means basically our non-obfuscated, that means no obfuscation. 25% is 25% of the faces are obfuscated. 50 is half the images are obfuscated. 75% obfuscated, and 100% obfuscated. So obviously 100% obfuscated, it drops from 72 to 54. But if you get 25% obfuscated, it drops from 72 to 70, which means that if you are going to do an analytics model, and in which 75% of the data is not obfuscated, that means you get consent from those subjects to use their data, but 25% you take real world data where you actually obfuscate their faces, the accuracy you get is, there's hardly any drop, which means that this is a very realistic scenario which you can use in a real world application. Some people who have given consent to use of their data, some people who have not given consent, and therefore we can still use it in our deep learning model. Okay. Similarly, for emotion, from 66, 25% obfuscation drops to 65, 75% obfuscate drops to 62. For gender, from 91 to 90, 88, 87. So it's not bad. So partial privacy is actually not a bad idea. It is a good compromise for training deep learning models. Okay. So our observations are that the results are encouraging enough that we can continue this research to do analytics with privacy. Basically, incremental phase obfuscation led to drop in classification accuracy, but even in the extreme privacy scenario, the strict privacy with full head obfuscation, we do much better than chance. And this model design can be used to analyze other human attributes such as ethnicity, or we can go for higher level relations, social relations, or even personality traits. And the minimal difference between target obfuscated and all obfuscated suggests that we can actually do all obfuscation in our studies. And partial privacy is a good way of going ahead in this work. Uh, and also what we did is one in other interesting thing. Since we did this research during COVID times, there is this RMFRD dataset, real world masked face recognition dataset. So we used this dataset and applied our ChapNet on this, and actually it works pretty well. So this is not real privacy, but people have put on masks. And some people think by wearing masks you get privacy. Actually, it is not. We can actually do almost all analytics with masked images. So that was interesting to know. This was just a fun experiment which we did on the side. Okay, so I'll come to the last part. My sense is this is just the beginning. We need to do more work. Context can be insufficient and face might be better estimator. We found, especially for babies and for certain types of poses, our method does not work. It gives the wrong prediction. Also, context can lead to bias in prediction. For example, this is in the second column. This is a female teenager basketball player, but it wrongly says it's an adult male, because most of the data sets have basketball players who are adult males, and it wrongly predicts. In the right image, here is a man who is wearing a pink colored costume, and our network wrongly predicts that it's a teenage female, because somehow they think females will wear pink color costumes, and teenagers wear costumes and not adults wear costumes. Also, I think I want to put a caveat that just obfuscating the face will not guarantee privacy. And if there is a very strict privacy requirement, then you need to probably block out the entire body. Again, that is something. So our ongoing work and future work is we are trying to develop more facial analytics for other attributes. Very importantly, we are also extending this to video. Video analytics is very important. But then there is also the motion cue, and we don't know the impact of motion cue on gait, on tracking, on these things. We are also using the exploring bias in the features of a lot of the face this thing, and especially I think many of these data sets are highly biased in terms of the skin tone representation, and we are trying to study the impact of bias in these algorithms. One very important thing I want to highlight is the ethical implications of this research. Now, a lot of people want to obfuscate their face because they don't want to be detected or identified, because there is a lot of cases of abuse and discrimination on social media, for example, discrimination against women, or there is unconsented commercial use, that means pushing ads by social networking sites. And therefore, the exploiting of contextual cues for inferring attributes of de-identified person in visual data can therefore potentially pose ethical concerns. As researchers, we realize that, and therefore we say that we only advocate use of our research for face analytics with privacy only for ethical applications. I think we need to make this very clear. We do not propose that our research should be used for unethical applications. Okay, so with this, I come to my last slide. The summary is our human study shows humans indeed use contextual clues for determining facial attributes to emotion, gender, and age when you block and to give privacy. ChapNet is a deep learning model inspired by our human studies, which can do privacy-aware facial attributes analytics reasonably well. I think this is an important and exciting area, since more and more images and videos with humans are being created and shared. And privacy is a growing concern for both from the user perspective, and even if you are a company, then you have to be compliant with the privacy regulation. And if you are a regulator in a country, then I think it is very important to impose these privacy laws. And to me, it is also very exciting for research is there is lots of open research problems available in this area. And I think we are just beginning. Privacy preserving analytics is just starting. With that, I want to end. Our code and data is available. Thank you very much.
Thank you so much, Mohan, for this very, very interesting talk. I think the talk is perfectly in the shape of the AI4Media project. So, do we have questions? Quick questions, quick answers, please. Any question?
I have a question.
Yes.
Lorenzo, hi. I was wondering, I'm not even sure if this makes sense or is it possible, but have you thought of performing a human study on partially occluded faces identity recognition? Because you did the human study on attribute recognition, and then you show that algorithms cannot actually recognize faces like the Amazon pipeline is not able to, but what about people? Have you thought about that?
Great question. We have not done that, but so I didn't think of it. That's a wonderful idea, which can be done because can identity be recognized? So I think clearly one can use the celebrity data set and then obfuscate and try to see if people can recognize. Now I may it may work. I mean, depending if the person knows a lot about the celebrity, it may be possible. I don't know, but good question. I don't have the answer because we did not do the study.
I have a question. Sorry.
Yeah.
So first of all, thank you for the presentation, Professor Kankanhali. I would like to know if instead of obfuscating the face, you store an embedding of the face using models like FaceNet, and
Okay.
and then you can keep the anonymity in the database and still be able to predict the features that you want to predict.
Yes. So this is again a great question, and basically what you are saying is instead of sharing faces and this thing, we share the representations, and the representations provide anonymity and yet can provide the utility. Actually, we have some ongoing research, and we are still doing that. We are exactly studying this problem. Unfortunately, representations can leak. You can invert. You can invert the representations, and having a non-invertible privacy-preserving representation is again an open problem. We don't have a solution, but we
And
know for sure representations we can actually infer the identity.
because okay, the issue could be that you can reverse engineer the face to recognize the person.
Yes.
But then how does your model ensure it? Because it could be maybe that the Amazon face detection test that you did failed due to the difference in the distribution of the input. Because now your input has black patches that were not at the training time of the
Yeah.
Amazon
Yeah.
face detection.
Yeah. Yeah. So I think again it's a great observation. I think one needs to do some systematic studies in order to do that. But I think many people are thinking of sharing representation, in fact, sharing of machine learning models for privacy. So the whole idea is instead of sharing a data set with people, for example, it's a health database, right? There's very private information of health. So I train it on the data set, and instead of releasing the health data set, I release the trained model. But in fact, one of my colleagues in the NUS School of Computing, Reza Shokri, has shown that is what is known as the membership inference attack. You can actually find out the sensitive data. And people are trying to figure out how to mitigate this attack. But I think what you asked is slightly different. And I think that is something very interesting to think, that how can we make privacy preserving learning representations?
Yes.
Great open question. I think nobody, actually, to the best of my knowledge, nobody's done any work in this area.
Okay. Thank you so much. Thank you.
One more question, if any.
Sure.
I have a very final comment. You mentioned in the last slide as a future topic of investigation use of video. Indeed, reality is dynamic. So if we want to use your research in a real context, video should be an issue to investigate. So where do you believe video will have impact to improve your performance figures, either on gender or age or emotion?
I think definitely age and gender, absolutely, because I have another colleague who is trying to do uh, privacy, basically identifying sensitive information from human gait. So I have a colleague, Terence Sim, who does research in that, and basically he says gait information reveals a lot about you. In fact, if you carry a mobile phone with you which has an accelerometer, the accelerometer actually captures a lot of your gait information, and that can reveal a lot about you. It can reveal your gender, your roughly your age, and lot of things. So so I think video is a rich source of data, and in fact it is scary because people can find out a lot of things about you. And how do we obfuscate videos in such a way that people are unable to do that and provide privacy? It seems to be a difficult question to me.
Yeah,
So it's
sure.
going to be even harder than images. But
Sure.
I think
Thank
it's
you very
very important because so many videos are being captured everywhere.
Sure. So thank you very much, Mohan. I think it's time to pass to the first session of the workshop. So, Hannes, are you online? Yeah. Can you
Hello,
take the
welcome.
floor and lead the session? Thank you very much.
Yeah, I think you can see my presentation now, or do you? Yeah. Do you see my presentation?
Sure.
Yeah.
Yes.
Okay, so welcome to the first session with 5 talks, and several of them will be related to the problem of data scarcity. So that's when you have only a few data samples to learn from. I will give a sort of an introduction talk first. All right, so let's make it big. So I just need to keep also a bit look at the timing. Okay, so what's the motivation there for future learning and for what's the issue? So state-of-the-art deep learning algorithms usually, if you're training them from scratch, you need a large annotated data set for training them in order to succeed. For example, for image classification, you need in the order of hundreds to thousands image for each class. So the famous ImageNet dataset, which has 1,000 classes, and for each image class it has around 1,000 images, which is quite a lot. And it's often not possible or too expensive to gather and annotate such a large data set. On one side, there simply may not be enough data samples for your task. For example, when you are training, which is often the case in industrial inspection, so online assembly line inspection, when you're training a defect detector for online quality inspection, these defects, of course, they are occurring not that often. And so you have just a few samples of how your defects look like. On the other side, it might simply be too costly to annotate all the data sets, all the data samples, even if you have a large data set. Because of course this annotation has to be done manually. And if you want to have a high quality data set, for example, in the MS Coca data set, they were doing not only annotating an image by one person, but by multiple persons. Yeah, so for example, the MS Coca dataset, it has nearly 3 million human-labeled object instances in more than 300,000 images. And for each image, you have to annotate the bounding boxes, but also a sort of an object mask. And yeah, I couldn't find out how much that really was, how much the cost was for Microsoft to annotate this data set, the MS Drucker data set, but it must have been quite expensive. Okay, so there are, because this is a very common problem, actually, there are a variety of approaches to work around this problem of data scarcity. So, and you can coarsely group them according to the slide here. So first of all, you have transfer learning, which is very popular. So you have here a pre-trained model trained on one of the big open source datasets like ImageNet, and you have your small custom dataset, and you're fine-tuning the pre-trained model on your small dataset. Another possibility is to generate a synthetic dataset for training. For example, for object detection, you could think of taking random images as background and overlaying on this background your objects, several appearances of your objects. So you just overlay them randomly on your background, and of course then you have automatically also your ground truth, so your segmentation mask for each image, for each training image. Then you have the field of domain transfer and domain adaptation, where you transfer an existing available data set from its original domain to your target domain. So, for example, if you want to classify or detect something for cartoon images, you could think of taking one of the big photo databases, or of one of the big data sets which have normal photos, and transferring them, converting the photos to a cartoon-like appearance, cartoon-like style. So here you're often using generative adversarial networks, so the famous GANs, for this task. Then you have the whole many approaches which belong to semi-supervised, self-supervised, and unsupervised learning. So here you have additionally to your labeled small data set, you employ a large unlabeled, so unannotated data set. And in this talk, I will focus on few-shot learning. So these are methods which are designed specifically to handle only a few samples per class. Okay, so for few-shot learning, the task is, we will focus a bit on the classical few-shot learning problem for image classification. So the task is here to classify an image into one of n classes. And usually you, in the few-shot scenario, you have only a few samples for each class. let's say 1 to 10 or so. And this is a very active research field, and with a lot of progress happened in the last, let's say, 3 to 4 years. You can see that also in the benchmarks. For example, when you go to papers with code, you have the progress for one of the common fusion image classification benchmarks, and you can see that there is a steady progress. So for fusion learning, for image classification, you can classify the available methods into roughly 3 categories. Of course, these categories also overlap. So the first one is data augmentation and hallucination methods. Here you are having your few available samples, and from these ones you are generating more samples in various ways. So you are sort of hallucinating. Then there are the so-called metric learning or embedding methods. Here you embed your samples or features calculated from them into a metric space and do the classification in this space. And the third category are meta-learning or optimization methods. And here you transform an existing learner, so existing network, quickly in a few steps, so that it's able to classify the novel classes. And I will give for each of this category one example method. So for image augmentation methods, there is one approach which is called delta encoder, and it utilizes a variant of an autoencoder. The main principle of the method is that the encoder learns transferable deformations between pairs of samples of the same class. And on the opposite, the decoder then applies these deformations to synthesize novel samples in the feature space from a certain reference sample. So you can see the principle of the approach in the figure on the right side, where you have here in the training you have these pairs of samples, and you're training the encoder to learn these deformations, and then you have your reference images, and from these ones the decoder generates then deformed future representation. You can see that also on the bottom, there you have the samples with the there is a single image which is framed in blue, which is the real ones, and all others are synthesized samples, but they are synthesized in feature space, so on the left side, and on the right side their nearest real image neighbor is shown. And you can see that the synthesized examples are in feature space, they're quite diverse. So and with all these synthesized examples or hallucinated examples, you then are able to learn a better classifier. Then for a good example for a metric learning method are the so-called prototypical networks. And here the key idea is actually quite simple. So from the input data samples, you're learning a non-linear mapping, so feature encoding via a neural network into the feature space, into this embedding space. And the mapping itself is a simple neural network composed of 4 blocks, and each block is simply more or less standard. So you have the convolution layer, the batch norm, and then the activation and the pooling layer. And you for each class, then in the embedding space, you're calculating a sort of prototypical example, and that's simply calculated as the mean of all the class samples embeddings. And you can see that on the right side, you can see this C1, C2, and C3, which are the prototype, the class prototypes. And then when you have a new query image which you want to classify, you simply find the nearest class prototype in the feature space, and that's your output. So that's the class of this query image. And here, a normal Euclidean distance is employed. Then a good example for meta-learning method are the model-agnostic meta-learning. Is the MAML approach. And here, the key idea is that the key observation is that in a neural network, typically only a part of the network parameters, so of the layers, is task specific. It's, for example, in a convolutional neural network, usually the first layers, the lower layers, are very general. Often they look like sort of gradient operators or edge or corner operators or GABA filters. And only the higher layers, so the last few layers, are more task specific. And what MAML now does is that it optimizes for a good network representation, which is able to quickly adapt to the new image classes. And so you have here, the key thing is that you have here 2 optimization loops. The one is in the meta-learning optimization, where you are optimizing the network representation. And the other one is the normal, is the quick adaptation and to a new image class, and that's a normal the normal training, but it's sort of a fast training, so just in a few gradient descent steps. And the nice thing is that this MAML approach is very general, so it's not usable for few-shot image classification, but also for, let's say, regression or reinforcement learning or other vision tasks like few-shot pose estimation or whatever. All right, so at the end, just a few words on the activities of our research group, so Ioneum Research Digital in the AI4Media, in this few-shot learning task within AI4Media. So we are focusing here on few-shot object detection. So here you're detecting objects in an image. Usually you want their bounding box, and yeah, using only few object samples for each class. So we want here to, because usually, all the object detectors, they are able to, they are trained on MS Coco, so they're able to detect these 80 object classes like person, car, dog, and so on. But it's often the case that you want for certain use cases or search or retrieval use cases, you want simply other image classes, simply other object classes which are not contained in the MS Coco dataset. So we are focusing, as I said, here on few-shot object detection and use cases, especially for annotating material in media production and for archiving. And the use case is a bit different here from the typical benchmarks and from the typical data sets used in academics. So several ways, for example, the number of samples per class, it may differ. So you do not always have, for example, 5 samples per class. It might be less or more. And typically also new classes are added iteratively. And yeah, our approach is based on a very well-known method called frustratingly simple few-shot object detection. And yeah, we are working currently on that. So that's work in progress. We are working also on a GUI for a comfortable adding of new object classes and the samples. And we have here a GitHub repo. Yeah, that's the link. So yeah, this is a task my colleague Werner Beiler is working on. All right, so that's it for my presentation. Maybe one quick question, because I needed also the 5 minutes for questions, but I think one question is okay.
Can I ask you a question on the first approach you reviewed, the delta decoder?
Yeah.
So I was wondering how is the decoder guided in generating these new examples? Because somehow you would like to have variation in the source space, but you are generating an embedding. So can you say something about it?
I'm sorry, but I didn't delve into the paper into the details of the paper.
Okay.
So
there's a question
I
from the
cannot.
chat also.
Yeah, I'm sorry. You might have to take a look into the paper itself. So
Yeah, okay, no problem.
you can Google for it, or I can put the archive
I will
on
do
it.
that.
Yeah, I'm sorry. Yeah, I just
There's a question from the chat.
Yeah.
Could you please comment on generalizability of few-shot object detectors?
On the generalization ability.
Mm-hmm.
So they how to say the task here is not to generalize, but to learn very specific object classes which you are adding with a few samples. So it's not the task of few-shot. Few-shot learning is a very specific problem. So the generalization might not be that good, I suppose.
Okay. So are we moving to the next talk, maybe?
Yeah, okay. So the next talk will be, about few-shot object detection. So maybe Mihai can, add here more on that, also on the questions. So the talk will be few-shot object detection by Mihai Dogaria, University Polytechnica Bucharest. So Mihai, are you here? Can you?
Yes, can you hear me?
Yeah. A bit, maybe a bit louder would be nice. Could you turn up the volume a bit?
I'll try. Is this better? I'm not sure it's working right
Yeah,
now.
but you are understandable.
Okay.
So now it's better.
Okay, perfect.
So can you simply grab the PowerPoint? Yeah.
Okay. So is it visible now?
Yeah. Can you make it full screen?
Perfect.
Thank you.
Okay. Thank you, Hannes, for the introduction. So, hello everybody. My name is Mihai Dogariu. I am with the University Polytechnic of Bucharest, and I will be presenting to you our work on few-shot object detection. The summary, the structure of this presentation goes as follows. We'll start with some general aspects about few-shot object detection. Then we will discuss a bit about our approach and what we have planned for our future work. So the general aspects of few-shot object detection starts, of course, with the few-shot learning that Hannes already presented. So I won't go into much detail on this as he already presented all the necessary information. I would just like to highlight the main aspects of what few-shot learning deals with. Well, the problem statement goes as follows. We start from a base training data set, which contains a large number of images from different classes. Each class is well represented by a large number of samples. And we have this this base training data set on the left part of the screen. Then we are presented with a with a support dataset, which consists of novel classes. This support dataset contains only a few classes, so capital N classes, and each such class contains only capital K samples. This K, as Hannes already said, is usually very small, up to 10 samples for each class. This then is known in the literature as N-way K-shot. So capital N is the number of classes, capital K is the number of samples for each novel class. The goal here is to teach such a network to be able to extract information and to adapt to these novel classes where they have very few samples. Then we have the query images, which consist of images from the novel classes. These query images can contain also images from the base training dataset, and hopefully the classification will perform correctly on these new queries. Okay, so this would be about the few-shot learning. Now, if we switch to the few-shot object detection, we keep the same few-shot learning perspective, but we apply it to a very specific type of application, namely the object detection. Object detection, for those of you who are not familiar with it, consists of it's not only a classification problem, it's more complex because you have to identify objects in an image, several objects. You are not restricted to only one object. So you have to identify the location of these objects, which is a bounding box, and also to correctly classify the object that is contained in that bounding box. So we have here a classification plus a localization problem which is adapted, which can be, let's say, run on several objects in a single image. The output of such an object detector consists of bounding boxes, as you can see in the image, and an object class for each such bounding box. Of course, this is a very complex problem because, as you can see, there is a lot of overlap, there is a lot of occlusions. You may have very, very difficult classes inside your dataset and so on. Now we'll move on to our approach. Our approach consists of two parts. The first one is a two-stage fine-tuning, and Hannes already mentioned this paper, and I would like to present it and talk to you about how we adapted it. So this fine-tuning approach is from the paper Frustratingly Simple Few-Shot Object Detection, and relies on the following mechanism. So you have the data set on the left part of the screen, and this is run by an object detector. This one is a very common object detector, is the FastRR CNN, where we have the backbone ResNet architecture. It might be ResNet 50, 101, 151, or any other backbone. And then you have a region proposal network and a ROI pooling layer, at the end of which you have different regions from the image, which are considered to be objects. So then you extract the features from each such object, and you pass them on to a box classifier and a box regressor. The box classifier deals with assigning a class for the object that has been proposed by this part right here. And the regressor needs to adjust the bounding box such that it fits the object better than the box that was proposed by this part of the network. Okay, so the main idea of this work is to take a regular object detector, and after you have trained it on the base training data set, only fine-tune it on the novel classes. So by fine-tuning it, you will only look at the left part of the network, so only at the box classifier and at the box regressor. And that should be it. So it's a very, very simple approach. That's why it's also called frustratingly simple. And it works very well. So in the first stage, you have the normal training on the base data set. Then on the second stage, you freeze this part of the network. So you have a fixed feature extractor. And this is mainly due because this part of the network handles only proposing regions for parts of the image which are considered to be objects. So here you have a class agnostic feature extractor and a region proposal, which is very, very good in our case because you have all the general characteristics of objects which output from this part of the network. I think this also deals with the question that was asked at the previous presentation. So how does it deal with the generalizability? Well, if you have a two-stage object detector, the first part of it will only propose general regions which contain objects, and the second part deals with classifying those. So it's very good to have them separated in the two-stage object detectors in order to capture the generalizability characteristics of the entire data set. Okay, so after you have trained the feature extractor, you will now present it with a few base shots, so a few images from the base training dataset and a few images from the novel dataset. We are doing this in order to preserve this generalizability and do not overfit only on the novel shots. Then we keep the same loss function as in the original object detector paper in faster RCNN. We just lower the learning rate a bit and fine-tune the box classifier and the box regressor. One interesting aspect that we are faced with now is how do we initialize the last layer of this network? Because if we add novel classes, of course, the last layer of the network will differ in size. It will increase by the number of classes that we add. So there are two approaches. One is perform only random initialization, and the other one is to fine-tune your predictor as it is on the novel class. The approaches that worked better for us was to perform random initialization on one dataset and fine-tune the predictor on the other dataset. Then we tested two types of box classifiers for the ending part. So for this part right here, one of them was a cosine similarity classifier, and the other one a fully connected layer. All in all, the cosine similarity one worked better, although the difference between them is not very, very significant. Afterwards, we performed the evaluation on the Pascal VOC and the COCO datasets. And I'll come back to the results after we will present the second part of our approach, because we have them both together in the evaluation part. So the second part of our approach was to focus on positive sample augmentation. What does a positive sample mean? Well, if we have an annotation space like this one, where each colored circle represents one class of objects, and each sample is denoted by a different shape, then the features that best describe that class are inside these colored circles. Of course, as close as you go to the center, the easier the problem becomes, because you have very, very specific features which are good for precisely determining one class of objects. The further you go to the boundary of this circle, the harder the problem becomes. Then we have the positive samples, which are inside the circle, and the negative samples, which are outside each circle. Now, this problem becomes difficult when you have samples such as this point right here, which falls on the hard part of two classes. This can, of course, happen, and it can be classified as being part of class A or class B with almost equal probability. So these are the difficult samples which we need to focus on. Okay, so this approach builds on top of a single stage detector in order to increase speed and efficiency. And the main idea of this approach is to augment positive samples with several multi-scale variants. This is the architecture of this approach, and it goes like this. In the training part, you have here in the bottom side of the screen regular few-shot object detector. A regular object detector, in front of which we add a self-attention module. This network is a Siamese network with the one on the top. So the weights of these two networks are tied. They are being adjusted together at each optimization step. And here we have a reinforcement branch. Now, I would like to discuss about how this network progresses through training. So in the first step, we perform a normal training on the base training data set. Now, the reinforcement branch is frozen. So this part right here, the top part, is frozen in the base training step, and we only optimize the parts from below. Since these two networks are tied, of course, that this network will also be initialized when this one is being trained. Now, for the second step, we also perform a fine-tuning approach similar to the one in the first part of the presentation, where we use the reinforcement branch. And during this fine-tuning, in the reinforcement branch, for each positive sample, for example, here we have a picture of a ship on grass, and we want to extract only the positive part of this image, so only the bounding box containing the ship, and also a bit more of the contour because it might contain some useful information. We remove its background. We perform a multi-scale replication, which means that we want this crop to be at different sizes. Usually you can have the double of its size and half of its size. And then we perform random clipping from the new image. So we are presented here with a positive sample group. The reason why we are doing this and we are not showing the entire image is because usually this image can contain more than one object. And for example, on the COCO dataset, each image contains an average of 5 objects. And if we want to train only on the novel class, of course, the novel sample will be only one object from the 5 objects in the image. So if we train with the entire image, then we might introduce a lot more negative samples than positive. So, and it can hurt the training process. Okay, so we present the top network with a positive sample group of images. And we also promote weights for hard samples. So we focus on images which are hard to predict, which have a low probability, and we boost their scores with cosine similarity. We also suppress hard negative samples by fine-tuning some hyperparameters and also using the self-attention module from here. In the inference part, we drop the entire branch from the top, and we only focus on the weights that have been learned in the bottom part in the object detector. I remind you that this one had its weights tied with the Siamese network on the top. So of course, whatever one of them learns, the other one also retains for the next optimization step. Okay, so the evaluation on what we tried so far, we tested with several other backbones. So there is a plethora of such architectures. For faster RCN, for example, you can play with the backbone and test different types of ResNet. You can try SSD, sorry, not SSD. You can try any other two-stage predictors. In the one-stage predictors, you can also try with YOLO, you can try SSD, RetinaNet, and so on. So we did this, and finally we found that the best performing ones were YOLO on the positive sample augmentation and faster RCNN with ResNet and FPN on the frustratingly simple approach. Okay, we report the results on two benchmark datasets, Pascal VOC, which consists of a training set composed of the training sets from 2007 and 2012, along with the validation set from 2012, and the test set is the one from 2007. We perform a random split where we choose 15 of the 20 classes as being our base classes, and 5 of them, the rest of 5 are novel classes. So this means that we perform a 5-way K-shot learning. We repeat this splitting process 3 times and report here the map metric on several values of the K from K-shot. So each of these 5 classes will contain 1 sample, 3 samples, 5 samples, or 10 samples in each split. The first three methods here are obtained by fine-tuning an object detector on the respective approach. And the results are, of course, okay. But when we switch to the approaches that I presented before, we observe a large improvement. So we need to focus on the last two rows. The TFA is the frustrate is the a two-stage fine-tuning approach, and the FSSP is the positive sample augmentation. Okay, so here we can observe that while we add more images in the novel datasets, the positive sample augmentation improves considerably. And this happens on all splits. So on the 10 shot approach, we have here a higher improvement in the positive sample approach than in the fine-tuning one. But for a low number of samples in each split, the fine-tuning one works better. Okay, so this is on Pascal VOC. On Coco, the training set consists of 80,000 training images plus 35,000 validation images, and the test set the remaining 5,000 validation images. We have here 60 base classes as the 60 classes for the base data set, and 20 classes for the novel data set, which are exactly the same as in Pascal VOC. So this is a typical approach for benchmarking these few-shot object detectors. We report the average precision and the average precision at IOU, at intersection over union, for 10 shots and 30 shots. Here, the positive sample augmentation performs a lot worse than the fine-tuning one. So if in the first place the positive sample augmentation would improve the training over the fine-tuning one, here is exactly the opposite. Again, we are looking at the bottom two rows. These are the most important ones. Okay, so having two approaches from which work differently on the two benchmarking data sets, our work now focuses on joining these two approaches in a hybrid system. First, we are looking at applying the positive sample augmentation on top of the fine-tuning approach, and then we will do the reverse. So these two approaches are almost ready now, and we'll have the results in 1 or 2 months, I believe. Then we are also investigating some different types of positive sample augmentation. This is not the only paper that deals with such a technique, and they are very, very interesting because both papers that we tried are very simple to implement and have very good results. And as a future work, what we are also looking at is to exploit the fact that the few-shot object detections have a lot of models to work with. So as I've said, you have YOLO, you have faster RCNN, mask RCNN, you have SSD, RetinaNet, and so on. So these are very popular choices for object detectors, which can also be customized with different backbones, different future pyramids, and so on. So if we have so many models, we are looking at ensembling methods for them. There are 3 types of ensembling methods that we will be approaching, namely independent ensembling, where we have several models, and the last layer is removed and replaced by a centroid classifier. Then we perform average probabilities over all the results on these networks. There is another type of diversity ensembling, where you introduce randomization in the model training. So you drop parts of the network, you perform data augmentation, you switch the initializations, and so on. And this works very good if you have numerous models. And then you have cooperation and sampling, where you encourage the conditional probabilities to be as similar as possible by using the symmetrized callback libel divergence. Okay, so that concludes our work. If you have any questions, I am open to answering.
Many thanks, Mihai. So we have time for one fast question. Okay, I cannot see any on the chat, so I have a question. This fine-tuning step for the novel image classes, how long does it take? So it's a matter of minutes for a few new classes, or does it take longer, or?
Well, it doesn't take too long. So the base training, approach, so the base training step takes a lot longer. We
Yeah,
perform the
of
base
course,
training.
but the fine-tuning
Yeah,
step
yeah.
is the
No,
thing I'm
the fine
interested.
tuning was, I believe, in less than half an hour.
Okay, okay, so it's a matter of minutes, yeah?
Yes, yes, yes,
Yeah.
yes. Even the
Oh,
base training took us, I don't know, maybe 10 to 12 hours, something like that. But of course, it depends on the computer performance.
yeah, of course, yeah. Okay, thank you. So the next talk will be by Paolo Rota, University of Trento, about data samples are not equals, a curriculum approach for object detection across domains. So, yeah,
Hello.
it's your floor.
Let me try to share the screen. Can you see the screen?
Yes.
Yes.
Okay. So, yeah, good morning. Hello, I'm Paolo Rota. I'm here. I'm a researcher here at University of Trento, and I'm working on different topics related to computer vision and machine learning. My short talk today is entitled, as introduced, so data samples are not equals, a curriculum approach for object detection across domains, and this is the outcome of a work joined with other three people that I will introduce in the end of the talk. Real world application, artificial intelligence, machine learning and deep learning in general. In the last 10 years, they achieved astonishing results, blooming in many fields such as computer vision, mechatronics, robotics, medical data analysis, audio, and so on. Despite these results, however, real-world applications related to AI are often not as evolved as theoretical research would like to sell us. And this is due to a bunch of well-known problems. So, for example, in many applications, data is not easily available, sometimes because it regards a niche topic, sometimes due to privacy issues, and, Professor Kanhanali has shown us a lot of examples before. Sometimes data is available, but there is a lack of qualified annotators. Medical imaging, for example, is a good example. For example, if we look also to autonomous driving and robotics, we find obstacles such as people's skepticism or legislative voids that hamper the diffusion of the technology. In some problems, in some of these problems, of course, machine learning researchers can do quite a little, but not all of these problems are kind of this widespread. There are some that are can be in our control, and one of those is data bias. Indeed, it's something that we can do something, at least, if not to solve it, at least to mitigate it. So data bias is a problem that happens all the time. We try to use a specific data set to train a machine learning model, and we want to deploy such model on a different scenario. It is related to the distribution of the data in the decision space. Imagine we want to collect some data, a set of data, and we want to label, we label them, and we train a linear classifier that is reasonably good in discriminating the two classes, as you can see here. You can see here in the example a binary classification task in which a simple linear decision boundary can divide the two distribution, class 1 and class 2, having an optimal separator between the two. Now, after a certain period, we want to collect additional data on a different condition, but still sharing the same task, the same label set. We realized that this model, I mean, the model that we trained before with the previous data, is not as good as it was with the previous data. And this is due to this problem that the distribution of the data has changed. I mean, it's different in the two different data sets. So we can call this domain bias, okay? And we need to do something at least to work in the adjustment of the model, so the model boundary, or to change the decision space in order to perform well on both data. So this is an example of what is data bias in a real scenario. So here we have 5 different autonomous driving data sets. Each one has different peculiarities. For example, taken in an urban scenario, such as cityscapes and Kitty. Others have, for example, specific meteorological conditions, such as foggy cityscapes. Others are purely synthetic. Synthetic datasets are very common because they enable the possibility to train models using a huge amount of fine label data. However, they suffer a large domain gap with respect to reality. So in the work I would like to present today, we focus on a specific setting named unsupervised domain adaptation, in which we have 2 different sets of data sharing the same task and the same classes. As we mentioned before, let's say one data set will be called source. Of this, we have the data and also the label set at training time. And the second data set that is called target, where we just have the data and not the labels at training time. The goal is to learn a model that is able to perform well on both domains. So our goal is not simple classification, but we want to perform unsupervised domain adaptation on object detection. The problem has been introduced by the previous speaker, so I don't say much more about it. So our problem in the overall is, let's say, we would like to transfer the semantic information of an object detector that we have on the source dataset to a target dataset, which we don't know the labels, and of course it's a different domain, so it has the data distribution has different peculiarities. So what we want to do is to leverage a paradigm that includes self-paced learning and curriculum learning to teach the model examples starting from the easiest to the hardest. So let us begin from how we want to perform unsupervised domain adaptation on this set of data. Our idea of bridging the gap between source and target is by generating examples using generative models. In our case, we propose a method inspired by cycle GAN, which is basically a network that translates images from the style of the source to the style of the target. This enables us to train a model that has labeled images of both domains. So we can therefore learn a comprehensive model that sees both domains during the training. CycleGAN is ideal because it is able to generate images without the need of paired images across domains. For the few who don't know how CycleGAN works, it is composed by two generators. One is G and the other one is F. G generates an images of targets starting from an image of the source, and F does the opposite. The cycle is closed by forcing consistency loop between X and the transformation of X through F and G. And of course, the other way around, so the target through G and F. And the training is performed using, using adversarial losses too. The object detection model that we used is the faster RCNN that has as well been introduced by the previous speaker. Is a very powerful network that performs very well, and so we decided to pick this model. As an additional ingredient, as I mentioned, to our work is curriculum learning, which is based, which has been, let's say, proposed nearly 10 years ago by Kumar et al. And it basically very related to self-paced learning strategy. The main idea is that a subset of easy samples can be automatically selected by the classifier at each iteration. Training is then performed using only the subset, which is less prone to drifting and is progressively increased in the subsequent iteration when the classification became more mature. Self-paced learning is applied in other many studies in the last 10 years and is related to, as I said, to curriculum learning and is biologically inspired by the common human process of gradual learning, starting from simplest concepts. Curriculum is generally maneuvered by a rule. For example, an increasing monotone function, as in the picture that is taken by curriculum dropout paper of Moreira et al. Self-paced instead is the rule of adding new samples is not set a priori, but is based on training performances. It could be, for example, using prediction confidence as sampling metrics. In our idea of curriculum, we tried many different type methods, and based on empirical and theoretical assumptions. However, eventually we have found out that the most effective strategy is related to the aspect ratio of the detected objects. Indeed, we consider easy objects, easy difficulty objects, big and well-separated objects in the image. Medium difficulty objects are medium or big objects not well separated, while hard difficulty objects are small and badly separated objects. We defined a rule that considers the number of objects present in the scene and their size. So the overall architecture works like this. So it works in two phases. The first is the unsupervised domain adaptation by generation, in which we generate a large target dataset starting from the source dataset, then training a joint model between source and the generated target. The second phase, we use the train model to generate pseudo labels. But we include them in the training using a curriculum strategy, as we said in the previous slides. So the results are evaluated mainly using two metrics. The first is mean average precision, that is the usual metrics that is used to evaluate object detection. And the other one is inception score, which is used to evaluate generated images. So first of all, this is the result, just to give you an idea how the cycle-gun based method is able to generate images that are looking like the other domain. And as you can see, these results are pretty comparable. So real images with the translated images, they have a very similar inception score. Here in this table, we compare the three different sampling methods. Our very simple, with other two different methods. One is based on perceptual metrics as an outcome of a user study, and the other one is based on a domain discriminator. As you can see, not by a large margin, but still our proposed method is a little bit better, especially for the easiest and medium objects. So here is the table with the overall results. We have evaluated on 4 different tasks. Basically 4 different pair of data sets. We compared the model trained on the baseline, so basically on the source, the domain adaptation of various methods, and then of course we report the upper bound of the model supervisory trained on the target. As you can see, our results is better than the competing, but and what is not, it is still giving the best improvement comparing to the model itself trained on the source only. In the paper, you will find a lot of other tables, of course, a ablation study that will show that every single piece that we add to our stack is going to improve the results. So starting from source to domain adaptation, then self-paced, and then curriculum. So in conclusion, we presented a simple and effective method to bridge the gap between domains for object detection and using image generation. Image generation is a valuable method to bridge this domain gap, as you have seen. Self-paced curriculum training helps, and they help much more if they are used together. To improve the performance of the detector. And a simple method for discriminating easy to hard objects is the most effective in our context, especially for at least, let's say, for object detection. On the other side, also we proved that the domain adaptation for object detection is a problem still far from being solved. So there is a lot of work to do. So in conclusion, I just want to thank my colleagues. So in particular, Petru, that did all the experimental part. He did it when he was visiting here at University of Trento from University of Bucharest in 2019. So looks like ages now after COVID, and his supervisor at his own university, Radu Ionescu, and of course Nico, the head of our lab. So thank you, and I'm here for questions.
All right, so thank you for your talk. We have one question from the chat by Alberto. How much of this domain gap problem is due to a bad statistical characterization of the source data set?
This is a very good question. And it is true. I mean, it is. The different. I mean, the composition of the data sets is it's very important in order to define this this problem in itself. Of course, if you have only a very biased data set, the results of any model that is trained on this data set will be very good only if you get images that are related to the domain. So if you get an image that is sort of extemporary, it would be very hard to get good and decent results. So this is very important.
All right, thank you. So the next talk is from Symeon Papadopoulos from Aristotle University Thessaloniki. So please proceed.
Can you hear me? Can you see my screen?
Yes, everything.
Okay. Actually, I'm Ioannis Mademlis. I'm a postdoctoral research associate at the Artificial Intelligence and Information Analysis Lab of the Aristotle University of Thessaloniki. And I will present our work for work package 5 of AI4Media concerning learning for autonomous UAV cinematography. So UAVs are unmanned aerial vehicles or drones, and they have evidently revolutionized the media industry. There are many different cinematography applications where camera-equipped drones allow us to capture aerial shots that were previously impossible or extremely difficult or very costly to capture. Drones can access remote or hard-to-reach places. They can easily follow along and capture close-up views of various activities. They can perform impressive fly-throughs, flybys, flyovers relative to the desired filming targets. And of course, they're rather easy to deploy, at least much more than dollies, helicopters, or cranes. For these reasons, they have already been deployed in several cinematography applications, such as movie production, sports coverage, news coverage, etc. They are a central pillar right now of professional cinematography shooting. Due to the peculiarities of UAVs and their rapid popularization, it was necessary to define a relevant visual vocabulary, a taxonomy of UAV shot types. This has been done in the recent past with the formalization and standardization of UAV cinematography building blocks, such as framing shot types, which determine how much of the target video frame area is covered by the filming target, for example, by a person. This includes a close-up shot, a medium shot, a long shot. These are all types of framing shot types. Additionally, camera motion types were defined and subgrouped in different categories. A camera motion type, or a CMT for short, determines the relative motion between the UAV-mounted camera, and therefore the motion of the UAV itself, and the filming target, which, of course, the filming target can itself be static or moving. For example, if you are filming a cyclist or a car in a sports race or a man walking in the woods, this moving target, obviously. In the context of this taxonomy, visually pleasing combinations of framing shot types and camera motion types were also identified. Now, let me play the video. The various UAV camera motion types were geometrically modeled in a straightforward fashion, assuming, of course, that both drone and target positions in the 3D space are known at all times. This video shows an example of the orbit camera motion type, a type of filming which was in general popularized by the spread of UAVs. On the left, we see a drone orbiting around a simulated cyclist in a simulator environment. And to the right, we see the top-down plot of the movement, both of the target, the filming target, which is the cyclist, and the drone orbiting around him and filming him. In general, fully manual professional shooting is difficult because it requires precise coordination between UAV piloting and camera operation. Thus, advances in AI and robotics have been employed to facilitate autonomous UAV shooting in mainly two different ways. At least for the purposes of this presentation, we can consider that there are two ways. Low-level methods, which is autonomous UAV trajectory and camera motion planning and execution. That means algorithms which plan and implement the flight path of a UAV around the target so that the desired camera motion type is captured in the footage. And high-level methods, which is essentially autonomous UAV cinematography planning. I'll talk more about this later. In all cases, aesthetic criteria must be fulfilled in the captured footage. So this is what differentiates these methods, say, from regular aerial robotics. Methods for autonomous UAV cinematography can be grouped as either trajectory optimization methods or learning-based methods. Additionally, there are hybrid cases where learning algorithms are employed by trajectory optimization methods as building blocks for achieving specific purposes. Now, trajectory optimization methods were initially developed mostly by the computer graphics community, since the pre-existing task of virtual camera placement is very similar to the problems faced in autonomous UAV cinematography. Typically, the user specifies high-level goals, such as indicative video frames of the desired footage that is to be captured, and then a feasible trajectory computed via constrained optimization algorithms. In most cases, the scene must be static, and the 3D map of the environment, of the flight environment, must be known. Sensors such as GPS transceivers, IMUs, or motion capture devices can be used for actual target localization in the 3D world, but computer vision algorithms can also be used for this subtask, typically with lower accuracy. Thus, exploiting learning-based vision algorithms, such as convolutional neural networks for target localization on frame on the captured footage, in the context of a trajectory optimization method, is a typical hybrid approach lying between full-blown trajectory optimization and machine learning. In the most advanced trajectory optimization methods, user-defined paths are computationally adapted to avoid collisions and respect aesthetic criteria, but computed paths must be constantly recomputed in real time. You cannot just pre-compute the trajectory and be done with it when the environment is dynamic. Finally, a typical constraint present in many of these algorithms, which was not an issue in virtual cameras for computer graphics, is how to simultaneously plan trajectories for several UAVs that film a common target or an area so that each drone is outside the field of view of the other drones at all times. This more and more important since shooting using multiple camera-equipped UAVs is gaining traction as the prices go down. Now, as an alternative to traditional trajectory optimization, end-to-end machine learning has been recently exploited for autonomous UAV cinematography. In a simple example, targets can still be tracked using visual 2D tracking algorithms. The immediate future trajectory of each filming target can be predicted from the camera feed via visual heading angle estimation, if necessary. And a safe UAV trajectory that ensures the capture of visually pleasing footage can be computed on a live 3D environment map. Such maps can be constructed and updated on the fly, for example, by LiDAR sensor mounted on the drone. In principle, of course, visual SLAM from the filmed RGB footage itself could also be used to this end for dynamically constructing such a 3D environment map, since cameras are much cheaper than LiDARs, but the resulting maps are obviously not of the same quality. Now, the most important developments in learning methods for autonomous UAV cinematography have come through reinforcement learning, and this is where will I focus these presentations from now on. For example, a reinforcement learning agent for high-level cinematography planning has been presented in the literature, the agent autonomously selects the next shot type across time. In essence, the agent performs the job of the director, saying that now we want an orbit shot, next we want a chase shot. A chase shot means that the drone follows a moving target from behind and films him. The input of this agent is the local 3D map. The map of the area of the flight area must be known a priori. The current shot type, which is in essence the output of this agent from the previous time instance, and the temporal duration of the current shot type up to now. The output is essentially a parametric description of the next shot type, and training takes place in a photorealistic simulator. The reward function for the reinforcement learning method penalizes bad shooting angles. A shooting angle is considered bad if it deviates from some prior parameter, which has been manually entered. It also penalizes small target image size on frame. Therefore, the target, for example, the person we are filming, must cover a significant portion of the captured footage. And the long duration of each selected shot type. It is considered good to have visual variety and therefore a reasonably frequent change in the current shot type. Reinforcement learning has also been used for low-level autonomous UAV control in cinematography settings. Here the goal is to map visual inputs to desired actions so that the desired shot is captured without knowing the actual filming target position in the 3D world, ideally at least. Aesthetic criteria are typically captured by the reward function. In the simple scenario of frontal face shooting, we want the drone to move so that its camera captures a person from the front. The state, the state in the terminology of reinforcement learning, is the current image of the head, while the discrete actions that the agent outputs are equivalent to camera panning and tilting. The reward essentially penalizes any deviation from the desired frontal shooting angle. And in the simplest case, training can be performed on a labeled dataset of multi-view head images. For example, there is a work that did this without having a simulator, as is typically in deep reinforcement learning. The same method has been extended to a continuous action space for continuous UAV control methods. In this case, face alignment and warping algorithms were employed to synthesize new intermediate head poses, but training still takes place using a dataset of discrete multi-view head images. Finally, the discrete variant of this method has been adapted to use with an actual photorealistic UAV simulator for the training and evaluation processes. In this case, the state is the current RGB image, what the drone sees. The action is the next UAV velocity vector. And during training, the reward function rewards a particular drone to target 3D distance and a zero difference between the camera axis and the face orientation, so that frontal shooting can indeed be achieved. Instead of reinforcement learning, imitation learning methods have also been applied to autonomous UAV cinematography. I'll give here an example where a neural agent can be pre-trained on real professional videos in a supervised manner so as to predict the next state based on the actual history of the last K states and on the desired final state. Each state in this algorithm is the set of computer vision estimated 3D and 2D coordinates of the target relatively to the UAV, with 2D coordinates being, of course, on-frame pixel coordinates. Finally, the next UAV and therefore camera pose is geometrically estimated based on the predicted state. However, most of these learning methods for autonomous UAV cinematography, which have been presented up to now in the literature, support only a limited aesthetic palette of camera motion types, while imitation learning methods typically have the additional disadvantage of requiring extremely large amounts of training data. In the context of AI4Media, we're currently developing a neural reinforcement learning agent for UAV control that is able to perform 10 complex camera motion types from the taxonomy I mentioned at the beginning of this presentation. It is currently being trained in a simulated photorealistic environment, which is the AirSim simulator based on the Unreal Engine 4. Here we see an image of the training environment, which is a cyclist in a countryside map. In our method, the state is the RGB image taken from the UAV camera at the current time instance, and the relative angle between the 3D UAV velocity vector and the 3D camera axis. The possible actions that the agent can output in our method are a change in the instant pitch and yaw rotation angles of the UAV velocity vector, a similar change in the camera pitch rotation angle, and a small change in the linear UAV speed. Basically, the drone can turn a bit right, a bit left, a bit upwards, a bit downwards, or slightly accelerate or decelerate at its time instance. As soon as the set of actions has been selected for the current time instance, we transform it into UAV velocity vector and camera axis changes using simple geometry. These new vectors are fed as commands to the flight controller, for example, a Pixhawk UAV autopilot, which of course in our case is simulated by the AirSim environment, but it could be actual hardware instead. Thus the current actions are executed, and the next video frame is captured from the simulator, meaning the next state is observed. During training, we penalize distance between the ideal UAV 3D position and the ideal 3D axis, camera axis vector, as estimated by the desired camera motion type geometric model equation, which I gave an example of such an equation at the beginning of this presentation. And this is computed, this penalty, or in fact, the reward, is computed across the entire training episode. Of course, the equation used for computing the reward requires the 3D position of the filming target to be known, but it is indeed known by the simulator during training. After training has been completed, the final neural agent will not require this information. The input state during the inference stage simply will be the currently captured RGB image and the relative angle between the UAV velocity vector and the UAV camera axis. Therefore, 3D information about the target, the filming target at each time, is only required by the simulator, not by the agent itself. We employ an enhanced variant of the state-of-the-art TD3 reinforcement learning agent for continuous control. It's an actor-critic method, typically used for such tasks. And we use a CNN backbone for feature extraction and an LSTM for the main agent. Up to now, we have trained the proposed agent on a simple reinforcement learning benchmark environment. In this plot, you can see that in this simple task, which is the richer task on the OpenAI gym environment, our agent exceeds the baseline in rewards over training episodes. The next step is to integrate this agent with the AirSim-based UAV simulator, which I previously described, so that we can actually train this agent for autonomous UAV camera motion type execution. This is still work in progress. Moreover, we intend to use this environment and the experimental setup as a platform for innovating in reinforcement learning methodology itself. We intend to do this during the second year of AI4Media. I have the reference here. I guess the presentations are to become publicly available, so anyone can check them out. And that's all from my side. Thank you for your attention.
All right, thank you. So there's time for one question. Okay, nothing from the chat. So I have a question. You mentioned at the beginning of the presentation so the diverse shot types used in URV. So are these the same as in classical cinematography, like static shot, close-up shot, medium shot, pan shot, and so on? Or are these specific to UAV filmography?
There are some peculiarities in the UV cinematography case. That's why a novel taxonomy was presented. That was before AI4Media.
Okay, so there's a different extended maybe taxonomy.
Yes, there's a different taxonomy from
Okay,
standard
yes.
cinematography.
All right, thank you. So we will proceed with the last presentation from Francesco Marchetti et al., University of Firenze.
Okay,
so yeah, please.
I'm Lorenzo, so I'm going to give the talk.
Okay,
Can you see the slides?
Yes,
Yeah?
yes.
Okay, so I'm going to talk about predicting multiple trajectories, exploiting memory-based neural networks. This is something that can be used in the context of AI4Media, and we will see a few examples at the end of the presentation, for social behavior analysis and gaze prediction. Okay, so the motivation for learning how to predict a trajectory are many. So the most natural one is the application to automotive, where, of course, you are interested in understanding a complex scene where each agent can behave in many ways and can perform different actions. So you, as an autonomous driving agent, you need to know all the possible tracks that another agent can take. But more close to our project, this can, of course, be of interest for fully automated cinematography. And this is a nice link with the previous talk, where, of course, for planning trajectories of the drone, it is extremely relevant to predict and forecast trajectory of filmed targets. And finally, this is the application we are working on at the moment. We are interested in understanding where a user is going to look for a 360 video stream. This is very relevant since these video streams are extremely heavy on the network, and you are interested in adapting the video stream based on where it is more likely that the user is going to look at. So the problem definition is, this maybe is trivial, but I'd like to be clear at the beginning of the talk. So the idea of trajectory forecasting or prediction is you observe a certain amount of locations in the past for an object in some state space. For example, in a top view state space, you would have R2. And you also have some contextual information that can be a map or the position of other agents. And you would like to predict a certain amount of future steps of that agent. And for each agent, you would like to have multiple hypotheses. Okay. So if you extend this problem to social trajectory prediction, in this case, you have a set of agents. And of course, you observe a certain amount of time steps and locations in the past for each agent. And in this case, you jointly predict multiple hypotheses for each of the agents in the scene. Okay. So a nice example would be this one, where you would like to know where this cyclist is going. And of course, multiple futures are possible. He may go straight or may turn left. And of course, it is important to take into account the diversity of these futures. So not to predict a lot of identical future trajectories. Currently, the state of the art is based mainly on a recurrent network for the prediction of future timestamps. And the multimodality is often obtained using variational autoencoders or any kind of generative model that is able to sample multiple instances from a distribution. In general, the social prediction is performed by modules that are pooling features from different agents into a single descriptor. And finally, there are some approaches where instead of generating all time steps one by one, they are generating goals, meaning that you know the end point of the trajectory. And then with this goal and the map, you can generate the whole trajectory, conditioning the generation on the goal. Our approach is fairly different from all of these approaches, and the trade-off in a good multiple trajectory prediction model is to get enough variety in the trajectories, meaning that if you keep generating novel trajectories, you would like them to be all different, but also to be consistent with the past observation and with the context. But you don't want to lose accuracy, meaning that if you have one of the trajectories which is close to the actual trajectory that then is going to be performed by the agent, you would like to have a very low error in that case. Okay, so we propose a completely novel model with respect to the existing one, which is based on the use of a memory, okay? So here is an overview of the framework where you can see on the left, you see this is the input, a past trajectory and a top view semantic map. This semantic map, of course, can be obtained by integrating LiDAR and semantic segmentation plus some ego motion tracking. Okay, so this is a very multimedia kind of problem. Okay, but in the end, you work on very simple and terse data, which are 2D trajectories in this case. So the main idea is that the past and the context are encoded and they are used to decode a future trajectory. The decoding happens on the right here. You see here the decoding step, where we are recombining past and the context descriptors with some observed futures. So let's take a look into detail on how the inference is performed. So at inference time, the reading controller is a network component that is able to find the top K futures into the memory, okay? So to be clear, this memory is not an episodic memory, meaning that it is filled and emptied at each episode. This memory is memorizing samples from the training set. And we exploit these samples to get the multimodality at the inference time. So the reading controller is getting these top K examples from future. So here in the memory, the key is a combination of past and context embeddings, pi and gamma. And you get this phi here as this result from the query into the memory, in memory. And then what happens is that you keep the past and context equal for all the decoding that you have to do, but you combine them with the various futures embedding that you get from the memory. Then you have a decoder which is able to reconstruct each of these trajectories, okay? And this is the way we obtain the multimodality, okay? So you see that the model is very flexible because you don't need multiple heads in the network to perform multimodal prediction. You just have to change the amount of Ks that are retrieved from the memory. And this is very advantageous because you don't need to retrain the model when the K in your scenario has to be increased or decreased. Okay, so how do we train this model? So the training is has several steps. So the first step we perform is we learn some representation. We train a sort of an autoencoder where the vector is encoded from past, context, and the future we observe at training time. And then we only decode the context and the future. So we attempt to reconstruct the future trajectory by looking at the past, context, and the future. Of course, the trajectories are encoded with the recurrent units, and the context is encoded with a simple convolutional neural networks. The pixels here are semantic labels. So in this case, we have multiple labels. In other dataset, you may just have road and not road. But in general, this is a flexible approach where this map can be substituted with anything, like a saliency map of a video, for example. Okay, so this is how we learn how to represent the embeddings pi, gamma, and phi. But one important part is how do we train the writing controller? So a memory is composed of a storage, a writing controller, and a reading controller. So the reading controller is fairly simple. It's based on a cosine distance. So we only learn the ways to combine the past and the context memory. I'm skipping these details here. But for writing into memory, this is more complex because we need not to saturate the memory, not to memorize all the dataset, but also get very good reconstructions out of the embeddings that we store, okay? So in the end, the memory, when you finish the training in our experiments, it's only retaining like 3 or 4% of the original dataset. So our approach is kind of good to at compressing the training data. So the writing controller is training in a very simple manner with this simple idea. So the idea is if you have a, let's say you have some training at some training point in your training process, you have a memory and you have the encoder and decoder which are trained. So you get a new example that you've never seen, and you try to predict the future for that example by reading examples from the memory. So in case the prediction error is high, of course, this example, which is a training example because you are at training time, it is worth writing, okay? In case the error is low, of course, you do not need to store this example in memory. So to implement this behavior, what we do is we define a loss that takes into account this adaptive miss rate error, which is kind of an accuracy of our trajectory based on this idea here that for different time steps, we evaluate as correct an object that falls into a ball of a certain size, and we evaluate that as an error if it's outside, okay? So this is an accuracy function that can be used to formulate this loss here. And what we are trying to optimize here is the weights that are generating the right probability P, okay? So for a given embedding, the right probability is fed with the reconstruction error, which is E, okay? So which is computed this way. And you know if you have to write or not the vector in memory, depending on the output of this probability. So in case you have a low error, you are the loss corresponds to the probability, so you are minimizing the probability of writing into memory. The other way around, if you have a high error, you are trying to maximize the writing probability. So the small component, the writing controller, learns to behave like this, okay? And we have seen that more trivial solutions, like just using the error as a sort of probability, right? They are less good at generalizing to new datasets. Okay, so once we have done with this training, so we have learned the encoder and the decoder, and then we have learned how to write in memory, then we empty the memory, and then we fill it by swiping the whole training set. And now, at that point, our method is ready to predict novel trajectories, okay? So regarding results, let's introduce the setup. So here, what we see is a past observed trajectories, which is the X. And then from the present on until the future, you are predicting all time steps here, you see? And the settings are standardized, and usually you go up to 4 seconds in the future, and you compute two metrics, which are the average displacement error, which is computing all the errors at all time steps and averaging. And you also evaluate the final displacement error, which is only looking at the last time step. Okay, so at the last time step, you compute the mean square error between the predicted point and the ground truth trajectory. Of course, when you predict multiple trajectories in the experimental setup, requires to get only one prediction, and you usually pick the best one. So this is the standard scenario that every other work in the literature uses. Okay, so here you see our results are kind of state of the art. You get an improvement over as soon as you get to top 5, you start getting kind of state-of-the-art results. Interestingly, if you go up to 20 predictions per trajectory, our method keep reducing the error. These are meters. So our approach is able to predict future locations of objects. Here, this is a driving dataset, Kitty, where at 4 seconds in the future, you get 1.6 meters of error. And here we also report result on Argoverse, which is a much larger dataset. And in this case, we actually also got an honorable mention from the challenge organizers. So these are results in a different setting. So the authors from Infer, they split the data differently. So we also compare with them. And again, here you see that as soon as we get to predicting multiple trajectories, our approach is much, much better than Infer and other approaches. Interestingly, we also ran these very simple baselines like a Kalman filter, a linear predictor, and a multiple layer perceptron, which are kind of good baselines. So it's also very important to try very simple baselines before you try very complex approaches. But of course, these are unimodal, so you can only compare these numbers with unimodal predictions. And of course, when you get a little bit of complexity into the model, you also get better results. You see, Infer, for example, is better at unimodal predictions with respect to the baselines. Okay, so an interesting experiment we did that is to try to transfer the trajectories we are able to learn from Kitty or Argoverse, for example. In this case, we trained it on Kitty, and we transferred on Oxford Robot Car and Cityscapes, which are two other datasets of autonomous driving. You see that our approach is clearly superior to existing approaches like Infer or a convolutional STM, which is another baseline. Okay, so I would like to conclude with a few ideas for future works. So the approach we presented in this talk is a novel usage of memory-augmented neural networks applied to trajectory prediction. So memory-augmented neural networks are often used in an episodic manner in natural language processing tasks. So here we exploited the fact that we can store relevant examples in memory to obtain the multimodality. We have shown that our approach is superior in terms of zero-shot transfer capabilities, so it's better at generalizing. And interestingly, in the context of AI4Media, we started also with a physical and remote visiting with Quentin Guimard and Professor Lucille Sassatelli from University of Côte d'Azur. We started to work on the problem of predicting gaze in 360 video streams. So the idea is having multiple trajectories can benefit the adaptation of the video. So we are working on that, and we expect results in the next 3-4 months. If you're interested in this work, please have a look at the papers that we have here. And also, we also released the code for the CVPR version. I would say that the PAMI version is probably on the way, but the CVPR version is kind of complete. The model is also pre-training, but you also have all the code to retrain it on your own trajectory data. So here are an example of our cyclist. You can see in blue the observed past, and in red you see the multiple future trajectories. On the top left, except for this, problem here. Okay, so you see the map and the multiple trajectories that you can see are all reasonables, and they all take into account the map. So thank you for your attention, and of course, if you have any questions, please feel free to ask.
So many thanks, Lorenzo. Any questions from anyone? So don't see so far, but maybe someone. All right, so then I have one question.
Yes.
Would it make sense to combine this approach with some more, let's say, high-level information, like from an object detector, so that you would know where are the persons, where are the cars, and so on? When I'm correct, then it's not using that kind of semantic information, right?
Yeah, so this is very relevant, especially when you look at pedestrian reach traffic. So here I have shown results on driving datasets where the behavior of agents is mostly defined by their past trajectory, and the context is also relevant, but in our experience is not that relevant. Other agents are really relevant, especially when you deal with pedestrians. We are working on that. And of course, all the data you get to go to the top view is extracted automatically with object detectors. The thing that you are correctly saying is that we are not looking at other agents, but currently we are working on an approach where the agents are kind of sharing the memory, so we can perform a joint prediction similar to social LSTM, for example. So this is of course important. Yeah, I would say for especially when you have, for example, if you would like to pilot a drone with this kind of technology, you need to take into account multiple targets, and the prediction must be performed jointly and not individually. So yes, this is a very nice question.
All right, so many thanks to all the presenters of this session. So we are over time, so we have to shift the discussion to the very end of the day, and we'll hand over, proceed immediately with the next session.
Yeah, so yeah, I agree.
Yes,
I would like to stop sharing. Stop sharing.
Because it's 11:40, so yeah, if we want to stay in time.
Unless there are some other questions or discussion, maybe we can just go to the next session. So that would be Ioannis chairing the session.
Yes, hello. This is Ioannis. So the next session has two presentations. The first one is from Dr. Jakob Abesser, if I'm pronouncing it correctly, from the Fraunhofer Institute for Digital Media Technology in Germany. And he's going to talk to us about disentanglement representational learning for music annotation and music similarity. Dr. Abesser?
Yes, I hope you can hear me. See my screen?
Yes, we can hear you.
Yeah, perfect. Okay, thank you very much for the introduction. My name is Jakob Abesser. I'm a senior scientist at Fraunhofer Institute for Digital Media Technology. And today I want to present joint research work with my two colleagues, Sebastian Ribecki and Hanna Lukasiewicz. And the topic of our research is disentangled representation learning for music similarity. So I want to start with a short motivation of our research, then give some details about the applied deep neural network architecture, which are the conditional similarity networks. I will talk about sampling strategies and the dataset that we use in our research, and detail our extensions that we propose to the state of the art. And finally, I will close with the evaluation experiments and the results that we obtained. So we've been working on music information retrieval for many years. And the main fact why music is a very interesting and challenging subject is that it is inherently multidimensional. So what that means is, if we look on the right side, if we are asked as humans what we consider as similar music pieces, we might focus on different aspects of music. So for instance, we could compare two pieces of music just based on the musical instruments which are used. So this would relate more to timbre similarity. And we could at the same time also take into account the mood that the piece of music invokes at the listener. So we would consider two happy music pieces to be more similar than, let's say, a happy piece and a sad piece. And in the traditional approach in music information retrieval, we focused a lot on extracting such parameters like music instrument recognition or mood estimation, and then try to apply some kind of similarity measure based on these attributes. And the common way to do this, or the common application scenario, is that we have an example and we want to query with this example from a given data set to find the most similar items in this data set. Now, if we look at different tasks, we can see that the similarity, or the notion of similarity, is kind of different with respect to its specificity. So that means we can see on the left side, we consider a music fingerprinting scenario where for a given query song, we want to find all the files in a data set which include, for instance, an exact version of this, or which include segments of this query file. So this is like an exact similarity. And on the right side, we can see that if we just want to get as results songs maybe with the same music genre or the same music style, this is maybe a more vague idea of similarity. So in our work, we are focusing on metric learning, which was already mentioned in several of the previous talks. So the main idea is to map our data instances into some embedding space or some metric space, where ideally data instances or examples which are more similar, they end up more close to each other, and dissimilar instances end up further apart. Of course, these days we're focusing on deep metric learning. So that means we use a deep neural network to be able to map the data instances into an embedding representation, which then basically defines the embedding space. So in our work, we're using an approach which originally was proposed in the image processing domain, which is called conditional similarity networks. And we can see on the right-hand side a schematic view of this network. So it implements the triplet learning strategy. So that means we have an anchor, we have a positive and a negative example, and ideally we want to train the network in such a way that in the embedding space, the anchor and the positive example are closer to each other than the anchor and the negative example. So that means we want to train the network such that the embedding kind of reflects our notion of similarity. So we can see that each input file is mapped to an embedding using what we call a core network or backbone network. And the special aspect of the CSN networks is that the embedding representation is then multiplied with a binary mask. And these the masked embeddings, they then span the embedding space. And now I mentioned before that we want to focus on different aspects of music similarity. In the related work, which is kind of the foundation of our research here, the authors distinguished between 4 different aspects, which are the instrumentation, the mood, the tempo, and the genre of a piece of music. And now the main idea is that during training, we can use different notions of similarity. So that means we can, for instance, in one batch, use the similarity with respect to genre. And we want to make sure that, let's say for the example shown here is blue. So that means by using a masking, so that means we only consider, let's say, the first or the right part of the embedding. We can make sure that these semantic aspects, they are basically represented by different parts of the embedding vector. This is a nice way to kind of to make the embedding vector also more or better interpretable, which is a very important thing. So as the backbone network, we use a variant of the inception network. So without going into too many details, we can see that the network consists of 6 of these inception blocks. And each inception block basically contains a naive and a dimension reduction module, which I will briefly explain on the next page. And we can see that this network architecture is quite efficient because it avoids an excessive computational cost while increasing the number of neurons per stage. So here are the 2 components of these layers. So we can see that the naive module basically implements convolutions with different kernel shapes, and then again concatenates the filters. And afterwards, the dimension reduction module uses the 1x1 convolutions to again reduce the number of filters of channels. So for the triplet learning, one important aspect is the way how these triplets are sampled from the data set. And we use the semi-hard negative mining approach for this. So that means the triplets are sampled online during the training. And here, as an example, we can see that given an anchor, a positive example, we can see that on negatives, which would be selected, which are within this red region, they would be considered as hard negatives, because in the end, we want to train the network in such a way that the negative is actually further apart from the anchor than the positive. And on the other hand, all the negatives sampled from the green region would be considered as easy negatives because they are kind of already well represented. So they are further apart from the anchor. So the interesting region is this orange region, which provides us what are called semi-hard negatives. And if we look into the triplet loss formulation, so this is the loss function which is used during training, we can see that this margin is kind of one hyperparameter which needs to be chosen here. So the data set that we use in our experiments is called the DIM-SIM dataset. It includes triplet annotations from 3-second-long excerpts from music samples. So these music samples were selected from the Million Song dataset, which is a popular dataset in music information retrieval. And these triplet annotations were done by humans, usually from between 5 to 12 different annotators. And they basically contain the information given an anchor, which of 2 further examples are considered to be a positive. So which one is considered to be more similar compared to another one, right? And after some cleanup of the annotations, we end up with around 880 high agreement triplets. So here the agreement between the annotators was above 90%. So in the original paper, which is kind of our baseline system, the authors used a MEL spectrogram, which is a time frequency representation of audio as input to the network. And we propose in our research to extend the network in such a way that we have, instead of 1, 3 input branches. And also we want to incorporate 2 additional musical dimensions, which are the tempo and key. So the key represents kind of which pitches or pitch classes fit well to a piece of music. And we know that these two aspects are not well captured in the mass spectrogram itself. So we decided to extend the network to have multiple input branches in such a way that it also processes two additional feature representations. So the tempogram is a kind of a temporal likelihood of different tempo values. So we can consider it to be like a saliency measure for a tempo candidate at a certain point in time. And the sense chroma features, this is a 12-dimensional feature which measures the likelihood of a certain pitch class. So if you think of like a pitch class like C, C sharp, and these chroma features are commonly used for key detection. So we have 3 input branches, and the results are concatenated within the network in an early fusion manner. So on this slide, I would like to summarize the main results of our evaluation experiments. We can see on the table on the right side the results from the baseline experiment. So this was kind of the starting point of our research. So we were able to re-implement the baseline and also reproduce the results that the authors achieved. So here we have 4 musical dimensions. This is a single input model, and we have an embedding size of 256. The triplet score basically is like an accuracy measure. So from the test set, it counts the percentage of triplets where the positive example was correctly identified. We also used as a baseline a simple model based on the OpenL3 embeddings, which are very popular embeddings for pre-trained embeddings for audio. They were trained in a self-supervised scenario with an audiovisual correspondence task. So these are our 2 baselines. And now here are the results of the proposed model. So for the multi-input scenario, we can see that using the 6 musical dimensions instead of 4 gave us a boost in the triplet score. We can also see that using the multiple input strategy itself was also beneficial. These findings are also summarized in the plot below. So we can see that the circles, so the red one is basically the baseline system of the OpenL3 embeddings. So we can see that the x-axis represents the embedding size, and the y-axis represents the triplet score. And we can see that the multiple input settings outperform the single input models. Also that the having more musical dimensions is kind of supporting the, or is beneficial to modeling the concept of musical similarity. And on the final slide, I would like to show that we also investigated, based on the highest performing model, which of the musical dimensions mostly influence the overall quality of music similarity. And here we found that genre, mood, and era, and I have to mention that era kind of captures the decade where a certain music recording was done. So this is highly correlated to the music genre, of course. And they provide kind of the highest contribution to the similarity modeling. So this also is well reflected in the fact that most in the literature, usually genre recognition is often used as a proxy task for music similarity. Okay, so thank you for your attention. Some references. So I'm happy to answer any questions.
Okay, thank you, Dr. Abeser. Do we have any question on this work? Oh, there is nothing in the chat. Can I just ask you whether do you plan to extend this from the metric learning aspect, research-wise, or this is finished work?
Well, we have discussed more in terms of maybe thinking about other musical dimensions. So maybe one part of our research, which was maybe not highlighted that much in this work, was that in the DimSim dataset, I mentioned that we were relying on human annotations of music similarity. And I think one interesting aspect could be that in order to add basically the two dimensions tempo and key, we didn't have any human annotations for that. So instead of what we did was we used state-of-the-art feature extractors, which was the Matmon Python library in that case. And with this, we basically generated ground truth triplet annotations based on some musical rules. But maybe as a downside of this method, since the automatic feature extractors are not working perfectly, I mean, they achieve, let's say, an accuracy of an F-score of 0.8, there's probably some kind of error propagation from this extraction step to the triplet scores. And I think that would be interesting to investigate. Influence could be.
So how to handle the noise in the labels?
Exactly, label noise. Yeah.
Okay, thanks a lot. Now we can move on, I guess, to the next presentation. Next, Rémi Mignon and Lenny Renaud are going to talk to us about differentiable piano sound synthesis with a DNN controller. They're from the Institute for Research and Coordination in Acoustic Music, or IRCAM, in France. So, Lenny, you're going to present?
Yes,
Okay.
coming. Just take some time to share my screen. Oh.
We can't see your screen, Steve.
We cannot hear you either.
Sorry for
Is
this
there
delay. I had a small problem configuring the slides. Okay. Can you see my presentation now?
Yes.
Yes. Thank you. Thank you very much. So hello everyone, and welcome to this presentation of what was being introduced of the work that's been done on differentiable piano sound synthesis with the deep neural network controller. I'm Lenny Renaud. I'm a PhD student at IRCAM under the supervision of Rémi Mignot and Axel Rebel. And let's jump right into it. So the main project that is proposed by our team for the AI4Media project is the generation of realistic audio musical performances. We are given a music piece which is written in the symbolic domain, and we try to get the audio as if a musician actually played the music piece and someone recorded the performance. We really want to put an emphasis on the fact that this is not automatic music composition, which is a common task in the field, but we really want to actually render an audio performances from a composition that's already been made by a human or a computer. So. And there are two kinds of realism that we want to model. We want to capture the realism of the performance, how the musician control its instrument to inject interpretation on top of the music sheet. And there's also the realism of the instrument sound that we want to model, how close our model can sound like an instrument being actually played and recorded. And the main applications we are aiming for are artistics. For example, we can have composers and producers to have a preview of their composition without having to immediately hire an instrumentist. But also such a system can also generate annotated datasets of realistic music pieces, which could be used for training other music information retrieval models for tasks such as instrument recognition, transcription, bit detection, or tempo estimation, so on and so forth. These annotations are most commonly encoded in the MIDI format, which is also mainly used by the composers and producers. In that case, we try to make our models compatible with this format. Up until now, we've been working solely on instrument sound synthesis. So the second step when we have sufficient performance data and we want to render the audio from the performance. Which can be understood as how an instrument sounds when it's being played. In order to design this model, we have put different constraints. So, like I've said before, try to be compatible with MIDI. And this model has to be fully differentiable in order for later on putting a performance modeler before it and to have a full pipeline for end-to-end performance synthesis. And the main criterion for evaluation is the realism of the synthesis, as we try to get as many details that the human hearing is sensitive to. And for now, we'll try to focus on the piano, which there's a significant amount of aligned data, MIDI to audio and paired. First, I'm going to present you a quick overview of techniques used for instrument sound synthesis. First category are the samplers, where we simply play back recordings of an instrument on nut triggers. Show you an example of a hardware sampler and a software sampler, which is the main method used in the softwares and in the industry. They sound realistic since they actually play records of actual instruments, but the ear can notice when the same samples are used all the time, which can be detrimental to the realism in some cases. And also it needs a lot of memory space in order to store all these samples, which can lead up to several gigabytes of data. Other categories of synthesis methods are the signal-based ones, where we analyze the samples of instrument we want to model in order to find the synthesizer parameters, and these synthesizers will produce the sound. There are several categories of synthesizers and techniques we use, such as additive synthesis, subtractive, amplitude and frequency modulation. And main advantage of these techniques are the fact that we can control and we have an explicit control over the sound generation process. But it requires complex and detailed controls in order for these methods to actually sound realistic. Same goes for physical-based synthesis methods, where here we simulate the actual physical phenomena that occurs when the instrument is being played. Which requires a very deep understanding of the instrument to be modeled correctly. But when it's well done, it usually sounds realistic. But these methods can also be computationally heavy and hardly transposable to other instruments once you have modeled one. But with recent progress made in the data-driven generative models, there have been several propositions for instrument synthesis using deep learning, mainly taking inspiration from the speech generation methods, but applying them with MIDI conditioning. So, for example, you have in the time domain the wave minute, which has been conditioned on the MIDI input. Also, maybe in a more traditional manner, having acoustic model that would transform the MIDI into a spectrogram, and then having vocoder that transform the spectrogram back into a waveform. The data-driven methods recaptures the realism of the sound, but they are very data hungry, and you know, the data to feed into for the learning process. And we actually have very little control over the synthesis process other than the conditioning itself. Up until recently, when for now more than a year and a half, the Google Magenta team released a framework called Differentiable Digital Signal Processing, where they've implemented differentiable synthesizers, which can be controlled by neural networks. This combines the interpretability of signal-based synthesis, as we have explicit synthesizers, but we can control them, and to such we have the expressivity and the modularity of deep neural networks. In the case, this modularity of the system can help to design and incorporate high-level acoustic modeling knowledge into a deep neural framework. So for our case, when we want to model piano, I'm going to present you a very crash course on its acoustic and mechanics, and have those in mind in order to implement an architecture. The piano sounds come from strings, which are being struck by hammers. The strings then vibrate accordingly to the wave propagation equation, which is the same as for guitar, harp, or any other strings instrument. But the piano strings are known to be stiff, which introduce inharmonicity between the string modes, which is particular to the piano sound. Also, most piano notes have double or triple strings in order to have homogeneous loudness across the keyboard, but the strings in the same duet or triplet may not have the exact same frequency, which introduces partial beating and a phenomenon called amplitude double decay. Also, there are other elements in the piano that generate noise, which is not related to the string if not itself. For example, when we press down the key, this produces sound. The krill then launches the hammer, which will strike the string, and the damper is being released. But when the note is finished, the damper muffles and absorb the vibration of the string. And also, when the pedals are being used, they also produce back some noises. And also they have an overall context that can change the sounds of individual notes. So, for example, when several notes are played simultaneously, they influence each other's with what we call sympathetic resonance. The pedals also changes the acoustic properties of the instrument by, for example, releasing all the dampers at the same times. And of course, the piano model and the piano brand can influence the overall sound, and that's why we have high-end pianos or cheaper ones. So now that we are aware of all these different elements and we are having a rough idea of how they can influence the sound, we've designed a model architecture that can try to learn those connections. So here it is. So where we go part by part and explaining the functioning. We have in the input what the pianist can control on the instruments, which are what the notes are being played, what pedals it can press, and of course which piano the pianist has chosen, he or she has chosen to play on. And like in the original DDSP paper, the sound is produced by summing an additive synthesizers, which adds many sinusoids, and a subtractive synthesizers, which filter white noise. The overall is filtered by an impulse response, which is modeling the reverb and the acoustic environment. And all these three modules of differentiable synthesizers are controlled by a recurrent neural network, which will parameterize the synthesis. And during training, the model is optimized with regard to the difference of the target and generated signals in the time frequency domain. We can look in particular at the additive synthesizers, which simulates all the phenomena in the string vibration. So for each note played, there's a monophonic network that will output the overall and relative amplitude of the note harmonics. We've also included an inharmony network, which includes from a simple model from Rigaud in 2011. In order to displace the harmonics, in order to take the harmonicity into account. We also provide information on not release for letting know the model when to stop the sound producing and to generate the effect when the string is muffled by the damper. And finally, there's also a variable which is compute a detuning factor between two strings of a duet in order to recreate the partial beatings. As for the subtractive synthesizers, this one models all the noisy elements. So we want to provide as many information on when the different noisy elements are triggered. We pass the onset, so the start of each note, in order to signal that the model should produce all the keystroke, hammer, and damper release noises. And also when the active notes are finished, it knows when to action the effect of the damper being pressed and being absorbing the strings. And also with providing the signals of the pedals when they're being action and when they're being released, so that it can also re-triggers the same noises. Same goes for the global conditioning, where we provide different elements which will influence the overall sound of the piano. We pass down a context vector, which is computed from the notes being played at the same times, the pedals being pressed down, and the piano type embedding. And this context vector is passed down to the controller for the monophonic network and also the tuner and harmony network in order to modify the synthesizer's controls accordingly. And this context network also output the overall reverb. We've trained the pipeline for now on isolated notes and chords from the maps dataset. And then here I have an inference test on the sample that was unseen during training and validation. So the target sound which the model should aim for, but has not seen during training, is this one. Did you hear that? Or... And the one which was produced by the synthesizer is this one.
No, the audio cannot be heard.
Can be heard. Oh.
No, I think you have to change the input of your. You have to go to the mic and change the source of your microphone.
To
it may not be
from the. Now if we get to rewrote. That's a shame. Yeah, something will be possible for today. Sorry for that. Well, I can still make some commentary on the spectrograms at least. What's good about the resynthesis is that the harmonics are well placed in frequency and have a realistic and decay. And also it reproduces some amount of modulation, even if it's not of the same frequency as the original. Also, you can notice here that this pedal lift noise was not reproduced by the model, but I think there was other version of the model which can reproduce it, but not in this one. Also. So yes, promising results, and we have to conduct some listening tests to assess and to see if other people actually feel there's a huge difference or not between those two, and also against the baselines. In order to what's left to be done for this work in particular, we're currently scaling up to the larger Maestro dataset, which was used for training the baselines. And then once we've been retrained on this dataset, we have to conduct several listening tests in order to assess the audio quality and to compare them against the different methods that was presented right before. And if everything, the results are good, we can submit this work into a conference. And in the next projects in the continuity, we have once we have this differentiable and realistic sounding piano synthesizer, we can use it as a generator for transforming the written pieces into performances directly from the audio data. We can also expand the work with other instruments, and since the MIDI cannot encode all the controls an instrumentist may have on instruments, we may have to use, for example, GANs to model what's little MIDI cannot model. And then when we have all these different instruments model, we can use to generate musics of synthetic performances from the Simulink data directly and to train models on other MRI tasks. So thank you for your attention, and I'm ready to take any questions.
Okay, thank you, Lenny. Do we have any questions? Does anyone have any question about Irkam's work? I don't see any question in the chat. Can I ask you one thing, Lenny? I'm not familiar with the differentiable DSP, so does it have parameters of its own that are adjusted by gradient descent during training, or it's just used to process what the network gives it? And then,
I think the gradient can pass through the differentiable synthesizer, so that's why it's possible to train directly with regard to the outputs with the audio outputs. So since the synthesizers are differentiable, the network controlling them can be learned with gradient descent.
So it's just a conduit for propagating the gradient signal. It's not parameterizable itself. Okay.
Yeah, they don't have any learnable weights. They're only just modules that are being controlled, but they can pass the gradients during training.
Okay, thanks a lot.
Okay, welcome back everyone to the afternoon session of the AI4Media WP5 workshop. Alberto Messina from RAI, Italian public broadcaster, research and development department. I will chair this session until 16 o'clock for the discussion. Let's start with the keynote from Professor Alan Smeaton, Dublin City University, a speech that, yet from the title, seems very, very interesting. Multimedia analysis and multimedia retrieval. Is there a mismatch? So Alan, are you online?
I am indeed, yes. I'm just juggling with the sharing again. I'm assuming that, or hoping that you can see my screen. I know it's not on full screen, full PowerPoint presentation mode, because I have I got the PowerPoint and then I got my notes on one side, and I'm in the office I don't have two screens, I only have the one. So if I was to show it on presentation, you'd only see the side of my head for the entire presentation. But anyway, so thank you for inviting me for this to give this presentation. I decided not to give a talk on the work we're doing in computing memorability of images and videos, or face patches, or video compression, or any of the work projects that I'm involved in with colleagues and students. Because I have this talk which has been inside me for quite some time, and it is both a presentation and it's a whinge and a moan, and it's waiting for an opportunity. And when Alberto Del Bimbo sent me the invitation, I said, yes, this is the place where I can unload this talk, which has been inside me, bashing around for quite some time. So it's a talk with no graphs, no mathematics, no results tables. It's in order to peak and to retain your attention, though, it is a presentation with an extravaganza of unsplash images. So there's, if you don't quite agree with or follow or are interested in what I'm talking about, there's at least some pretty pictures to look at. So it begins by saying something we all know, that visual imagery assaults us, and that the digital forms of media are embedded into our life for work and for leisure and for entertainment, and the technology support for creating or capturing or compressing or storing and transmitting or rendering this multimedia information is now mostly solved. But the technology we use for finding information, or for having that information find us, is now a fantastic resource. And at our fingertips, what we have is ubiquitous, fast, scaled, dynamically updated search across media in various forms. And it just works, and it works seamlessly in the background. And it's based on many decades of work in information retrieval, which have been subsequently engineered into fantastic systems, which are a tremendous business story. Maybe not developed as much in terms of functionality as they could have, and perhaps have been hijacked by that business model and that business concern, and could do better in terms of the quality of the search service that we get. We use computer vision techniques to analyze visual imagery across a range of applications. So we've got medical applications, we've got autonomous driving, we've got surveillance, we've got generation of media, and we've got many, many more beyond that. And much of this is based upon our underpinning computer vision work on object detection, object tracking, classification, which has been catalyzed by the development of neural network-based architectures. And all of these applications, like medical driving, surveillance, and so on, are applications which are a means unto themselves. The computer vision is used within the application without requiring other information or resources or processing, which have equal-sized challenges. Now, by that I mean that computational challenges are the application without the dependency on computational challenges elsewhere. There's a little bit of a twisted point, but I'll come back to it later on. So the application is basically the application. Now, what I'm particularly concerned with is the topic of information discovery, sometimes called information seeking, sometimes called information finding, sometimes called information retrieval. And we do this for work and for leisure pursuits constantly throughout our day. And the reasons for our information needs, the causes for us to acquire information, are a lot of the times for support for our human memory and the fact that we have forgotten things. And the gaps that exist between our human memory and the systems which support us is what I want to address this afternoon. So today, I want to talk about information discovery for visual media, which is basically images and videos. And I want to go back in history to where we were heading, and where we thought we would end up in terms of information discovery, and why we are not at that place right now, and how we could change tack and we could pivot to a better place for information discovery, and what that would mean for computer vision. So throughout our lifetime, our memory fades naturally, and sometimes it can fail from a mild degree to a severe degree. Sometimes this is always caused by some neurological damage. And the neurological damage that can cause human memory to fail can be immediate, like with a trauma, or it could be progressive, such as with age or with some neurological diseases. It can also be fail as a result of drugs like alcohol or dementia or Huntington's or Parkinson's. But even without any of these factors, we just forget things. All of us forget things. We do not remember everything. And as many of you find as we get older, this forgetfulness starts to accelerate and become more and more pronounced. Now, the investigations into how long we remember things were first carried out by Hermann Ebbinghaus way back in the 1880s. I almost said 1980s, no, it's the 1880s. And the results of that work that he carried out are still hold true. And that is that there's an exponential loss from our long-term memory unless information is reinforced. So when you hear something once, right, unless it's hugely important, or unless you're hugely paying attention, or unless it's hugely emotionally significant for you, there will be a decay function associated with that, which is an exponential decay function. And it means that the best way to learn something, or not to forget it, is to learn it, then forget it, then learn it again a second time, and you'll forget it again, and then learn it a third time, and repeatedly relearning will reinforce, will burn it, hardwire it almost into your brain. So to stop memories from decaying and fading, we need to rehearse and to repeat and to revise through spaced repetition. That's why cramming just before an exam doesn't work. You need to have this spaced repetition of visiting material in order to be able to remember it. Now, there are other memory tricks besides the spaced repetition that we can use to reinforce our memory, like connecting something new that we know we want to remember with existing information that we already recall. So you weave it into your existing knowledge base, so to speak. And this is achieved using things like mnemonics or word association or visualization or chunking or breaking complex information or processes into smaller parts. And that's fine for learning something you know you want to remember. But so much of our day involves dealing with transient information that goes across our desktop. And at the time, we don't know that we may want to remember that, right? And it's subsequently, we realize the importance of it, and we have a need to recall things that we saw once that is now gone. Goes across our desktop or our devices, we see it, we interact with it, and then we move away. I'm also conscious that in juggling two things, I've come out of sync with the fancy presentations images. So these are examples of the memory tricks, the sort of rinse and repeat. Okay, we have busy desktops, right? That all of this visual information goes across in front of us, and we don't realize how important it is. Now, human memory already benefits hugely from the use of supporting technology. And the trivial example is phone numbers. We don't have to remember phone numbers anymore because our phones remember them for us, and we use aliases in order to access them. We also have notepads and post-its and tracking devices for keys and calendars and diaries and more, but we've never planned a technology from scratch which was designed to help our memory. We've evolved technologies to help our memory over time, and especially in recent times, and almost by stealth. Because so much of our lives are spent online and digital, we've learned that we don't have to remember things to the same degree as previously, because we can always search for things from our own past. You saw a web page, if you saw a news story, if you saw a social media post, you can always retrace or find that information by retracing the routes that you used to locate it in the first time. And this information, this finding or refinding of information, is a scenario where we want to locate or to relocate something we think we may have seen in the past, and there's a lot of conditions in that phrase. And that could be a word, a phrase, a name, a story, an event. And it could be something that's nestling in an image on a web page, okay? Oops, that's gone the wrong place. It could be something that's nesting in an image on a web page, or in an advertisement, or in a movie that you saw, or on social media, or in an email, or we may be able to recall certain aspects of it, but not describe it fully. Several years ago, in a study by Jamie Teven and others at Microsoft, she found that as much as 50% of searching for information is refinding information that you've already found previously, but you've lost it. In other words, you've forgotten where it is. And that study was based on 40%, a figure which came based on web searching and an analysis of web search log files. Undoubtedly, that percentage of refinding information is much greater than 40% now. Why? Because, well, that was just focusing on web search, but now we've become even more digital, and we have all of these other resources such as social media and email and other information sources which go in front of our desktop. So let's look at the technology that makes searching happen for us. Or before that, let's look at how it used to be. Information retrieval has been around for decades as a maturing discipline. And by the 1990s, it had evolved to a model of search which was based on a single query giving a ranked list of search outputs. And that ranked list was computed based on the statistical distributions of words in documents and in queries. We had mathematical models for those processes, like the vector space model. We had term weighting, giving higher importance to less frequently occurring words, things like TF-IDF, and weighting formula like BM25. We had language models for the distribution of words in text and in documents and in queries. And we basically represented queries and we represented documents as bags of words. Yet, at the same time, in the 1990s, we realized the difference between tasks that we may wish to perform.
Alex, I'm sorry to interrupt you. Probably you're switching slide, but we are not seeing this.
Okay. Yeah, no, I think I've gone ahead on the slides, but so I'm okay with this one for the moment, but thanks.
Oh, sorry for that.
Yeah, no, good. We realized the differences between tasks, between information needs, and between queries. And we had stateless search systems. So these web engineered search systems, which hit our desktops in the mid-1990s, were based on that model of information retrieval from the early and the mid-1990s. Stateless, right? No connection between queries. and no support for the differences between different tasks that we may wish to perform, the different kinds of information needs we may have, and the queries, the different difficulties that we may have in formulating queries. We were developing interaction models, theoretical models in the 1990s, where searches were incremental, where you search for something, you get results, then you search for something else which builds on that first search and extends that or focuses or broadens. We had simple techniques which were being introduced into systems, like the incremental value of additional information in a ranking. Currently, when you do a search, you get a result, and the first ranked one is the one that's closest, and the second is the second closest, and the third is the third closest. Well, by the time I get to the third or the fourth or the fifth, I don't want the one that is the third or the fourth or the fifth one, because it's a duplicate of what I've already seen. I want to have a ranking which includes diversity. So as we go down that ranking, I'm being introduced with more diverse documents and diverse outputs because I've already seen the duplicates earlier on. So those kind of simple techniques from the 1990s and into the 2000s were being posited as search systems that could be used. Then in the mid-1990s came the World Wide Web, and suddenly there was a need or an opportunity or a business model to provide search across all of the web. Unified web search, not unified search, but unified search across the web. And companies like Google and AltaVista competed to build the engineering for web scale searching across the web with really fast indexing, really fast search response times. This was realized using what information retrieval engineering and not information retrieval search could offer. Stateless search with no continuity or supporting the overall information seeking goal that enveloped each individual search. And instead, what we had with the web engineered search systems, and what we still have with those web engineered search systems, is on really fast response time to reinforce the illusion that you're actually getting somewhere with your search because it's so fast in its response time. Even if that search is taking you down a blind alleyway or up a cul-de-sac, you still have the illusion you're making progress. And the fault, if you're not finding relevant documents or relevant images or relevant queries, is your fault. Why? Because you haven't formulated your query well enough or appropriately enough. And that was, and it remains, the business model of fast response time with targeted advertising. And we accepted this because it was fast and it was free. And very quickly, we grew used to this as being the way that search operated. Now, we have small variations on that, and those small variations are minor. An example of this was about 10 years ago when Google introduced the knowledge graph, which still sits as a side panel on the output. So if you do a search for Alan Smeaton, you get all of the pages about Alan Smeaton, and you go on for pages and pages and pages of ranked list of documents. Oh, and there's this side panel here, which has been there for, I think, nearly a decade. So these variations on that business model of super fast response time on huge collections and huge sized indexes still continues and persists from the mid-1990s. As a service, search is free. And even though we pay for it with our data, as a quality service, it's not very good. Okay, let's take a worked example. Suppose you have a task, and this happened to me recently, so it was kind of interesting that it was exactly the same use case that came from Craig Manning's book on Introduction to Information Retrieval from a decade or so ago, right? We had mice at home, like mice, okay? And my wife, being the woman she is, says, how can we get rid of mice without killing them in a humane way? Could we trap them and take them to the countryside and release them? So my task was to find out a way to get rid of mice in a politically correct way, where politically correct means my daughter and my wife, okay? So my information need was to go for a search and find out about information about moving mice without killing them. I then had to turn that into a query, right? And I could talk to you or to anybody else. And I could ask a colleague by saying, how do I trap mice alive? But when I go to a search engine, it's mousetrap, okay? So my task with its very rich complexities has been dumbed down to the two-word phrase mousetrap. And of course, that's going to give me lots of stuff with the kind of version of the mousetrap rather than the catch, port, and release kind perspective scenario. So there's an example of the difference between the overarching task and the query that we are forced to use. I'm forced to verbalize my information need in words as short as possible because I don't want to type in a big long sentence into the search engine in order to get this. And we've become used to this. Web search and enterprise search use a brute force approach, and our overarching tasks, the things we actually want to find in terms of our information seeking, information finding, information discovery, there's a mismatch to the rapid fire stateless searching on the web and in our enterprises which satisfy our information need. So I type in mousetrap, I get some stuff. I then look at them, I say, oh no, actually I want to be alive mousetrap. And then I end up going down a blind alley and it's about 4 or 5 or 6 searches, my fault, so it seems, before I eventually get to what I'm looking for. So there's no support for negotiated discovery, no information exploration, no information seeking. And as users, we don't really miss this because guess what? We never really had it. And the reason for that is because information retrieval is hard. It's hard because we're all different from each other. We have different experiences, different backgrounds. And also, even with our different backgrounds and our different experiences, we have different information needs. Sometimes we're looking for information which is verificative. In other words, there is a method to trap mice. Or explorative, as in, is there a method to trap mice? Who is the president of the European Commission is a verificative query. Tell me about the European Commission is an explorative query, yet we probably use exactly the same words to type in those 2 queries, even though they are so varied in nature. Sometimes our information needs are precise. Where was the movie Castaway shot? Versus vague, as in, tell me a bit about the movie Castaway. Sometimes our information needs are short-lived, and sometimes they're for a long duration, as in, did you catch that mouse yet? Okay, which went on for days and days, versus short-lived, which is just give me something now and then I move on. And finally, sometimes our needs might have a cost associated with them, in that I'm prepared to invest of my time in putting into this search in order to refine it, in order that I want to get the document or the page or the image or the video, versus I'm too much of a rush. If I don't get it within the next 15 seconds, then it's too late. So with all of these different dimensions of information need coming from all of these different persons who come to search, what does search offer us? Well, what it offers us is this. Same homogenized search system, search query, rank list, browse, and if you're satisfied, great. And if you're not, then repeat by inputting a different search query. Don't go on to the second ranked page of ranked documents or web pages because nobody really goes there. Less than 10% of the time would a search go onto its second page. There's no relevance feedback. There's no state between one search and a refined search. There's no learning. There's no interaction. There's no conversation. And there's no complaints from us because we've got used to it. So search, as we know it, isn't really that good in those respects. And a further complication is that nowadays, when we see things for the first time, we may not be paying attention because we are all have a continuous partial attention and as we work and as we relax. The only one who's paying full attention to this presentation, I'll bet, is me, right? Because I have to, because I'm talking and juggling the PowerPoint and the cheat notes, right? All of you also have multiple tabs open on your browser, right? And if I've managed to retain your attention, your undivided attention for the last 20 minutes, then unbelievably, right? But inevitably what we have is we are multitasking because our devices, our smartphones, tablets, and laptops are multi-purpose and our browsers have multiple tabs. So as we see information that comes across, right, it may be something which at the time it comes across our desktop, we were only paying partial attention, and that's inevitable. And that means that finding information, which Jamie Teven says was 40% of the time, is actually much greater because when you saw the information in the first place, you were only half watching, okay? Now, recently, refinding has morphed into what is called personalized search. That's the term that the information retrieval folks are using it, where stateless search systems like web search are augmented or wrapped around with external resources like context information. But we're still short of supporting the broad information seeking models that were developed decades ago, although it's a step in the right direction. Slide. Visual search on the web is either duplicate or near duplicate detection or searching by tags. And systems like TinEye, which you see on the screen here, and its equivalent in Google and Bing and Yahoo and their equivalents are fantastic engineering achievements. I took that picture, which is a bit too small to see there, which is the brochure picture from the university I'm at, literally taken outside the building here. Shove it in, and within a couple of seconds, I find that, you know, which is searched through, I can't actually see the size of the thing, but it's 48 billion images have been searched in fractions of a second and found the 65 occurrences elsewhere on the World Wide Web, which have got this. Absolutely fantastic engineering to do this. But for ad hoc image or video search, where you don't have an image as your query, where you're trying to remember what you thought you might have seen, try to remember what you thought you might have seen. Gosh, there's an awful lot of looseness associated with that. And that's ad hoc image search, either on the web or through your own personal collections. And for enterprise or searching through enterprise systems like TV archives, what we do in order to deliver that system is that we reuse the model and the engineered infrastructure of text search. So even though images are not words, we still represent those images as words and as tags. And the intersection between computer vision and visual search is exactly this point. We tag images and videos with tags like words or phrases, and we reuse the bag of words, term tag weighting, and the vector space model and the language models of word distributions in a vocabulary of tags. That is the point which represents the intersection between computer vision with its fantastic achievements in other application areas like medical imaging, diagnostics, and autonomous vehicles. That's where that intersects with information seeking. It's as if information seeking or information retrieval has said, oh, we've got a system here, works on web scale. It only represents documents or, in your case, images or videos by words, but hey, it'll be really fast, it'll be really efficient, it'll give you really fast response time, we'll be able to do huge archives with this, and it'll probably do you some of the time for your search. So we've shoved the computer vision techniques into information retrieval models to engineer visual search. Why has there been nothing more? Why has there been nothing more adventurous, more challenging, more novel, or even perhaps even useful, right? Because it's not perceived as being worthwhile, perhaps, or more likely because it isn't perceived as being lucrative. Ad hoc or image or video search uses the use case for this are more, or rather they could be more frequently occurring in our day-to-day than using Unsplash or Shutterstock to find an image to illustrate a talk. And that's what I did. That was my image search and my video search in the last few days in preparing this, was finding all these images. But visual search at scale is the same engineering that we used for web search for documents. Ad hoc image search should be used to help me to find or to re-find information from my past. And that's because so much of my information across my desk and my devices and my TV and my Netflix and my social media is multimedia and image enhanced. News articles on all platforms have imagery. Social media posts have imagery. Instruction manuals for how to fix the washing machine or use a mousetrap, right, have imagery. Netflix movie covers have imagery. Advertisements have imagery, imagery, much more so than when the web first arrived and we developed text-based search in order to navigate us to web pages. Images and short form of videos are everywhere. And we know also from earlier on that we're always forgetting things where I last saw things, because we know from human memory from seeing earlier on that things get forgotten naturally. And because I work with multitasking and continuous partial attention. So I have continuous partial attention, I have a greater presence of imagery, I have an even more forgetful mindset, and yet still this gives a use case for an even greater need for sophisticated and useful visual search, rather than an engineered substitute, which is what we currently get. So I waste an awful lot of my time refinding information, yet each of the imageries I see could be a key to refinding some of that lost information. I waste this time trying to formulate what I think I might have seen as words, whereas the imagery associated with that if there was a more sophisticated and supported form of image search, then that would help me use up or recapture some of that time which is spent wasted on refinding. Now, this imagery as a key would be a complement to the methods we currently use for retracing our steps, and it would be much better than trying to describe using ham-fisted words to describe the contents of an image that I think I might have seen, and to formulate as a query to put into a Google-like search system. So what do I want to search among? Well, I want to search in my bubble. Okay, my bubble, my world, all of the images that I would have seen on all of the web pages, all of the emails, all of the social media posts, all of the news articles, all of the TV, all of the stuff that I have seen. I want to be able to search through that for the refinding task. Now, that's not the same as the initial finding of information that I may not have seen previously, but remember, refinding is more common than finding, and therefore, ergo, it follows that there should be greater support or specialist support for refinding. My bubble and the stuff I've seen will overlap with your bubble. So I'm being a little bit selfish by saying that I want to index all of my stuff, but some of my stuff will overlap with some of your stuff. So there could be some engineered solution and some cleverness in the back end that will allow a shared rather than a duplicated analysis of that. The challenges that this presents for computer vision and for visual search are much more complex than refinding equivalent text documents, because when we refind text, we generally recall the words or the phrases we use, whereas when we're trying to recall using images, we're using images as a key, then we can't use those words or phrases because we're not very good at formulating in terms of words or queries. And since so much of our visual information seeking is refinding, and our human memory is liable to forget things, this is what I see. This motivates the use case for visual search. The kind of techniques that are needed for computer vision and the challenges that this would pose to computer vision are that the indexing of the stuff in my bubble should be at query time, not in advance, because you don't know what I'm looking for, what aspect of what I'm looking for. It's only at query time when I start to interact and dialogue with the system. It should be done on the fly. It should be done in real time, and it should be done on all of my bubble. The targeted analysis for things which are specific to my query. So don't just index looking for indoor, outdoor, cars, bicycles, and all of the usual stuff that come with tags, but look for specific things in an image. So computer vision asks an image, is this here? Is that here? Does it contain? Rather than tell me everything that it contains. Analysis of imagery should be differential in that here's an image and here's another image. Tell me what's the difference between these images, because I'm the search system and I want to know which of these two, which are very close, is more likely to satisfy her or his information need. And of course, there should be reuse of previous analysis and sharing of analysis with past or perhaps even with future information seeking, possibly with others. So you think, this is conversational AI. This is conversational information. This is dialogue with the system. So is it conversational AI? Well, and this has become very popular with the advent of Amazon Alexa and Apple Siri and Google Home, etc. And these voice-activated and voice recognition systems were initially chatbots driven by neural networks mimicking human interaction and basically just putting queries to FAQ systems in order to answer, to give pre-canned answers to pre-canned queries and use very clever voice recognition. And it's a form of weak AI in that it was very narrow and niche in specific domains. But conversational systems are making progress and they're moving beyond just chatbots. And we've seen systems like IBM's Project Debater, which what it does is it doesn't just give you FAQ type answers, it will argue with you. So it will take ingest huge volumes of text documents in a Watson-like scenario, and it will allow you to dialogue and interact with it in a conversation in an argument forming scenario. Now that is a form of conversational AI, but it's arguing with 400,000 web documents that have been indexed. I'm not interested in arguing with 400,000 web documents. I'm interested in my bubble. So systems like IBM Project Debater, but applied to my bubble and applied to my visual imagery. So am I really talking about conversational AI for ad hoc imagery? No, because those conversational AI systems don't really search within my bubble or within my footprint, and I want to search within my bubble and within my footprint. So could this happen? Well, think about what it would look like. All of the stuff that you've seen or ever seen, searchable directly in answer to you, thanks 10 minutes, directly and answerable to you in a conversation or a dialogue, which retains information from one search to the next search to the next search during an information seeking session in support of a task. Now, the closest approximation that we have to this is an annual event called the Lifelog Search Challenge, which takes place at some of our conferences. This year it's taking place at ICMR. Previously, it isn't associated with any given conference. It moves around from conference to conference to conference. And what this does is it gathers a lot of information taken from visual cameras, wearable cameras, and it presents challenges, as in search challenges, to search through the visual camera imagery. And that's probably the closest that we have to this. Would I pay for this if I had this personalized search? Information seeking and computer vision combined together. Whoops, right? Information seeking and computer vision combined together, just dedicated to supporting my search in my bubble. Well, would I pay for it? No. And that's because we've grown used to not having to pay for in terms of credit cards and real money, right? We will pay for it in terms of our data. And if this will only work if there is a business model which would be sustainable for this. So think about the business model that could work for this. If I was to authorize or use a search system, then that search system would have to get inside my bubble. Okay, I would let that search system inside my bubble, and that search system would learn an awful lot more about me than the digital footprints and the cookies that I leave behind when I do web browsing today. So it would, if we think Google knows an awful lot about us, then this would be even more inside our souls. But I have to really trust a system in order to allow this to happen. And I don't trust these systems now. So these systems would be able to leverage this data to get more or even better targeted advertisements to me. But this part about the trust for these systems, my take on this is that this is a great idea. It was a great idea 20, 25 years ago. It could be done, but I think we've polluted or soiled the relationship between search systems and digital footprints and how they have been misexploited for our own benefit, or for the benefit of the companies rather than us. So information seeking and computer vision, is there a mismatch between the two? Yes, I believe there is a mismatch between the two. I believe there is a mismatch between the kind of analysis that we could be doing with computer vision to support this kind of search scenario, or support for search scenario. I believe that the engineering for business use case first, rather than for humans' actual information needs, comes second. That approach has been bad for image search because it made us change, and it has developed technology for visual search systems that are less than they could have been. So instead of supporting us, we were forced to change and to reuse the model of web search. So what happens next? Well, currently search, especially visual search, as it has grown, is growing in importance as being a key or an index to our finding or our refinding of information. That, however, isn't sustainable because of what search companies make in terms of profit from poor support for information seeking. We want more. If only we could see what we could get if we got better information, visual information search to support our information needs. And perhaps that's being a little bit idealistic and utopian, but that's what we're supposed to do, to think about these kind of things. In the end, however, I think we're caught because we're fixated on our own personal data and abuses of that personal data because of the past, and therefore we don't trust third-party systems to let them into our bubble or let them into our soul. We don't trust them enough for this to become more widespread. Finally, thanks as always to funding agencies. There's a laundry list of logos there for them there, and I'll take any questions that you may have in the 5 minutes we've got left.
Oh, thank you very much, Alan, for your speech. Very inspirational speech, I would say. So I was really glad to hear what you said, because most of the things that you have been presenting were also in my head in a way or in another, but not as formalized as in the way you did. So I think that there should be questions in the floor. So please don't be shy and ask yourself. Otherwise, I've got a couple of questions for you. But I would go first Who go first? No one. Come on.
In the gap, I could have my Cristiano Ronaldo moment.
Yes. Sure. So maybe Lorenzo, you got a question? I see you.
Yeah, so more of a thought. So what is your peak idea or opinion on the fact that, of course, some things are moved out of our ability to memorize, like, as you said, the phone numbers. We never remember those anymore. Now we are forgetting how to get from point A to point B because we have GPS and so on. You know my line of thinking. So what do you think this is going like in the future? What are we still be able to remember, or are we just going to be slave of our devices? So
I think we're becoming, and you look to younger people for the hint of what the teenagers would be like when they're in their mid-20s, or even younger than that. Yes, we will be slaves to our devices, is one way to put it. Or secondly, the flip way to put that is that our devices will support us more. And therefore, there's less of a need for us to remember trivial things, because those trivial things, and we can, in theory, move our thinking and our cognitive processes to a higher plane of thoughtfulness. In fact, we don't. We just get memory lazy. But this has happened with most of our senses. Transport, for example, we used to walk, we used to cycle, now we drive. Okay. We used to have poor eyesight. Now we've got spectacles and contact lenses. We used to have poor ear hearing. Now we've cochlear implants. So using technology to support the failings of our bodies or our minds is a natural thing. And I think while you might think, oh gosh, I don't want to have the devices, I'm going to be a slave to my device, I'm never going to be able to remember things because I don't need to. That's just natural human evolution in that trend. It's unstoppable. You can't stop this river of technology that's basically augmenting or supplementing or perhaps even replacing aspects of your mind. And as we get older, as we grow older, and as our lifespans increase, this dependency on devices will become even more so, because when you're at this end, when you're at the older end, when you get into your 50s, 60s, 70s, 80s, 90s, and 100s, then memory decay happens even more so. So I think while we start by looking at the younger people, really when we look at older people getting into very older age, then the dependency on technology as a memory prosthetic, as a memory prop, as a memory crutch, as a good thing for memory support, that's inevitable.
Okay, thank you.
Really looking forward to see my memory decay when I am 90, really. Let's hope I can do that. Is there any other question from the floor? Otherwise, yeah.
I would like to ask a question.
Yes.
Yes. Hi, Alan. Thank you very much for accepting the invitation, and thank you for the excellent talk. I would like to ask you about the issue of data availability and data silos in this concept that you presented, where you described all the data being available from social media and other actions and so on. Sometimes there seems to be the difficulty of this data not being available or interoperable and so on.
Yeah, because it comes from across different systems, and it's not sort of unified, and that isn't a bad thing, that there's one system for Facebook, and there's one system for Instagram, and there's another system for me, and there's another system for my email. But there are the idea of having your personal digital footprint stored on many different places is natural, and we're not going to change this. The only place where it is unified is on your desktop or on your smartphone or on your tablet. So I see the role of the thing that we're all looking at right now, whether you're looking at this talk through a phone, a tablet, or a laptop, as I am. This device, with all of its computing capabilities, this device is the place where all of those different silos of information can come together. Now, it may be then stored, virtually here, and then virtually stored on a cloud resource, but there is a place where all of your data is brought together, which is on your devices. So I think it's just, again, Yanis, I think it's an engineering challenge to bring those things together.
Okay, thank you very much. Thank you very nice.
I think we can have time for one more question from the floor. If no one is from the floor, I have got one burning question by me. Okay, but I will happily leave the floor to next. I see someone. Frederic Precioso, maybe. Go ahead.
So I join Yanis and all the others. Thank you very much, Alan, for this great talk. And you're famous in the community for years. I remember doing my PhD years ago, and you were already there on these topics. And so that's very interesting. I'm still have been wondering why in the last, let's say, decade, I remember some decade ago, we were all focusing on search engine to look for data, documents on repositories. Then the interests have shifted. And I'm still wondering why there is not so much intense research in transferring all the progress that has been made with deep networks on the content analysis to search engines. I mean, I would love to get some sophisticated, whatever Safari, whatever search engine you could have on your desktop to catch your words, or smartphones, but to retrieve documents very more efficiently than what you have now. I mean, all this software that we were using at the time, like Copernicus, or I mean, there was a bunch of local search engines that have almost disappeared. And I'm not understanding why there is no more effort or focus of the community to bring us this. I mean, I'm storing more and more PDFs every day. I would love to get something that is allowing me to find the document by the cover of the book or by the text. And I don't understand why this doesn't. So I don't know if you have ideas.
Yeah, I to put it into just simple words, it's because they make too much money already. There's a very simple model of search. Rapid fire, boom, 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 give you an answer in a fraction of a second, searching through billions of documents, and it puts the onus on us, right? Whereas the business model that drives that and makes companies billions of euros every quarter, right, is an engineering task which doesn't take advantage of this, of increasing the sophistication of the search, because there isn't as much money to be made on that. So, I mean, because I'm pressed for time, I could give you a 10-minute answer, or I'll just give you the 30-second answer. And the 30-second answer is because they already make so much money using that simple model. Why change?
Yeah, but why us don't we focus on this? Why not bringing this new?
Yeah. Yeah, you against the world. Well, you and me against, well, you and me and Yanis against the world, maybe, but it's because we are small scale compared to them. It's just.
Yeah. But you still have this book from Tomasi, I think, that was trying to make deep learning in search engine, and recent book. But I mean, it's not as trendy as it was 15 years ago.
No, and even the use of deep learning in search has been learning to rank. Okay.
Yeah.
I mean, how contradictory is that, right? Yeah. I mean, deep learning with its sophisticated insights being used to learn to rank. So instead of doing term weighting in IDF and BM25, right, it's learning to rank based on search logs. I mean,
yeah, I do agree. Okay, thank you very much.
Okay, thank you very much again. I think we had a very interesting and brilliant keynote and discussion. So I thank again Professor Alan Smithson for his presentation, and let's move on to the presentation session with the next speech, which is from our Italian colleagues from CNR, who are going to present VISIONE.
Thank you. So I'll share my screen. Okay, hopefully you can see my screen now. So hello everyone. I'm Lucia Vadicamo, a researcher at the Artificial Intelligence for Media and Humanities Laboratory of the Italian Research Council. And today I'm going to talk about VISIONE, that is a video retrieval system that has been developed by a whole research group over the last 2 years. And it was designed to include several models for the analysis and retrieval of video data. So with your system, a user can search for a target video by using full natural language sentence, so giving a description of a target scene. It can specify some keywords tags describing the scene, or we have also a canvas where the user can draw simple bounding box to specify objects within their location, appearing in the desired keyframe, together with the colors. And finally, our system also supports similarity search, so using an image as query. And this is our user interface. As you can see, there is this bounding, this canvas where a user can draw diagrams depicting object and colors, and the text box to specify keywords and description. And this is replicated because we also support temporal search, temporal query. So simultaneously search for 2 keyframes that are temporally close in a video segment. So let's see an example where we just search for one single keyframe. We have a palette with color and common object for an easy drag and drop on the canvas. Every time the user interacts with the system, the results are automatically updated. In this case, I was placing a cell phone, but the user can also type a different object that maybe does not appear in the palette. In this case, a person. So I'm searching for a keyframe with a cell phone person. The user can modify the size of the object, move it in the canvas, or refine the research, for example, specifying the maximum number of occurrence of each object. In this case, I was searching for one person. We can also add a tag, as I said before, for example, mountains, or a full-length description. In this example, a man holding a mobile phone, mountains are visible in the background. And these are the results. You can also test our system online at this link. VISIONE participated this year and also 2 years ago at the Video Browsers Showdown. That is an international video search competition. During the competition, a dataset of about 1,000 hours of video data is used. That is the same I showed you in the previous demo. And during the competition, 3 tasks are issued. The first is an visual no item search. So a short video clip is presented to the participants that have to find exactly that video clip. In the textual no item search, the task is again find a particular video clip, but without having seen it before. So the user knows exactly the content of the video. A detailed textual description is provided, but may have no clue or can't remember the visual aspect of the video. And the last task is an ad hoc video search, where a more generic textual description is provided, and the user has to find as many video shots that fit the textual description as possible. So this is an example of a textual quiz task issued at the Video Browsing Showdown, and how our system can be used to quickly solve this kind of task, for example, using the temporal query. So in this case, we were asked to find a video with a close-up of a blonde girl in front of a bookshelf, in between shot of her and elderly man walking. She wears a green vest. One of the old men wears dark and parted clothes. And in the final shot, they walk off and she turns around. So in this example, I used the first sentence provided in the query for searching the first keyframe. So the close-up of a blonde girl in front of bookshelf. We can, of course, expect the results. And as a second query, the second sentence that we had. So one girl and elderly man walking, and she wears a green vest. These are the top ranked results. We can group them by video. So this is the top ranked video. In the browsing interface, we can play the video starting from a given keyframe, or we can also inspect all the keyframe extracted in a video in a temporal sequence. And this way we find out that this was exactly the video we are searching for. The last keyframe is exactly depicting the final shot described in the text when she walks off and when she turns around. In this slide, I reported the overall architecture of our system. So we actually use we have several components because we exploited several state-of-the-art artificial intelligence techniques to extract feature and descriptors from the video keyframes. So relational aware features, visual features, annotation, colors and objects. But the main peculiarity of our system is that we transformed all the descriptors extracted from the images, as well as the query formulated by the user, into textual form. And this was as the advantage that then we can exploit off-the-shelf full text search engine to index and search the video keyframes. So this allows us to rely on the latest text searching technologies without having to worry about implementation issue. Now, unfortunately, in this talk, I haven't the time to go into detail of all the components of the system. I'll show you just two for instance, and also to show you some approach to transform these features into a textual representation. So for example, for the object and colors, for the detection, we use approaches taken from the literature, so not developed by the CNR, but that are in the state of the art. So various YOLO detector and also the recent varifocal net. In total, we have about more than 9,000 of objects. And we also use a palette of 11 colors. For transforming these objects and colors detected in the image, we designed this approach. We split the image in a grid of 7x7 cells, and we encode this information into textual document because, as I show you in the schema before, in the index we have several fields. In this case, we have a field to store the information about the class of the object and the colors, and a field to store the location of the object and colors in the image. So we create two textual documents. In the first document, we store in this example, the classes of the object detected in a keyframe. In this case, two persons were detected. So the first part of the document is person 1, person 2, then we have 3 vehicles and so on. In the second document, we store the spatial location. And for this purpose, we decided to give a alphanumeric code to each cell. And then for each cell, we store the class of the object appearing in that cell. So the first, for example, in this cell, we have 2 cars and 2 vehicles. So in the document, we will write the code of the cell A3 with the class of the object, car and vehicle. And so on, we do the same also for the colors. To support the search given a scene description, so a full natural language sentence, we use the transformer encoder reasoning network that was proposed by my colleague of the CNR recently at the International Conference of Pattern Recognition. And it is an architecture built upon one of the modern relationship-aware self-attentive architectures, that is the transformer encoder, which can spot out hidden intra-object relationship. And it text is able to produce both textual and visual features that lie in the same highly semantic space. This is the overview of the architectures. You can find all the detail in this cited paper, and also you can find the code on GitHub. So we have that image and text are seen respectively as a set of image, region, and sequence of words. And region and words are extracted through bottom-up attention model based on state-of-the-art approach. So for the image, faster RCNN, and for the text, the BERT. And then they are processed using transformed Bayesian reasoning modules. And in the end, they are mapped in the same space where they can be matched and compared using the cosine similarity. But now the problem is how we transform, how we can index this deep learned feature for image and text that are dense real valued vectors using a full text search engine. So we need to transform these features into a textual form. And for us, a text is just a space-separated concatenation of some alphanumeric words. And we suppose that inside, in the inverted index, the term frequency are used as payloads. So we have a code book of some code words and a posting list for each code words that store the document where that code word appears within their frequency. So once we have that, now the problem is how to do this transformation. And we propose to use the surrogate, what we call the surrogate text representation based on the scalar quantization approach that we proposed the last year in this cited paper published in Information Processing and Management, where we propose an approach to transform the deep feature into a sparse integer positive vector, as we will see in the next slide. And then one crucial point is that we use this integer vector as term frequency vector. So we build a text that we call surrogate text representation because it's made of some synthetic code words. In this case, I call it tau1, tau2, and so on, where each code word is associated to one dimension of the vectors. So in this case, tau1 is repeated 2 times because 2 is the first dimension. Tau2 is repeated 2 times, and so on. So in this case, we have a way to build a text whose term frequency vector is exactly the vector we're starting from. Still, we have the problem how to transform this deep feature into term frequency vector. And for us, the crucial point is that we want that this mapping should preserve as much as possible the proximity relation between the data. That in your case means to preserve the dot product, as we can use the dot product to compare this deep feature as well as the term frequency vector. And then for efficiency issue, we need that this vector, integer vector should be sparse, because we use inverted file to index the documents, and so each document will appear in as many posting lists as the non-zero element in its term frequency vector. So we should require that these vectors are sparse. And this depicts the main step of our approach. You will find all the detail in the cited paper and also all the experimental evaluation. In this case, just for your convenience, I depicted the vectors as histogram just to show you the different magnitude at the various dimension of the vectors. Is an example in 10 dimension, but of course in our kind of deep feature usually have thousands of dimension. So the first step is applying a roto translation. We recenter the data and then apply a random orthogonal transformation that preserve the ranking under the dot product, and also allow us to rebalance the variance of the components along over the dimension of the vectors. Then we should deal with the negative value, because frequency vectors cannot have negative values. So in this case, we use the zero-value transformation that simply makes a copy of the vectors, negate it, and concatenate both the original vector and this copy, and then keep just the positive values. So in this case, we obtain a vector that is twice the dimension of the original vectors. And finally, we threshold to flatten, we apply a threshold to flatten to zero small values, and this is needed for obtain sparse vectors. And we apply a scalar quantization where these factors as controls how many significant digit we want to maintain. In this case, we obtain integer vectors that is used as term frequency, and we obtain then a textual representation as explained you before by repeating each code words a number of times proportional to the term frequency. So in conclusion, VISIONE is a content-based video retrieval system that supports various types of query. We saw some of them today, and it also exploits several techniques for the analysis of the content of the video keyframe. As we saw, our approach is based on the idea of transforming all the information in a textual form to exploit off-the-shelf text search engine. However, there is still a room for improvement. For example, our system for now has a quite simple user interface. Let's say some advanced browsing functionality are not yet implemented, but is part of our future works. And more interestingly, for now, let me say that is an image-based system, because the dataset we used come with already extracted keyframe. We haven't already implemented our own keyframe and shot detection and inserted it in the system. But more interestingly, we would like to work on video to text matching. So if one of you is interested, we are open for collaboration, of course. And because now we have this text to image matching, but the temporal component is not analyzed. We are not analyzing directly video shots. So it will be very interesting to try find a way to extract features that are aware of both relation between object in the scene, but also the temporal components. So that's all. Thank you for your attention.
Thank you very much, Lucia, for the interesting presentation. And I think we have time for one question. If there is anyone from the floor, otherwise I've got one. Let's see, I don't think so. One speaking, so I can ask my question. This is somewhat related to one discussion we had before with Alan. So where we were about to where we were discussing why don't we include in the current search engines also advanced techniques like the ones we can see in your presentation. Then the answer was, well, because they already do a lot of money and blah blah. What I get from your presentation, of course, I would like to study in depth, but is that the system you set up is of a certain complexity, you know? And so my question would be, in your opinion, so from the opinion of the expert who knows the system, how much engineering work is needed to transform this into a full-fledged industrial level advanced engine?
Okay. As it is built now, actually, we try to make it simple. And so exploit, for example, as I said already, it's not commercial, but Lucene is public available search full text search engine in this direction to not really have to re-implement an indexing and searching approach for each kind of new feature that we could decide later to include, which component we would like to include in the system or not. So transforming all this system in a commercial application will not be probably the most difficult part will be the user interface, because we focus mainly on the techniques for extraction and analyzing of the video content and how to index them, but the product has not a user interface ready for a general user for commercial use.
Okay, but anyway, it's quite a separate functionality, so you can focus on that if you want to use something which is market ready. Okay, so I think that we could leave with 10 minutes delay if in the session if we have one burning question from the floor. Otherwise, I can switch to my presentation. Let's see if there is yet another burning question that can be solved in 2 minutes. Doesn't seem to be the case. Okay, so it is not the case. Thank you very much, Lucia, again for your presentation. Then I switch the hat from chair to presenter, and I will give my short presentation, which is about try to. Can anyone tell me if you see the full screen presentation?
Yes, you can see it.
Yes.
Okay,
Yes.
yes. Okay, let's move the gray box away. So in the next 20 minutes or so, I will try to discuss and to present theoretical and practical aspects about usage of archives and datasets for AI. This is the work that's being done jointly with my colleague Maurizio, who today is on holiday, lucky him. And so I will try to represent correctly these ideas as well. Okay, so the aim of this presentation is to illustrate the potential of using media archives for AI, try to identify some related challenges, and give some information on what we are studying and practicing at the moment. Everything in 20 minutes, but I think I can do that. Okay, so let's start from the archives. One may think that archives are stacks of cassettes that are stored in some dusty place there, maybe in Rome. But actually, this is not more the case because in the last years, there have been a massive digitization process in order to transform cassettes and tapes into digital files. So now all these media items are available in digital form, and together with the items, we also have a lot of metadata. Yeah, there are some assumptions that one normally does when think about media archives. The first assumption is that media archives store a lot of content. Well, this is actually true. I wouldn't say that this is not true. If you have a look at the content of RAI archives, which are the archive I know, we have something like 80 million documents available, something like 2 million hours of video, 2.1 million audio hours available, and so on and so on. And about types of material, we have television, radio and TV scripts, photographs, magazines, contracts, musical performances, costumes, scenography objects, and a lot of other things. So the assumption that the archives store a lot of content is actually true. If we want to put words into some fancy slide and think about a person trying to see all the media, all the content of the television archive of RAI, he would need something like 15 generations to watch all the content. So if he stopped right today in 2021, he should have started something like 450 years ago when Pope Julius III was elected and Tiziano was painting Venere and Madonna. So just to give you an idea of the amount of content, maybe when you think about 2 million hours, it's not really touchable. But if you think about this, maybe it is more concrete, Yeah. So the second assumption is, okay, we have all this content, we have all this information, it is natural to think that all this data can be easily used as data sets in AI applications. This is the common assumption, the common point of view of many collaborators, of many people we work on every day. Let's start with trying to define what is a data set from a certain point of view. We have several types of data set. We can have monomodal data set, basically a bunch of pictures or a bunch of audio clips. Then we may have multimodal data set, like for example, videos plus audio. So it's two channels available for the same item. We have annotated data sets, which add information about a description of what is happening in the scene, both from the video and from the audio point of view. And we also can have another kind of data set, which I call linked data sets, which contains not only the pictures and the audio, but also information about the objects, the locations, and the things that are more or less related with the scene. Most of the time, we hear and we discuss about annotated data sets, but we can have also the other kind of data sets as well. Looking into the RAI archive, we have basically all the types. We have monomodal data sets, like for example, videos and pictures of the same location under different point of views or under different historical shooting times. We have, of course, multimodal data sets. Videos themselves are kind of multimodal data set where you have, of course, pictures and audio at the same time. We have annotated data sets in our multimedia catalog. So you have pictures, keyframes, descriptions that relate to the audio part or to the video part, together with information about the people who are involved in the production or in the shooting of that particular piece of content. And also linked data sets. Like, for example, it happens that for an aired program in the broadcasters on radio, you have not just the content, but you have maybe the music sheet in the archive. Maybe you have a picture of the place and of the event where the music was played. Maybe you also have the booklets. So altogether, this information set sort of documents the events more than the media itself. So it's a sort of rich and organized description of historical events. Okay, what is bad or what is critical with annotations? The fact that it's made by humans, and sometimes humans have opinions. So you have issues that can be summarized as follows. Documentation data are sort of stratified, layered over many decades, and they are complying with different description models which evolved over time. So the description model the archivists used 20 years ago is different from the description model they use today. And the budget also has an impact, because you may have variations in the budget that makes the documentation better or worse depending on the moment. Then different documentalists may interpret and apply the criteria differently. So the same scene can be described quite different from depending on the user, depending on the observer. But even if you share schemas, they can be used using different criteria. So you may have maybe complied with the same documentation model, but then depending on the business domains, the model is used differently. Okay, another effect is that annotations are not the dream we would like to have. So this is a typical, say, dream of a researcher, in which you have the picture, which is exactly described, and each region is associated with a label describing that part. Well, actually, in the archive, you have something completely different. You have a clip of maybe 10 or 20 minutes described by a short, sometimes very, very, very short natural language sentence, in which you have a lot of implied templates, like, for example, interaction between persons, natural scenery and objects described in the same sentence. So if you really want to come to a, let's say, to a description that is similar to the one I showed in the previous slide, you have to do a sort of reverse engineering of the description to find the exact timing in the content where a certain description applies. So it's something that can be called temporal reverse mapping. So you have a description, you want to find the segments to which each part of the description applies. This is something where we actually are doing something lately. We are using the original description from the archive, and after a series of steps, like abstraction, translation into another language, tokenization, and so on, and most of all, visual linguistic alignment, we are experimenting to exactly tackle this problem. And I'm showing you a couple of examples where, starting from a full-length description pertaining maybe to 10 or 20 minutes of content, we are able to detect the parts or even the bounding boxes of the content, of the pictures, which are exactly associated with a certain part of the description. And this is a way to build data sets, from existing metadata in a way of in a sort of paradigm that uses AI to build data sets for AI. Another example is let's say the standard pipeline for phase management, which everyone knows, but where instead of starting from a generic list of names, maybe the word was list, we start from the names that we find in the archive descriptions, and then we are able in this way, following quite a standard approach, nothing really original, to build a pipeline in which the gallery reference is updated dynamically and is always aligned with the information which is coming into the archive, so that all the detections and all the labeling is done with respect to the actual names, with respect to the actual characters that are taking part in the daily productions, instead of having to rely on a generic reference list of names. But the theoretical problem, which is behind this stuff, is that you may have an archivist describing the content, but then you have other description domains which are interested in that description or in the content, which use a completely different way to describe the content. So this introduces a problem of adapting the descriptions that are in the archive to be used in other contexts. The case would be very simple. You have the source business domain, the archive, where you have media, rich annotations, but you don't have any pre-trained model. So forget to have any pre-trained neural network. You have just the media and the annotations. And you want to use these annotations to enrich the annotations which are published online by our platform, RaiPlay. Well, immediately you find out that the classification schemes are different. You find out that the kind of pictures are different, because typically online you find newest content, while in the archive you have maybe very different quality for the same object, for the same scenery, or for the same person. So I try to stick with what is the reference description of machine learning domain adaptation, and I suspect that the problem overall is something which is near to the unsupervised transfer learning, much more than in the other cases. Even if you think to have the same task, sometimes it is not the same task. This is the case of editorial segmentation, for example. If you take the archives, Raiteke, then they do segmentation, is done by documentalists who follow production item scheduling with no gaps and no overlaps. So the program is segmented exactly, and each change is exactly documented. If you see what happens on the online platform, you see that they are much more attentive to they pay attention to the highlights. So the two segmentations, even if you call them editorial segmentation, apply quite completely different criteria. So what I conclude is that you think that annotated datasets in the archive are good datasets for machine learning, but actually this is not true. You have to implement something which can be called dataset production, which is an industrial production that you have to think, to design, to set up. I tried to more or less to formalize this as a sort of transformation pipeline from a data set to a source data set to a final data set, in which you basically apply a cascade transformation until you reach the wanted conclusion. But of course, I don't have time to explore all the formalities here, but in that exact argumentation, it is also possible to model the costs that are related to each possible pipeline of dataset production and to write down equations that guide evaluations about costs, following which you can decide whether to go for completely manual adaptation, creation from scratch, or AI-supported adaptation. Okay, let me finish my small talk with the, let's say, a word of hope for all the researchers. Of course, I'm joking, because the final consideration is that datasets are also becoming objects of ethical concern. So my advice would be for you not to be in too much bad terms with your DPO, because if you want to use or exchange or do research on archive datasets or in general with the enterprise data, you should pay a lot of attention about ethical aspects as well. Okay, it has been fast, but I hope that was in a way also putting some light about the practical and theoretical problems that we have day by day when we wanted to exploit and to use the immense patrimony that we have in the archives for AI applications. So if you want to contact us to discuss, to contribute, to collaborate, you just have to write an email to us. So I'm open to questions. But now let me switch again to my session chair role. And if you got any, maybe one question, I will be ready to answer.
Alberto, can I ask you a
Yes.
quick,
yes, of course.
Like not really a precise question, more a comment. So in your talk, you refer to the mismatch between annotated dataset in your context and what we expect from a dataset as researchers for supervised learning. But what is your take on other regimen of training, like unsupervised learning? Because if you have all that data, maybe unsupervised learning could be feasible. I mean, if the researcher has the resources. So yeah. There's a lot of computation time to do that. But what's your comment on your data about that?
In fact, that's the big problem. The problem is both on the let's say on the fact that the kind of description that you have in the archive is actually not the one you need in the target domain. And so this, as a basis, it constitutes an issue that could be maybe partly addressed. I'm not an expert, but could be addressed in case you have a pre-trained model. So you have a set of models already trained being trained in the source domain. Maybe you can refine those models and to adapt to the target. But in the case as we are, which we don't have pre-trained model either. Then you have an additional problem, which is the one of producing the dataset, so transforming what you have in the archive to be usable in the target domain. So this is the big issue. And then you have to compare what to do. You want to completely rewrite from scratch the annotations, or you want to adapt the annotations. And if you want to adapt the annotation, you do it manually, or you do it assisted by some sort of AI, like the case we did with the trying to associate the description sentences with the video part. There's a sort of AI-assisted dataset production case. So that's basically the issue, and this is coming from practical experience. I mean, every time someone asks us about data, there is always mismatch between what is expected and what is available.
Thank you.
If I may add a comment, or actually to put this a bit more on the same sense is my question. If this unsupervised learning does not relate any completely, it's irrelevant to annotations. So for example, someone needs to train a method to build movie trailers. And in your archive, you have your movies and you have your movie trailers available. No annotation needed, not just the matching between the raw movie and the movie trailer, or the a TV show and a trailer for this TV show. Does it make easier for you to share this content, or are there any copyright restrictions that make this not applicable?
Well, in that case, you probably you're not in the unsupervised domain, but you're in some other easier case, because the task is the same. So you have exactly the same data you expect for your task. No, but in the case, yeah, there could be copyright problems. They're always there. And it depends on who you are. If for broadcasting company, for example, we have the rights for our own productions, but we don't have the rights for the movies. So if you want to perform automatic trailer production for movies, you should ask the majors to give you the content, not the broadcasters.
Okay, that makes completely sense. Yes, but even in the case of a RAI TV show, let's say, for example, if you try to learn a method to build the promotion video, let's say, for the TV program, then would it be easier? I mean, if you own the copyrights.
Of course, it is easier. Taking also into account that together with the copyrights, since a couple of years, we have also the data privacy problem. I call it a problem because it is a problem, for which we have also had very interesting discussions with our DPO. That was my suggestion, not to be in too much bad terms with them, because without them, you don't do anything. And after the discussion, the indication was, well, you can use content only if you show pictures of very famous people. Well, if this is the condition, then basically you can do nothing. Because if you take whatever piece from the archive, you have the famous people, but you also have the occasionally shot person in the background, or the less known people who were there right for the show, but they didn't give you the right to republish the content, and a lot of other complex law related stuff, which is actually very problematic. So together with the copyright, now there is also the privacy problem. Okay. That is provoking some headache to us as well.
Okay, thank you.
Okay, you're welcome. So I think that in order to remain within the 10 minutes delay, which is okay, we can switch to the next presentation, which is resume the program from the title is Learning and Reasoning for Cultural Metadata Quality from 3IA UCA France. Okay, the floor is yours. Who's going to present the next speech?
So is it Anna that is going to give the talk?
There is, I don't know the names, but Dr. Bobasheva, Dr. Gandon, or Dr. Profiost.
Yes, Anna will give the talk.
Okay, so the floor is yours.
Yeah, it seems that she has issues with the bandwidth.
Okay. Maybe if the other co-authors have the presentation, they can show the presentation while Anna is presenting, maybe audio only. If possible. Or maybe if this problem goes on, we can switch the presentation order so that we can give you some more time to organize. And if the next speaker, which is about DivClust, is available already.
I think it's there.
You mean your colleague?
I see the slides.
Yes. Yeah, okay.
But there is still a sound problem.
Yeah, I think you have to share the other window.
Yeah, you have to switch the window you share.
Or you, yeah. Like
or share the screen. Or share the screen
or
as
if you
we
go
did.
to the display settings and you do the switch screens, maybe it works. I don't know.
If you go to the display setting tab, top left.
No?
Yes, the next one.
Yeah.
Yeah.
No.
I think the first should be the
that
first,
one. Yes.
maybe.
Yes.
Yeah.
The first one is fine, Anna. You can switch with swap presenter and view slideshow. The first choice.
The first choice, yeah. Okay.
Perfect.
You can see it. Anna? You can see it, but we cannot hear you.
Yeah, we still can't hear you, Anna.
Maybe you can try to see if the correct microphone is selected in the. Sometimes this gets webex get it wrong. If you look at the where there's the mute button.
So maybe we can think about
So
participators.
okay, yeah, I hear somebody speaking. Wait.
Can you hear me? I had to call in. I don't know I've never used the webex. I tested with Zoom and everything was working. And okay.
Yeah, now we can hear you, so you can go on. Yeah.
Okay, just one second.
Go.
Just please give me 1 second.
Don't worry. We have time.
Okay.
Yes.
Oh. You see that? Okay.
Yeah, everything is fine. You can go.
All right. Okay. Sorry about that. Today, my name is Anna Babasheva. I work on Remix team at INRIA in France. And today I'm going to present our work on learning and reasoning for cultural metadata quality. That is a brief overview of our mono-year project that was contracted by French Ministry of Culture. The visual art collections are actually not just for pleasing our eyes, but also for giving us a knowledge that can be extracted from those collections. A lot of art curators are working endlessly to extract this data and make the data available through different interfaces, such as web portals. French Ministry of Culture has a long-standing interest in developing a search engine that can reliably search artworks by its content and also its properties like author or media or material use. And in the aspect, if we can provide some tools to make expert work easier and improve the collection. So right now, French Ministry of Culture receives a collection of the artwork called GCON with a public access through the web portal. At the beginning of our project, this collection had about 400,000 illustrated artwork records from French museums. The records include image and metadata. The metadata is stored in the RDF format and includes such properties like media, authors, museum, and also the description of content. Content metadata is organized according to iconographic thesaurus that was developed in 1981 by François Garnier. So we asked ourselves the question: can the digital artwork annotations be automatically enhanced and enriched by combining machine learning and knowledge representation and reasoning techniques? And can the annotation of the artworks be automated, or at least semi-automated? And can the search results be ranked by visual relevancy of the search criteria? And if the metadata model based on Garnier's thesaurus developed 30 years ago is still sufficient to describe the search of art? We combine two of the well-known and very powerful methods of deep learning from unstructured data such as images and semantic reasoning from structured metadata. Recent advances in deep learning, especially in convolutional neural networks, brought us a plethora of different models that we can use in image recognition tasks. And the semantic reasoning is the tool to query the data stored in knowledge graph in RDF format and extract a new and interesting fact through the reasoning. For instance, this is a graph of relations between Lagerfeld paintings and all the other entities that can be connected to. So obviously, these knowledge graphs are really interesting to mine. So we use these methods interchangeably in many steps and scenarios. And we reason to prepare training and data sets and validation sets and label it. Then we learn the model parameters to classify images, content to annotate artwork. Then we learn quantitative measures of object relevance to extend the existing metadata. And we reason on this metadata to improve quality and improve search results. We designed, sorry, nothing works. We designed a pipeline for our data to go through pre-processing, training multi-label deep learning classifier, applying training models, and extend metadata, and finally making queries to query this metadata. Let me get into details of each step. We extensively use Sparkle queries to query the metadata, and because the metadata is well structured using the RDFS and SCOS ontologies. Especially we focus on labeling using the property narrower that may give more interesting results. For example, for if the image is annotated by dog breed instead of dog itself. Also filter out certain concepts that don't have enough images. So filter out some concepts that certain media that cannot be classified. We balance numbers of training images per class, and we create missing links between some concepts, which I will discuss a little later. Then we selected and trained the deep learning classifier. We we've chosen between DGG16, Inception Z3, and ResNet 50, which have pretty much the same performance. And we choose Inception V3 for its speedy training and number of parameters that we have to store. We adapted the model to be multi-label classifier, fine-tuned the model, but even after that, the performance was much under the performance we used to see from the performance of photographs from ImageNet. But it didn't deter us, and we decided that we still can use the model prediction scores as the measures of visual relevancy, and we can store them. We can store them and reason on them. So we apply the training model and extend the metadata by saving the records in the same format as original metadata, RDF format, and we developed an ontology for that. And finally, we developed a few Sparkle queries to search on extended metadata and that enable us to detect noise and silence and search and rank results by visual relevancy. Here's our results in detection of noise and metadata. If we query our metadata to the concept horse that has dimension in the metadata, but has a very low prediction score, we can detect the noise in the metadata. For example, on the first row, you can see the sculpture that has absolutely no horse. On the second sculpture, it has a little horseman on the background that can be barely seen. On the third one, yeah, you can see the horse, but although it cannot be ignored, it is has to be of very little significance for this search. This is an example of detecting silence in metadata. By querying the extended metadata for the concept of a high prediction score, but that has no mention in metadata, we can detect those messages or those images that have some incomplete data. In all three of these images, you can see the prominent depiction of horse, but nowhere on the first two the horse is mentioned, and in the third one it's mentioned only through the indirect concept. It's a self-account. And here is yet another example of the benefits of searching using the metadata structure and deep learning prediction score. If we look for a dog among the sculptures of Pierre-Jean Jules Main on the portal of Ministry of Culture, we will not get this sculpture as a result. Why? Because it's not described as a dog, it's described as a greyhound. But when we classify this image, we can, although we get a very high degree of certainty, we also can derive that the greyhound is a dog. So if we run the same search now on our extended metadata, we can see that the image of the dog is almost at the top of the list. While we creating our labeled training sets, we noticed that not all the semantically similar concepts are linked in Garnier thesaurus. For example, on this picture, this painting, the human or man is represented by the words soldier and horseman, but the words soldier and horseman are not these concepts are not related to the concept of human in the hierarchy. That led us to poor labeling and a poor model performance. And we had an idea to add this newly found relationship back to the thesaurus, and that helps a lot in the creation of the training data set. Then, sorry, I can't. I'm very sorry, but my mouse doesn't work too.
We can
If you
still
want
hear.
to, now I can progress your slides.
You can?
Yeah, I asked for the control.
Okay, go ahead. Next slide, please.
It takes a little time for me
Okay.
to.
Okay, I got it. So this empirical discovery inspired us to ask questions. Are there other pairs of concepts that can be linked to improve the image context annotation? Can we find those pairs by studying pairwise co-occurrence and or distance between them in the metadata knowledge graph? Can we find the missing links by accessing external vocabularies, including the same concept? We think we found a few answers to this question, and by contrasting image, by using certain metrics and contrasting certain metrics with each other, we can detect that some pairs can be in fact linked. For example, the most interesting metrics that we can use on pairs is our scarcity index to measure similarity in the context, and distance similarity that measures the distance between the concepts inside the knowledge graph. We devise a simple algorithm that ranks this metric and subtract the ranking of the distance, and that pushes the pairs that are different by they're not connected by the thesaurus, but very close in the context on the top of the list. Thus, we could confirm that horse and horseman and boat and sea and horse and hitchcar are in fact related pairs. And we can use the same technique by adding them to the thesaurus. We also wanted to look at not just Garnier thesaurus, but also in the DivClust, and luckily we had a mapping between most of the concepts in Garnier thesaurus to the DivClust categories, and by extracting the subgraph from DivClust, we could calculate the distances between the concepts in this much broader graph. After visualizing the results, we can in fact see that concepts like crown, hat, helmet are close together, and they are close together in Wikipedia, but they're not close together in Bernice resource. And the same goes with the uniform, armor, and helmet. So this findings can help the art curators to annotate better the collection, and without much work on their part, if we just update the scissors. And finally, we wanted to see if within those pairs, if having one object on the image can help detect another object of the image on the same image. For this, we use the pairwise odds ratio. We estimate the pairwise odds ratio between two objects of concepts appearing on the same image versus not appearing on the same image from the metadata, and then we apply this regression to the scores of the probability scores that we have derived from we obtained from deep learning model. And on this slide, we can see that if the prediction score threshold, for instance, was set very high, that the concept C will not be put in annotation, but if adjusted by the high score of concept both, the prediction score of C was elevated and it made a cut. In a summary, we found all the positive answers for all our research questions, and in the meanwhile, we designed a few tools that could be very useful in a broader sense, and we published our code at GitHub, which is made public. And thank you very much for listening and coping with the technical difficulties I have. I would like to thank the Ministry of Culture of France for supporting this project, and AI4Media for allowing me to present it, and my colleagues and advisors, Dr. Zandon and Dr. Preciosa. Thank you very much, and I have questions.
Thank you very much, Anna, for your presentation, and also for overcoming the technical difficulties that were today. I think that we have still two presentations before the closing of the session, and my approach would be to, of course, not to have the final discussion because we don't have time, but maybe to finish at 20 to 5 with the presentations. So if we follow this plan, we can have time for one question to Anna on the floor. If there is no question to Anna from the floor, I have one, as a good chair always should have. And my question would be, of course, when you let's say extend or modify or improve, so the annotations that you have in an archive, in this case it's a cultural heritage archive, with additional automatically extracted information, you always may have the problem of understanding why the documentalist or the archivist has provided exactly that description and not a word more. So have you analyzed and studied the problem of say not to give too much impact on the work of archivists with this approach, which by the way I found very interesting, but in general terms, I would say.
And not really, but we've also realized that because of the experts were using these outdated thesaurus and follow the rules there, that was probably one of the source of noise. Maybe not the experts themselves, but no, we did not study why the experts make their decisions like this.
Okay, I see. Well, thank you very much again, Anna and colleagues. Let's switch to the next presentation, which is by Queen Mary University of London, DivClust, learning multiple clustering with a diversity controlling objective. Who's going to present?
I will. Hello, everyone.
Hello, Yanis.
Give me 1 second to share my screen. Okay, can everyone see it?
Yeah.
Okay, so good day, everyone, again. My name is Ioannis Maniadis, and I will present our ongoing work on deep clustering, which focuses on producing multiple diverse clusterings with deep clustering models. I would like to start by briefly defining deep clustering. Standard clustering methods, such as k-means, generally require a meaningful feature space on which to be applied. However, they perform very poorly when applied to raw, high-dimensional data, such as images. Deep clustering deals with this problem by combining feature extraction and clustering in an end-to-end trained model, which is trained with objectives that the developer believes will lead to meaningful clusters. An example of such an objective is, in the case of images, that transformed views of the same image must be confidently assigned to the same cluster, and that clusters must be of roughly equal size. As can be seen in the slide, the typical architecture of a deep clustering model includes a feature extracting backbone model like a ResNet, followed by a projection head that assigns samples to clusters. However, these models only produce one clustering, which is then evaluated based on its overlap with the ground truth tables of the dataset. The motivation for our work, however, is that there is, in fact, no inherently correct way to cluster any given set of data. The ground truth labels of a dataset simply represent our preferred way of partitioning it, but it is not necessarily the only partition of the data that might convey important or useful information. Therefore, it can be beneficial to have a way to produce multiple clusterings while controlling how similar they are to each other in order to be able to explore and utilize different partitions of the data. Accordingly, our work has focused on developing a method that, given a deep clustering framework, can expand it to be able to produce multiple clusterings while controlling their similarity. In the context of clustering more broadly, the problem of creating diverse clusterings has been addressed by various works. Some examples include Koala, DK-means, MNMF, and MultiCC. Koala proposed an algorithm for analytically building clusters by starting from individual data points and merging them in ways that fulfill quality and diversity objectives. DK-means starts with two clusterings, one from k-means and the random one, and iteratively updates their centroids so that they are decorrelated. And MNMF and MultiCC use matrix factorization techniques to find non-redundant clusterings. Importantly, however, none of the existing methods in the literature can be incorporated in deep clustering frameworks, as none of them are backpropagatable. To solve this problem, we propose a novel loss function that can be used in deep clustering models to control the similarity between the clusterings that they learn. Importantly, our loss is meant to be complementary to existing deep clustering methods. That is, it can be incorporated into existing frameworks along with their own objective, so that the multiple clusterings that are learned have the properties that each framework considers to be meaningful, while also being as diverse with each other as we want them to be. The first step toward defining this loss function is to define a way to measure interclustering similarity. In this context, each clustering is represented by a cluster assignment matrix P, which indicates which samples were assigned to each cluster. In this matrix, for each sample, the corresponding row vector P gives us its probability assignment across all clusters, and therefore it tells us which cluster this sample was assigned to. For each cluster, on the other hand, the column vector Q gives us the cluster membership vector, which indicates which samples were assigned to that cluster and with what confidence. The vector Q then can be seen as a descriptor for the corresponding cluster. Our objective then is, given two cluster assignment matrices, which correspond to two clusterings, to compare the similarity between the clusterings that they represent. And the reason I emphasize that is that it is not sufficient to compare the matrices directly, because our method of comparison needs to be invariant to permutations of cluster indexes. So in this example, which we have in the slide, it's very clear that cluster 1 of clustering A is almost identical with cluster 2 of clustering B. They have very similar cluster membership vectors Q. However, a direct comparison of the two matrices would miss that due to their being in different columns. To correctly compare the two clusterings, we define the interclustering similarity matrix S for a pair of clusterings A and B. Each element of S corresponds to the cosine similarity of the cluster membership vector of a cluster from clustering A with a cluster from clustering B, so that high values indicate more similar clusters. For instance, cluster 1 of A and cluster 2 of B, which again are nearly identical, have a high similarity in the corresponding value of the intersimilarity matrix S. Importantly, this matrix is a representation of the similarity between the two clusterings overall, since it expresses how similar each of their clusterings are with one another. And since it is backpropagatable and how it was calculated, we can directly apply restrictions on it that would limit how similar individual clusters are with each other, and therefore how similar the two clusterings are overall. Using the self-similarity matrix, we define two losses that control the similarity between clusterings in different ways. The first loss assumes that we want each cluster of A to be more different with each cluster from clustering B than a similarity threshold D that we decide. That is achieved by forcing all values of the intersimilarity matrix to be lower than that threshold D, since they directly correspond to the similarity between those clusters. That is done via the cluster-wise loss that can be seen on the slide, which, as is shown here, can be easily implemented through a ReLU activation and global average pooling. So again, this first loss restricts the similarity between each pair of clusters between the clusterings. That is, it guarantees that for each cluster of clustering A, there will be no cluster in clustering B more similar to it than the similarity threshold we've decided. The second loss applies when the objective is to control the similarity of the two clusterings not on a per cluster basis, but rather on the aggregate. And in this context, we define the aggregate similarity between clusterings to be the average of the similarity of each cluster of A with its most similar cluster of B. It is then required that this average value be smaller than the similarity threshold D. What this means, in effect, is that with this loss, we allow for some pairs of clusters to be even identical with each other, as long as they're counterbalanced by other less similar ones in order to satisfy the similarity threshold on the aggregate. And again, this slide shows that this loss too can be implemented with very straightforward operations, all of which are backpropagatable. Finally, to see how the proposed losses may be incorporated to an existing deep clustering framework, we see here again a generalized formulation of such a framework. The model projects data points to cluster assignments, which are used by the main loss of the model to train it to find appropriate clusters. Again, that is how it works when we only want to find a single clustering. To incorporate our proposed loss into this framework, we first choose either of the two losses that we went over as the diversity enforcing loss. And then the model is simply extended with multiple projection heads to produce multiple clusterings. And the total loss with which it is trained is the original loss of the framework for each clustering, plus the diversity loss between each pair of clusterings. And this is actually one of the major advantages of our method, the fact that it is plug and play and can be easily incorporated into existing deep clustering frameworks, as long as they produce a cluster assignment matrix P from which to calculate the interclustering similarity matrix. Moving on to the experiments that we conducted, we implemented our method by incorporating it in two deep clustering frameworks. Those were Pika and IIC, both of which require the cluster assignments to be transformation invariant and highly confident, and that clusters must have the same size. We trained our models in two different ways. The first way, we trained all clusterings and their corresponding projection heads in parallel from the start of training with the required diversity restrictions. In the second way, we start by training only one clustering, and then more clusterings and their diversity requirements are added in the training process incrementally. So we start by training the model for some epochs to produce one clustering, then two, then three, and so on. In the first case, a global solution that satisfies all clusterings is sought from the start, as all clusterings are trained in parallel. While in the second case, each time a clustering is added, it essentially explores solutions around the previous ones, which are already relatively well-defined as they've been training for longer. Together with the two diversity losses we proposed, these two training configurations, we believe demonstrate how versatile the proposed loss can be, depending on what the user's end goal is with regard to clustering diversity. That is, what kind of alternative clusterings they want to explore. In terms of evaluation, we want to evaluate our method on three properties. First, how successfully it restricts interclustering similarity. Second, how well defined the resulting clusters are. And third, how meaningful they are. To evaluate interclustering similarity, we use the NMI metric between the cluster labels of the resulting clusterings to measure how similar those clusterings are with one another. Here we expect the NMI to decrease as we decrease the similarity threshold D. To evaluate the quality of the clusters, we measure the average confidence of cluster assignments, which we expect to be high since confident cluster assignments by the model would indicate that the clusters are well defined. And finally, we measure the accuracy of the clusterings, which is how similar they are with the ground truth labels of the dataset, to evaluate how meaningful they are. It is important to note here that to evaluate our method, which produces multiple clusterings, we aggregate those clusterings at the end of training to obtain a single consensus clustering solution, and we then compare its accuracy with that of the models that only produce one clustering, and that serves as our baseline. For our first experiment, we apply our loss with the Pika framework on CIFAR-10, where we test different numbers of clusterings and upper similarity thresholds D to validate that our method works as intended in all these scenarios. From the results, you can observe that the NMI indeed decreases as the upper similarity threshold decreases, while the confidence remains high. What this means is that our method is successful in its primary objectives of controlling similarity, actually restricting it, while producing clean and well-defined clusters. Notably, you can also see in table A on the left that with a threshold value of 1, which is basically just Pika freely learning two clusterings without our loss restricting how similar they are, the NMI is 0.995, which means that the clusterings are almost identical. This highlights that our approach is indeed necessary to actually get really different clusterings from deep clustering models. And it is not sufficient to just change the architecture to learn more clusterings, because unless this restriction is applied, they tend to converge to a single solution. In the second round of experiments, we again use CIFAR10 and applied DivClust with both the global and cluster-wise losses and with both the IIC and Pika frameworks. We do that for 10 clusterings. And again, we observe that our method works with both models, with both versions of the loss, and it successfully restricts similarity without sacrificing the quality of the clusterings. Importantly, in all cases, the aggregate clusterings that our method produces have a higher accuracy score than the one produced by the single clustering baseline, which we believe highlights an important use case for our method in producing clustering ensembles. Finally, we test DivClust on CIFAR10, CIFAR100, and STL10 using Pika with overclustering, which is a modification proposed by their paper that increases accuracy. We train the original model with 1 clustering and then incrementally add 9 more clusterings for a total of 10 with similarity restrictions. And in these results, we see that DivClust again improves performance in terms of aggregate accuracy. So to summarize, in our work, we developed DivClust, the pair of losses that I outlined, and we have demonstrated that they can be used to effectively control the similarity between clusterings in deep clustering frameworks in a plug-and-play way. Additionally, we demonstrated the use case for DivClust application in that it can be used to obtain aggregate clusterings that are better in terms of accuracy than the clusterings produced by single clustering frameworks. That would be all from me, and thank you very much for your attention.
Thank you very much, Yanis, for your presentation. Quite I mean, concrete and very clear in the exposition. Thank you very much. We have one question from the chat. When you define your loss functions, you define clustering A and clustering B. What were they? Was any one of them the ground truth label?
No, since this is clustering, the ground truth labels are unknown to the model, and they're only used to evaluate those clusterings after they are produced. These 2 clusterings, our method extends to any number of clusterings. We use 2 to simplify the notation for the presentation. These 2 clusterings are, just that, arbitrary clusterings that the model learns based on the objective function of the base framework. So as I mentioned, for Pika and IIC, this means that the clusterings A and B must satisfy the requirement that the assignments be transformation invariant and that they equipartition the data. And with our loss, we also apply the restriction that they must be different with each other to the extent that we want. I'm not sure if I've covered the question.
Okay. I think so, but then
okay.
The answer is thanks. So I think it was clear. So before switching to the next and final presentation, I have another question for you. I think we have time. Basically, you described a general framework that can be applied to an arbitrary number of different clustering techniques. Actually, my question is twofold. The first one is how the let's say the training time scales up with the number of clusterings, and the second one, if you have any concrete application case in the media domain in which you find out or in which you plan to experiment with your solution.
Okay, so with regard to your first question, applying our loss has a minimal computational cost in itself in terms of the extra computation that is required to calculate it. As the number of clusterings increases, that is, as the number of projection hits increase, There is a computational overhead. However, it is very small. And to be specific, if I recall correctly from our experiments, we saw the training time come close to doubling only after we increased the number of clusterings to over 10. And of course, it scales somewhat linearly because it is solely dependent on the number of projection heads. And I would note that, of course, that is much more computationally efficient than another way of producing diverse clusterings, which would be to run the same model multiple times or with subsets of the data or other options that might be available. With regard to possible applications, we don't have anything concrete yet. This is an ongoing work, but one of the directions that we're looking at is to find other applications, although I'm not sure if we're going to go into more practical works.
Yeah, so maybe AI4Media use cases would suggest you some interesting case. Maybe you can go through them and see to start any collaboration. We would be available, for example, to explore. Yeah, so thank you very much again, Yanis, for your interesting presentation. And let's switch to the last presentation, for which we have a good timing left. So the last one is by CERT and Queen Mary University. Again, deep learning-based video summarization, current landscape and future directions.
Hello, hi there. This is Evlampios or Lapis Apostolidis here.
Yeah, the floor is yours.
Okay. Can you see my screen now?
Yeah, try to put in presentation
Yes,
mode.
of course. Okay.
Yeah, it works.
Okay. So my name is Evlampios Apostolidis. I'm going to present the current landscape and future directions on the field of deep learning-based video summarization. Just to mention that this is the outcome of a collaborative work between CERT and Queen Mary University of London, and made under the supervision of my supervisor at CERT, Dr. Mezaris, and my PhD supervisor, Professor Yannis Patras. So let's start by a question. Do we really need video summarization technologies? To answer this question, we should think of two facts. That video is the most descriptive means of communicating something, presenting an activity, an event, and that nowadays video is actually everywhere, captured by smart devices, wearables, and with functionalities that allow instant sharing in online video sharing platforms and social networks. For example, only YouTube was recently announced that more than 500 hours of video content are uploaded on their platform every single minute. So from the video consumption side, the question is how to find what we're looking for in endless collections of video content. A part of the response to this question, besides content retrieval technologies, is to develop methods that allow to create a short synopsis of the visual content and give the viewer the possibility to quickly inspect video's content by checking this synopsis. The same technological environment necessitates also the generation of different instances of the same video material for distribution over the different communication channels available. For example, social networks, video sharing platforms, and media archives. So how to produce all these different versions? Someone would need a technology, a tool that facilitates content adaptation, reuse, and repurposing. For example, that facilitates, that accelerates the preparation of a concise and complete summary of a TV series episode for the archive, of a shorter video for distribution via Facebook, and of a very small piece of content for distribution via Twitter. So what's the goal of video summarization technologies? Is to generate a short visual synopsis that summarizes the video content by selecting the most informative and important parts of it. In this slide, you can see a snapshot of Britain's Got Talent show, And after the video, right below the video player, you can see indicators of the key of the most representative frames and fragments of the video. These should be the analysis outcomes of an automated video summarization tool. And using these outcomes, one can create a static video summary composed of the keyframes, which is also known as a video storyboard, or a dynamic video summary, which is formed by stitching the key fragments in chronological order, and is also known as a video scheme. The current state of the art in the field is represented by methods that use deep networks and learn summarization in an unsupervised, supervised, weakly supervised, or fully unsupervised manner. And in this illustration, you can see a typical pipeline of a deep learning-based summarization method for generating either a storyboard or a video scheme. So the video is decomposed into frames, and then usually a subset of these frames is fed in a pre-trained CNN to extract deep feature vectors that represent their visual content. These feature vectors are then given as input to a trainable deep summarizer network, which either selects the most descriptive frames and creates the storyboard, or given a segmentation of the video, usually into its building blocks like the video shots, to select the key fragments of the video and produce a video scheme. So, based on our study of the relevant literature, we propose a taxonomy of the existing deep learning-based methods. At the higher levels of this arboreal illustration, you can see that these methods can be coarsely divided into unimodal approaches that rely on the visual stream of the video, and multimodal analysis approaches that also exploits textual modalities like the video title or the video metadata, etc. And the former class of methods can then subdivide it into supervised learning, unsupervised learning, and weakly supervised learning methods. In the next slides, we can see more about the lower parts. It's different class of these methods. So starting from visual-based supervised approaches, these methods learn summarization either by estimating frames importance based on their spatiotemporal dependency. And to this end, in this schema, we can see that such a summarizer gets as input the video frames and of course the human annotations, and then using different types of networks within, either architecture structures of RNNs, attention models, memory networks, tries to model the temporal dependency of the frames, or even more complex architectures such as combinations of CNNs and RNNs or convolutional LSTMs to model the spatiotemporal dependency of the video frames. And using these internal architectures tries to learn how to predict the importance of its video frames, given, of course, the human annotations. Another type of this class of methods tries to confuse a discriminator to discriminate machine and human-generated summary. So in this case, these methods use generator discriminator architecture, so GANs particularly. And after feeding the summarizer with the video frames, then the predicted summary is given as input to a trainable discriminator, which tries to make the distinction between the machine-based summary and the user summary. And a computed similarity score is used as a feedback to the summarizer to try to be better and better and try to fool the discriminator when seeing the summary. Moving to unsupervised approaches, these methods learn summarization mainly by confusing a discriminator to discriminate, this time the original from a summary-based reconstructed instance of the video. So again, we have generative adversarial networks in this quite big class of methods. The summarizer and the discriminator both get as input the original video, and then the summarizer contains usually a keyframe selection part, which estimates frames importance and selects the summary, and generative part that uses the summary to reconstruct the original video. Then the reconstructed video is given as input to the discriminator along with the original video, and the discriminator tries to make the distinction between these two. Once again, the similarity score is given as input to the summarizer, which is trained in an adversarial manner with the discriminator, trying to fool the discriminator by making a reconstruction of the video that is quite convincing. That is the original one. A few methods, unsupervised methods, target specific properties of the summary using reinforcement learning and tailored reward functions. The summarizer of these methods gets as input the original video, and then, according to some rules, targeted rules, predicts the summary. The evaluator gets the original input and the generated summary, and according to some reward functions, returns a reward value to the summarizer. This value is utilized based on the principles of reinforcement learning for training the summarizer. And finally, one method of this class of methods. Sorry, I think my screen is freezing. Okay, tries to model the motion of important objects. Actually, what these methods it does is that it initially divides the video into object level motion clips and then applies the same summary to video reconstruction mechanisms at each one of these motion clips. Moving to weakly supervised approaches, these methods learn summarization either using semantically similar web videos and aim to find commonalities among them, or using annotations from a similar domain and uses these annotations with cross-domain feature embedding or transfer learning approaches. For example, using annotations from first-person video summarization datasets to learn general purpose video summarization, or using weakly or sparsely labeled data in combination with reinforcement learning and handcrafted reward functions. The last class is multimodal supervised approaches that learn summarization using textual video metadata. And the main goal here is to progressively learn how to build a summary that has a good overlap in terms of semantics with the semantics of the video metadata. So these methods can be utilized for video category-driven summarization or metadata-driven summarization, etc. To evaluate video summarization, the most commonly used datasets are the SAMI and DivSum datasets. Both, as you can see, both of these datasets are small datasets with small videos, short videos, 1 to 10 minutes duration, and each video has been annotated by multiple users. The annotations for SAMI are in the form of video key fragments, so each annotator indicated the most important parts of the video, and in the case of DivSum are in the form of frame level important scores. Other less commonly used datasets are the OVP and the YouTube datasets. Also, small datasets also. The annotation comes in the form of a keyframe-based video summary. So for each video, you have 5 different collections of keyframes. And these datasets are mainly used in combination with SAMI and DivSum for data augmentation purposes. According to the established evaluation approach, the generated summary through deep learning methods should not exceed 15% of the video length. The agreement between the automatically generated and the user-defined summary is expressed by the F-score in percentages. Usually 80% of video samples are used for training and the remaining 20% for testing. And the summarization performance is formed by averaging the results on k randomly created data splits, and usually k equals to 5. From a comparison of the existing state-of-the-art unsupervised methods, we can see that the top performing ones are all rely on generative adversarial networks to learn summarization. So the typical schema for summary to video reconstruction that were described before. A few of them also integrate tailored attention mechanisms to better learn how to estimate frames important. A couple of them that rely on reinforcement learning do not show very competitive performance. And a couple of deep learning methods show random level performance. From the comparison of the existing state-of-the-art supervised methods, we can see that the best performing ones rely on the use of tailored attention mechanisms or the use of memory networks to model variable and long-range frame dependencies. Strangely enough, a few of these methods show very good performance in one dataset, but quite poor or even random level performance in the other dataset, thus seem to be highly tailored to the specifications of one of these datasets. Methods that were originally designed for unsupervised training, there was no gain after being trained with a supervision signal, too much gain at least. The use of textual metadata also does not seem to lead to extremely better performance compared to unimodal approaches, and the use of weak labels also show limited effectiveness. Once again, a few methods, state-of-the-art approaches show random level performance. In this slide, is used to make a point here that the top 5 methods among the top 5 methods in the bibliography thus far, almost half of them are unsupervised, which means that we can build highly competitive approaches for video summarization without using any source of video of ground truth annotations. These are some general remarks that summarize what I presented previously, and this slide is mainly for facilitating discussions after the end of the presentation. So given this study, we indicate the following future directions. Given the limited availability of ground truth data and the competitiveness of unsupervised video summarization, we argue that one of the main directions is to build methods that can be trained in unsupervised or in a semi-weakly supervised way, thus eliminating or minimizing the need for fine-grained human annotated dataset. Another direction would be to extend current ideas for unsupervised video summarization that mainly rely on this summary to video reconstruction process, thus targeting to build a highly representative summary by exploring mechanisms that introduce additional criteria about the content of the summary, such as its temporal coherence. Develop semi-weakly supervised approaches that allow users to intervene in the summary production process. For example, mechanisms that allow to generate a summary according to textual queries about the desired summary content, or establishing an online interaction channel between the editor and the summarizer in combination with active learning methods to incorporate the user's feedback about the content of the summary. Improve the training of unsupervised methods using augmented training data that not require human annotations, combined with curriculum learning approaches. Improve the training of weakly or semi-supervised summarization methods using data-driven approaches, such as using large sets of unpaired data, for example, raw videos and video summaries with no correspondence between them from a particular domain or application scenario, to allow a deep learning method to automatically learn a mapping between these raw videos and the summaries of the domain, so to get knowledge about the requirements of summarization. Overcome weaknesses of using RNNs for video summarization that mainly relate to the modeling of long-range frame dependencies and the parallelization of the training by advancing self-attention mechanisms that to encode frames position and model temporal dependencies as well. And of course, to exploit the audio modality of the video, which is another rich source of information. For example, can be used to spot the thrilling parts of a movie that should appear in a movie trailer, or use audio and video-based video segmentation to create summaries that offer an even more natural story narration to the viewer. This slide summarizes the contribution of the collaboration between CERT and QMUL in the literature thus far. So we We have proposed 3 unsupervised video summarization methods with state-of-the-art performance. We have proposed an unsupervised method for video thumbnail selection, which will be presented in the upcoming ICMR conference, and a new measure for evaluating video summarization, and of course a survey of the relevant literature that is currently available on archive and is under review for presentation. Thank you for your attention, and I remain to your disposal for questions.
Thank you very much, Avrampios, for your comprehensive study and presentation on this matter, which is always, let's say, very important for us as media companies, the ability to support summarization in a way. So it is very relevant, to my opinion. So really, I would like to exploit the last 3 minutes of the session to hijack the, the conversations this time and to put my question. That would be one future direction that I see missing, if I can, is to try to extend the reference datasets. Because I've seen that the reference datasets that are used in these comparisons are made up of few minutes videos. So I was wondering whether you put the programs that last 2 or 3 hours, if the corresponding technical methods would be of the same family, would be simply an extension of the current literature, or would be completely different and new, because the size and the dimension, the temporal length of the content would introduce, let's say, would evidentiate the limits of the current methods. That would be my question to finish.
This is a very good question. This is something that we would like to examine. Unfortunately, the existing data sets are quite small, and also in terms of the video number and in terms of the video duration. My estimate is that the existing architectures that have been evaluated on these datasets would need serious adaptation to make to show a good performance on quite larger videos. And the reason is that these methods heavily depend on the use of recurrent neural networks that show limited memorization capacity. One approach that was proposed was the use of external memory, storing data in external memory disks to make it feasible to capture a very long range dependencies among frames. But this is only one proposal. And of course, the evaluation of all these methods, or at least of publicly available ones, on quite larger videos would be a very interesting study.
Yeah, very interesting indeed. So I think we are in perfect timing to hand over to the next session. So I would like really to thank all the presenters, starting from our keynote speaker, Alan, who's still online, I see, and all the other speakers that today contributed to a very interesting session, in my opinion. I hope this opinion is shared also among the participants. So now it's time for the next session to start. Thank you very much again. And
thank you.
Congratulations to all for your research.
Oh, I think if there are, oh, hi, Lorenzo.
Hey,
so
hi,
I think I can start as a chairman, as a presenter, both. So thank you everybody for listening to this presentation. I ask if you can see my slides. I hope, no, I didn't, sorry, share the screen. Let me share the screen. Share screen. Yes, here we are. And here is so this is the first presentation of this last session. We have only 2 presentations, a lot about games. So I think it's a good way to finish this long, interesting workshop before the final discussion in a multimedia, interesting, funny way. So I will talk to you about learning virtual worlds, and these slides are prepared by me, Marco Di Benedetto, Luca Ciampi, Fabio Carrara, and Giuseppe Amato. So Content. We are talking about content all the day, but let's say again that annotated content has been a driving force in the AI renaissance. And as an example, and the example that we usually use is ImageNet, that was so important in 2012, sorry, for the renaissance of AI on image classification. And in AI4Media, we have in this work package 5 that this workshop is about, a task which is learning with scarce data. You already have heard a lot about few-shot object detection, GANs, unsupervised representation learning. And now we will talk about virtual environments. Why we will talk about virtual environments? Because they have been used for a long time in things like reinforcement learning, in which you have an artificial intelligence that has to interact with an environment. And you see, this is the famous DeepMind's DeepQ learning demo, 2015, yes, 2015, playing a game at Atari. So what's going on? There is a computer, a software, which is the environment, the game that, you know, I'm quite old. I used to play, and I hope some of you used to play with. But on the other side, you have artificial intelligence, which is watching the frames out of this environment and deciding what to do, actions. In this example, for sure, you see vision is not that relevant. I mean, the information is somehow very raw, very unreal, etc. But things have changed a lot. No? And in 2017, we probably, I think I was a commercial but now should be better. Okay. In 2017, there was a paper, interesting paper, in which that was beyond Grand Theft Auto 5 for training, testing, and enhancing deep learning self-driving cars. So self-driving cars were training, tested, etc., in an environment that was a game, GTA. And why this is important? Because in this kind of games, in these games that we usually see, they are very realistic. So there is the possibility to train for vision, to train artificial intelligence intended for computer vision. And for instance, this is the last, April 2021 demo by NVIDIA about ray tracing with a GPU by NVIDIA. For sure, you see how detailed they are and how real they seem. So in coming to our group, I work at Artificial Intelligence for Media and Humanities Laboratory, as Lucia Vadicamo before, at the ISTI CNR in Italy, in Pisa in particular. We have 4 subgroups, let's say. One is the one that I coordinate, which is vision and deep learning. Then we have multimedia, information retrieval, on a larger scale, which is coordinated by Claudio Gennaro. Then we have digital humanities, AI for text. And we are interested in learning virtual worlds for computer vision. And I will give you some examples, okay? We are not the only ones, we will see, but okay, we are interested and we do this in the context of the AI4Media project. So probably the first, if I'm not wrong, dataset we developed using GTA was a virtual pedestrian detection dataset. We leverage on the work by AI Image Lab at University of Modena and Reggio Emilia, probably you know Professor Rita Cucchiara, and they did this work for joint track, no? And we generated bounding boxes around every pedestrian in this dataset, and then we created our, let's say, extension of this dataset, which is called VPED, that you can find on our websites and so on and so forth. And just to have some videos, interesting video to show, it looks like this. You see the person, you see the bounding box. On this, you can train a neural network, and you have a different position in the world, let's say, very different situation, different weather condition, and so on. So what we did in this paper in 2020 that has been published on sensors, but okay, we have also other publication you can find on our website. Of course, what you could do, what you can do, and what we did first was to train on synthetic images and then to fine tune on real world images because there is a gap. So you have to do something to adapt the training that you do on virtual environment to real scenario, real camera like this. And but also we tried a mixed batch training. It means that we trained at the same time in each mini batch synthetic images and real world images. Okay, the results you can find in the papers, but what I would like to highlight is that training, a little bit surprising, training both together synthetic and real images in each mini batch resulted in very good results, very good performance, especially on MOT 17 dataset. I mean, we always test on real data, so the results are on real data. The problem is where you train the network. Okay, so this is, as I said, results on real dataset that are public available and accepted, let's say, by the community. And you see that it works quite well after training on virtual world. So we did other things in case where we have scarce data and in case where we can find these data, these objects, let's say, virtual environment for personal protection equipment. Another dataset, which is called Virtual World Personal Protection Equipment dataset, you can find on our website. And there are 7 classes of protection equipment. In this case, we also, let's say, created the test for testing on real-world images because they were not available on public available datasets. So we have virtual world images we created on GTA, and also we have these are 140,000 virtual world images, and then we have a small batch, 220 real-world images annotated by us that are real, in which you can test the results of the training. So just to have an idea of what we are talking about, so the virtual part, these are the person and the protection equipment with annotation we were able, and in particular, Marco Di Benedetto, Fabio Carrara worked on this, but I will talk about this again. And you see, very different weather condition. Of course, there is some gap in visual appearance with the reality, but it's promising also considering that, okay, things in visual computing are getting better and better every year. So what we did in this case was to pre-train on the virtual stuff and fine-tuning on the real images, and taking the results from the paper. What I want to underline is that of course it was necessary to have a very good performance, to have a small amount of real images after training in the real world, in the virtual world. But as pointed out in this slide, only using 100 real images, we obtained very good result, over 70%, you see, in most of the categories, and learning in virtual worlds and just using this small amount of real images. Of course, you can even having a training only on virtual images, but in this case for protection equipment, we found that it's let's say, more problematic. And a final example of a real video that we built inside the project of personal equipment, personal protection equipment detection, and you see how it works. So some publications, we have a paper on multimedia tools and application, and a paper at CBMI 2019 that also got the Best Paper Award, and part of this work has been done in the context of Personal Protective Equipment Safety I, which is a project funded by Tuscany region. So in GTA, you have a lot of cars. So not surprisingly, we worked, in particular Luca Ciampi, on traffic and auto counting, etc. So on the left, you see generated frames on GTA. in particular situation of traffic, and the annotation that we can extract automatically from the information inside the game, and is a ground truth. In the paper that was presented at VISUP 2021, we presented interesting unsupervised domain adaptation, which is not only specific for synthetic to real, also for other things, but we'll focus on this. What I want to show is that in this case, for counting, we are using density, which are these, let me have a pointer option, pen like this, okay. You see this part are density estimation of the cars in the place. From these, we extract the information about the numbers, okay? In this case, we define this unsupervised domain adaptation that works like this. The density estimator extract the density estimation for both real and training images which are from real world. Then we have a discriminator network, okay, that discriminates if this density, each pixel of this density extracted is coming from a real world image or a virtual world image. So we have a loss that try to fool the discriminator, so to have density estimation that look the same if they come from real world images or virtual world images from which we have the ground truth, and for sure for the source images for which we have the ground truth, we have the labels, we have the annotation, and we can also have the loss, which try to, to learn to count, to have the density estimation on source images which are from the real world, virtual world. As I told you in the paper, we use this for the unsupervised domain adaptation, day to night, camera to camera, camera to camera, again in this example, and synthetic to real. And so the focus in this talk is the last, let's say, example, which is a synthetic to real adaptation. So it is possible to adapt the training done visually for the computer vision on the virtual world to real world images, even in a unsupervised way. Unfortunately, we are not together today because of this COVID-19, and this was an opportunity for most of us to work on these things like social distancing. This is an example we built on Marco Di Benedetto did on GTA. And you see in this case, you can see a real, a virtual environment in which people are working. And if they are too close, respecting the rule of the social distancing, it's red and green, okay? So you can have a virtual environment in which you can try to learn or to test things that you develop for this. And we did some work on this. And we have a paper that has been submitted at Aspect System with the application recently. And in this paper, we present a lot of approaches, but in particular in this example, you see in Pisa a square in which we have a camera, and detecting people in this square, we are able to understand if they are too close, red one, or far enough for reducing the diffusion of COVID. And this also is using the results of training performed on virtual worlds. And recently, probably you have heard about using AI for making images like this. You see on the left, you have the game. On the right, you have the enhanced photorealistic stuff. I found it interesting. Let me play it again. Because, in this case, artificial intelligence is used to make the frames from the game more real. This is interesting because the more real they are using artificial intelligence, the more we can use them for learning other things like computer vision stuff. Of course, we have to pay attention to how this impact with the training, because there is some artifact, etc. But is, let's say, something very interesting because artificial intelligence can be trained in virtual worlds and also used for making virtual worlds more similar to real world. So here I put the photos of the people involved in the worlds we have seen from our lab. And let me just underline Luca Ciampi, which is working on counting, vehicle counting, people counting, things like this for his PhD. And so most of the things you have seen have been done by him. And Marco Di Benedetto, which is artificial intelligence researcher, but also has a background of visual computing, and his, let's say, background has been fundamental for understanding how to take, accessing the information inside games and how to create the virtual worlds, etc. So this is enough for this presentation. Discard the annotation. If questions are welcome. I am also the chair of this session, so I cannot ask myself, but also let me jump to the, okay. Stop sharing. Let me see if in the chat there are some questions. Okay, one last function. Okay, no, it's not for me.
So Fabrizio, I have a question
Grazie.
for you.
Many thanks, Lorenzo.
Yeah, okay, so I'm thinking about the application you have shown for protecting personnel. In that case, it seems to me that you could leverage the GTA engine with the skins of the models and so on. But I'm thinking about maybe in a different domain, you may not have a 3D world that is okay to generate the data. So can you comment on the cost of this part that has to be, has to be done like manually? Can we maybe think about a way of generating this world with AI? So
if I got the question, you are mentioning the fact that in some situation you have to create the 3D environment, the 3 models which are appropriate for the training that you have to do. Is this the question? Yes?
Yes. So
yes,
let's
yes.
think about,
so
I don't know, like...
Yes. Let me add something. Marco Di Benedetto in particular told me that there are huge amount of 3D models that can be both, but they are very expensive because they are intended for video games, etc. So you're right when you say that probably we need something to generate, and you mentioned the AI. And so this is also very interesting. Of course, if this will continue, there is a lot of research, scarce data also, unsupervised learning, etc. But if I think there will continue to be the need to train something for visual in virtual environments. And the 2 most important things probably are, one, trying to have visual worlds that are in appearance more realistic, but not for us, for humans, but more realistic in terms that are good for training, which is something has not been tested. Games that tend to be very funny, for instance, not very real, and also they are not intended for training. Another thing is that, okay, for the moment we have games that have a lot of stuff, but they cannot have everything. AI for generating the 3D models will be fine because on one side to manually create 3D models is very expensive. And on the other side, when the models are available, they are sold to big companies like Epic for Fortnite, things like this. And so imagine to buy this kind of 3D models, not probably very business, it's not sustainable. Thank you for the question, very interesting one. So considering the time, I think we can move to the last talk, which is also about game, but a different perspective, which is preference learning for modeling motivation in games. Is by Gravina and Mellart, which are people from Model AI in Malta. I think Gravina is going to talk.
Sorry.
David
Yes.
Mellart. Sorry, I searched for you before my talk. You were not, I didn't find you. So, David, thank you. Please share your screen.
1 second. Let's see. Is this working?
Yes, we can see, and I can hear you very well. So,
great. Thank you. So how much does our gameplay reveals about our motivation? How would we even measure it? Is it even possible to reliably predict motivation based on just gameplay alone? Hi, my name is David from Model AI, and I'm here today to address these questions and talk about preference learning for modeling motivation in games. In this talk, I will be talking about these general topics, covering player modeling, what is player modeling, why is it important in the larger field of AI research, preference learning, including the theoretical background for it, why ordinal modeling matters and why it's a good choice to model user behavior and user cognition and emotion, and some of the technical considerations in the type of preference learning, pairwise preference learning that we are using. Then I will talk about how to measure motivation using self-determination theory and the Ubisoft player experience questionnaire. And in the final bit of the presentation, I will talk about an application that we are currently developing to implement an end-to-end pipeline to measure motivation and record game telemetry and predict player motivation in a dynamic way. So first off, player modeling, or as often called game user research, is a field of user research which is focusing on understanding and often simulating gameplay. Generally, it has two main areas, which we call clustering and prediction. Clustering is basically static aggregation, usually by unsupervised learning or statistic methods, and mainly used in something called player analytics. Prediction, on the other hand, is a dynamic method that uses often session level predictions or even moment to moment predictions of gameplay outcome. Here we're focusing on predictive player modeling, which can be further broken down into behavioral modeling when we ask the question, what do the players do? This is, for example, churn prediction, where we try to estimate when people are going to quit a game. Or experience modeling, when we ask ourselves, how do players feel, which includes emotional outcomes and what we are interested in now, motivational drives. So, but why player modeling? What does player modeling has to do with the larger field of AI, and what can it offer? I would say that building and entertaining games is a good goal on its own, seeing the size and the reach of the games industry. However, games have applications far beyond entertainment. Serious games are used in the domains of healthcare and education and beyond, and they help people to learn and recover from injuries or debilitating statuses, providing value far beyond the entertainment. Player modeling also helps us to understand the performance and psychological state of our users, which can help us deliver a more engaging experience. Beyond the enriching interactive experiences, however, games user research also provides a robust testbed for different AI applications. Games are a unique combination of interactivity and freedom in a constrained environment. This provides basically a sort of naturalistic environment, as it was discussed in the previous presentation as well, that is somehow also controlled. So we have all the variables at hand. We know what's happening at all times. So it provides us with a very robust, very configurable, but comfortable test bed. So to preference learning. Preference learning is a paradigm in machine learning, which is unlike regression, which focuses on predicting the absolute values, and classification, which focuses on predicting nominal labels, is focused on predicting ranks or ranking different outputs. To contrast preference learning to the traditional approach,
we can look at studies in human-computer interaction, affective computing, and user experience research in general that predominantly use ratings and absolute scales. So the traditional approach to game user research and user research in general is using different tools to measure absolute ratings like Likert and Likert-like scales, self-assessment mannequins, or even time-continuous rating tools when somebody is asked to use an annotation tool that gives, I don't know, every 1 second a new value, and they adjust it in a 1 to 100 scale usually. Oh, sorry. So traditional approaches assume that the data is either interval or nominal, and they generally model data through the regression or classification, although classification is the more popular of these two approaches. So this is what they usually do. However, if we look at evidence from psychology, economy, neuroscience, we can see that the underlying phenomena that they are trying to model and trying to predict, be that cognitive processes or emotions, are actually ordinal. So we can see that an adaptation level of an individual interferes with their reaction to stimuli, and we, as humans, create sort of anchoring points in our experience that are contrasted against the new stimuli, just like with ordinal data. So we as humans know if one experience is better or worse than the other, but we don't really know, we don't really have an internal absolute scale for this. More than this, temporal biases also can affect the activation and appraisal of affect, emotions, and other cognitive processes. Cognitive and emotional regulation, therefore, is an ordinal process. We don't have objective scales and rate stimuli internally. So representing cognitive outcomes and emotional outcomes as interval or nominal data can introduce severe biases to a data set. When trying to represent ordinal data as other types of data types, a series of conceptual and technical problems arise. Treating ordinal data as interval data introduces subjective reporting bias, where the subject might try to maintain a different scale than what the researcher thought about when they were designing the experiment. On the other hand, treating ordinal data as nominal data introduces something called a split criterion bias, because classification and converting data to nominal classes, basically discretizing the data to a lower level of granularity, usually either as high and low or discrete emotional or cognitive categories, which might not reflect a fuzzy ground truth. So instead, we aim for an ordinal approach, where an ordinal representation focuses on the differences and preserves the subjective nature of the ground truth labels. We are interested in the relative relationships in the data instead of the absolute values, which are more noisy due to the subjective reporting bias. This approach is applicable both to ratings and ordinal labels. In the first case, what we call first order data processing, we collect the ground truth as rankings in the first place. This can be tricky, especially when we try to collect a large amount of data, a lot of questions, or trying to aim for something like time continuous annotation. So the second best thing we can do is called second order data processing. It means that we don't have to change any of our traditional tools. We can collect the ratings, but we interpret ratings as ordinal labels instead of nominal or interval ones. So how do we apply this in pairwise preference learning? Through something called a pairwise transformation, we apply a second order data processing using pairwise observations between data points. We treat ratings as ordinal observe their relative distance, and then discard the absolute values of these ratings. The new dataset that emerges after the transformation encodes the pairwise distances between individual data points, reformulates the problem of ranking as binary classification, and because there are two observations being made between data points, so we compare A to B and then B to A, the resulting dataset has always has 50% baseline. And there's an added bonus. Due to the number of observations, the dataset can grow quadratically, which means that we can learn on much smaller datasets as well. So this was the sort of like more technical part, and now on to the theoretical underpinnings of motivation and how do we measure it. So while we can also opt for looking for different drives, like what drives the players, what they find fascinating or enjoyable in a game, we opt instead to follow the theory of self-determination, which is more agnostic to the domain. The theory of self-determination describes motivation as a function of psychological needs. There are three of them, which I will be explaining shortly. And it also differentiates between so-called extrinsic and intrinsic motivation. So intrinsic motivation is elicited by external pressures and rewards, but has the downside that it has diminishing returns and eventually it can lead to a feeling of burnout. So this is an issue, especially when we are trying to build games that promote wellness, like mental and cognitive wellness and well-being. If we use sort of like traditional gamification and put in rewards and pressures, this can build and sort of like external motivation that can be measurable, but eventually will leave the players burnt out. So instead, we are focusing on intrinsic motivation, which are facilitated by our own psychological needs. And generally, it is more beneficial to our mental health and leads to well-being and a sense of fulfillment. So we know that when we measure a high sense of intrinsic motivation, we are also measuring a level of the player's well-being. So these three main factors of intrinsic motivation and our three basic psychological needs are competence, which is a sense of accomplishment and mastery over something, autonomy, which is a sense of control and self-efficacy, and relatedness, which is a sense of belonging or connection. Obviously, in games, it is not always another player. Sometimes this can be like a bot or the environment. And we're adding presence here, as it is a major factor of the game experience. Presence is basically a sense of being there and the authenticity of the experience. Sometimes it is explained as a feeling that a mediated experience is not being mediated. So to measure this, we use the Ubisoft Player Experience Questionnaire, which is a 21-item, 5-point Likert-like survey. It measures the core factors of intrinsic motivation and presence. And the motivation score can be averaged into a big factor item. So how do we apply this type of surveys in machine learning? So we integrate this survey into the game that records players' answers after a full play session. We use an aggregated gameplay telemetry as an input to our models. So we model the motivation during a given session, and then model the four factors of motivation separately. The resulting models can be used to assess player motivation of unseen players and identify core groups in the player base based on their motivation profile. So based on which type of motivation is more natural to them, or what kind of motivation they usually have. So this general approach has been already proven successful before. A study titled Your Gameplay Says It All already looked into using this type of survey on a very, very high level. So they modeled, this study models gameplays on a 2-year level, and tries to evaluate users' whole lifetime in the game. But it was very successful, and it was very successful both in predicting differences between player motivation and also creating motivation profiles. So how do we try to model motivation instead and approach UPEC and motivation modeling instead is on a much more granular level, and we experiment in building an end-to-end pipeline. So the goal of our project is to integrate the UPEC survey into a streamlined process that collects both game telemetry and user response in a seamless manner. We created a test bed for this project, which is a simple racing game, and collected preliminary telemetry data in-house. We collected the telemetry in an aggregated level, as we discussed earlier. And we hope that this telemetry can describe the gameplay dynamics and also latently the player motivation. The predictions are then converted back into a global ranking of the players based on their pairwise performances. And they're also working on a web application that can visualize the predictions and help interpreting the results. So this is the current state of our testbed. As you can see, players can choose generated tracks and their own player car, and then race against AI-controlled cars. The game telemetry is logged during the race, and after the race, they are greeted with this motivation survey that records their responses. The motivational factors are generated from their responses and sent to our backend pipeline. Our preliminary models use support vector classifiers to predict the difference between two players with quite good accuracy, considering that we have very limited data at hand at the moment. The results show that preference learning works reasonably well on limited data sets as well, with plenty of room for improvement. So as mentioned earlier, we can also use this type of prediction to create motivational profiles. Here, we check the correlation between the predicted factors and the motivation, or predicted factors of motivation and the telemetry features, which also provides us a good sanity check about the survey results. So we can see that high competence players are usually high performers. Autonomy players are usually having collisions and off-road, having more fun with the game. Relatedness players usually are mid-level players who drift among the bots. And presence players are generally the novice players based on their telemetry data. So the web interface we are developing and is still on its early stages, let us visualize the collected data and the predictions of our models. The web interface displays the predictive motivation of and profile of players and the features associated with their performance. It also visualizes some of the correlations, but you can see this is somewhat limited information, but we are working on improving the visualization that provides a richer information about the player population. So finally, a few words about us. We are Model AI. Our vision is to unlock the potential of AI and machine learning for every game developer. And we are developing AI engines that operate throughout a game's lifecycle, from automatic QA to telemetry data and game playing bots to live operations, from the first steps of the development into the life cycle of games. We are a growing team with a global presence in 3 continents, which allows us a great flexibility. Thank you for having us and listening to us. And if you have any questions or inquiries, please don't hesitate to get in touch with us.
Thank you very much, David. And as you told, please, if everybody wants to make a question. You mentioned that in the car game, there are cars controlled by artificial intelligence. And so I was wondering how could be modeled, let's say, the AI if it was considered a player, and more in general, modeling players in environment in which there are agents which are AI could even help AI to be more human-like, or things like this. Do you believe that is an opportunity or not?
Yes, so just for clarification, I think that was a slip of my tongue. So in this game, the bots are not artificial intelligence; it's more like game AI. So it's more like just behavior trees. But to answer the actual question, I think it is definitely possible, and we are striving to actually create human-like bots in other projects. So we have other projects going on where we research how we can create bots that are not just play the game well, but play the game according to how a player would play it, right? And create this.
Yes,
and obviously motivations can play a huge part of that.
Yes, because in different scenario in games, but also Alexa, I mean, many artificial intelligence that we see around have good performance, but they act in a way which is different from humans. And the more you know about how people, real people, play in games, the more you can have artificial intelligence similar to humans in ways like gun. I mean, if they are able to simulate the behavior, motivation of real humans, then they will be more human-like and more interesting to interact for us, at least, if not more good in playing.
Yes, so, definitely. And as you said in your presentation, it also provides us with more robust test beds for other applications as well, not just games.
Yes, of course. This is also very important because, yes, the work that you are doing in games that can be used even outside games. Please, if there are questions, they are welcome. Otherwise, this was the last presentation of this workshop, but the workshop is not finished. There is a last session in which you can interact with the presenters, even of the previous talks, and also to discuss for collaboration or whatever. Otherwise, you have the complete list of names of the authors of the presentation and of the presenters in the AI4Media program of this workshop, and of course you can interact with the project itself.
Okay, so thank you, Fabrizio. I would like to thank all the session chairs, all the presenters, and especially the two invited speakers. Not sure they're still with us, but they both gave great talks, very interesting topics. One message to the speakers. I see that some of you already uploaded the presentation in the shared drive. I did not, so like me, probably other forgot to do that. So please either send the presentation to me or upload it in the Google Drive so we can have an archive of all the presentations. I would like to say a few words, see if this can spin up a little bit of discussion. So first thing first, I really like the fact that we have seen, I think we have covered almost any modality in this workshop. I've seen video, I've seen images, I've seen 3D as a source for training models in other domains. And also we had music or audio in general. Okay, so this is a good sign that we are on the right track, I would say. And then a few remarks on some talks that made me think that there are maybe some connections that we may try to foster. As an example, starting from the presentation I gave, I think that maybe there's, apart from the ongoing collaboration with UCA, there may be possible intersection with the automatic cinematography, because of course the prediction of trajectory is really relevant in that domain. So we may discuss now or maybe offline about it. Another connection I think I may I may see is thinking about the deep clustering. Of course, there is a connection with learning from scarce data. there are a lot of methods that learn by clustering features and then using the clusters as pseudo labels. So maybe this is a good direction to see if we can go. And another thing I was thinking of, but maybe this is something that you should probably help me with understanding better. Can we somehow apply deep clustering to the summarization task? So I've seen a lot of methods that were using recurrent networks or generative adversarial models, but I think that maybe the ability to regroup can probably be of some help. And finally, the final remark is there are a lot of tasks that could benefit from multimodality. We have two partners working on audio. So I was thinking that maybe at some later stage of this work package, we could exploit the similarity in music and audio, either to perform multimodal summarization or multimodal retrieval. So this is something that I think I noticed from the whole bunch of works that I've seen in this presentation today. So if anybody wants to add something, or I don't know. So the Bimbo want to close it up, I don't know. No, Prof, muted.
Muted.
Yeah.
Sorry, apologies. So no, I don't want to add nothing because you know, you already pointed out with a good resume what has been done today. I believe that of course, if there are opinions, they are welcome. But the goal of this workshop is just to make all the partners aware of what is going on at each partner's side. So I believe that some collaborations already started. So one idea could be to you know, get a list of these collaborations quite soon. So I would like to ask all the partners to send us, to Lorenzo and me, the list of collaborations you have started in this 1 year development of the project, so that we can make this list available to everybody. And we hope that today these presentations have also given idea for other collaborations. In other words, the ultimate goal of the project is to establish strong connections between partners, so to reinforce the activity at each partner's site. So that's all. So I would like to know something from the audience, if someone wants to add comments or opinions.
I forgot to say something. So one thing that we really need to remember is that we have a partner which has a huge archive of videos. And in today's talk, they gave a very nice presentation on how they worked on the existing annotation. And of course, Rai has especially said that they are open for collaborations. So I think this is an incredible rich possibility to increase the impact of the research of everybody. So please keep in mind that we have this very strong industrial partner. And I don't remember the exact number of archive. I remember the generations that we have to pass to watch all the videos. So
15 generations.
15 generations, yeah. So no more hours of video, generation of watch time. So I really like the measure. Okay. So please, if you want to speak, let's open the discussion now.
Yeah, thank you very much for pointing out this thing. As you said, we are open to any form of collaboration. We have, unfortunately, we live times in which the burden and the overhead in determining whether or not a certain piece of content can be shared, can be used, can be employed in research is such high that one gets discouraged very easily. Because even before starting to think about any experiment, you have to solve such an amount of extra bureaucratic stuff, which is very far from our daily work, which is not always easy to maintain the, let's say, the confidence and the motivation. Having said that, I think that this is something that is felt also by others here. Yeah, both from on the technical level and on the data level, we are open to understand the requirements, to see what can be done in terms of trying to put the existing technologies and the technologies that are going to be developed under test with the real data, with data that are not, let's say, being already used for benchmarks or for other reference applications. So yeah, absolutely agree.
Johannes, I see you open the
yes.
Yeah, please go.
If I may, since you very kindly referenced our work. Yeah, so yes, I think that you're correct in both instances, that clustering and more specifically our idea may very well have uses in both representation learning through its use for pseudo labels. I mean, Schwab and DivClust recently demonstrated how that might be very effective. In the context of summarization, while I have to admit that it's not my field, so I have very little understanding of it. I have to admit that it crossed my mind when through the workshop that video summarization could indeed be done in reverse. Like instead of trying to have a model describe, in a sense, all the visual properties, you could separate the data based on those properties in different ways. So yeah, I think all these directions have merit, and I think Alberto earlier from RAI mentioned that as well. So yeah, I think we'll be very open to any ideas you might have about collaborations on this subject. Yeah.
Thank you. So anybody? Okay, so regarding the tracking of collaborations, this is something that we started to do with a shared doc. I think I may send a reminder email with the link. So if you're willing to update your going collaboration, if there is something new, so we can keep track of it, and that's good for reporting and also to manage the whole work package research. So I think if there is no more nobody else that wants to speak, maybe we can call it a day. It was we'll say long day, but interesting day. So maybe
we can close. We can close.
Okay. So thanks, Filareti, for setting everything up, for recording and sharing the video on Facebook. I've seen.
Thank you.
Time to
Thank
time.
you so much. Thank you so much.
So thank you for helping us organizing. So see you soon, guys.
Thank you, all the attendees and the
Thank you
keynotes.
all.
Thank you. Thank you very much.